Welcome to my course, Vector Calculus for Engineers. The course consists of 5 weeks. We'll cover vectors, differentiation, integration and curvilinear coordinates, line and surface integrals, and the fundamental theorems of vector calculus. Vector calculus is useful for engineers in a wide range of disciplines, but especially for those studying electromagnetism and fluid mechanics. In the first week, we'll learn the fundamentals of vectors, how to add and multiply vectors, how to use vectors in geometry, and how to derive vector identities. We'll also learn about the important concepts of scalar and vector fields. In the second week, we'll learn how to differentiate fields. We'll learn what a partial derivative is and how to use the chain rule. We'll define the gradient, the divergence, the curl, and the Laplacian. These differential operators will appear in some fundamental physics equations. We'll also learn how to derive some commonly used vector derivative identities. In the third week, we'll learn double and triple integrals. We'll also learn about polar coordinates in 2 dimensions, cylindrical and spherical coordinates in 3 dimensions. These curvilinear coordinate systems simplify problems with circular, cylindrical, or spherical symmetry. In the fourth week, we'll learn about line and surface integrals of scalar and vector fields. This will provide you the necessary definitions and skills needed to understand the crucial final week of the course. In the 5th and final week, we'll learn the very important fundamental theorems of vector calculus. These include the gradient theorem, the divergence theorem, and Stokes' theorem. Throughout the course, I'll discuss some interesting applications. Using partial derivatives, we'll derive the method of least squares. Using the chain rule, we'll derive the triple product rule and apply it to the ideal gas law. Using vector derivative identities, we'll derive electromagnetic waves from Maxwell's equations. Using polar coordinates, we'll derive Newton's equations for a central force. Using line integrals and surface integrals, we'll compute arc lengths and surface areas. We'll derive the work-energy theorem of physics and compute mass and electromagnetic fluxes. Using the gradient theorem, we'll derive the law of conservation of energy. Using the divergence theorem, we'll derive the continuity equation of fluid mechanics. And using both the divergence theorem and Stokes' theorem, we'll derive the differential form of Maxwell's equations. Thank you for joining me on this learning adventure of vector calculus for engineers. Let's get started. Welcome to week 1 of Vector Calculus for Engineers. In this week, we'll define vectors. We'll learn how to add and subtract vectors and how to represent them in Cartesian coordinates. We'll learn how to multiply vectors using the dot product and the cross product. We'll learn some analytical geometry and how vectors can be used to define lines and planes in 3-dimensional space. We'll define the Kronecker delta and Levi-Civita symbol and show how to use them to derive vector identities. Finally, we'll define scalar and vector fields. Fields will be used in the rest of the course to differentiate and integrate in 2 and 3 dimensions. Please join me in this first week of Vector Calculus for Engineers. So in a course on vector calculus, first we have to discuss the concept of a vector. So you usually see vectors as arrows, right? A starting point and an ending point, which is the tip of the arrow. A vector then is a quantity that has a length associated with it and a direction. It points in a specific direction. And in vector calculus, we're mainly going to be talking about three-dimensional space. So it lives in three-dimensional space. But it's not located at any particular position. So this vector you can move anywhere in space. It's not anchored in any particular spot. So let's talk about, we're going to have three vectors here to discuss. We have a vector A, a vector B, and a vector C. I'm going to use this notation of putting this arrow-like object on top of the vector to show you that this is a vector. Okay. Besides vector, we have scalars. Scalars are quantities that only have length, say. Not particularly length, but they're like real numbers. They're just numbers. For instance, a vector could be like the acceleration of a mass or an electric field. And a scalar could be like the mass itself. You know, what is the mass of the object, or what is the electric charge of a charged particle. Okay, so these vectors satisfy certain rules of algebra. They commute, so that means the commutative law is A plus B is equal to B plus A. That means you can add vectors, right? And addition is commutative. Addition is also associative. So if you add three vectors, A plus B plus C, if you add B and C first, it's the same as A plus B plus C, but you add A and B first. Okay? That's called the associative law. You can also multiply vectors by scalars. For instance, mass times acceleration is the acceleration vector multiplied by the scalar m, ma, as in Newton's law. How does multiplication by scalar work? Multiplication by a scalar will not change the direction of the vector, but will just change its length. Okay? Scalar multiplication of two vectors, A plus B, is distributive. So that's equal to a scalar times A plus a scalar times B. Okay, so these are the basic properties of algebra associated with vectors. So what I want to show you now is in a picture how one adds vectors, how does one add these quantities, and how does one subtract these quantities. Okay, so let's start with the addition of two vectors. So we'll look at A plus B. Okay. We can draw the two vectors. I will draw them in the plane of the light board. So let's say this is A, and this one is B. Okay, I put them so that their tails are touching. Vector A has a length and a direction. Vector B has a length and a direction. We can move these vectors around to wherever we want in space. The way you do vector addition is you place these vectors head to tail. So if we move this A vector down here, we would get the A vector would look like this. Or if we move this B vector over here, the B vector would look like this. A plus B is the vector that goes from the tail here to the connecting heads here. This vector. So this vector here is A plus B, which is also equal to B plus A, which is why you can get there in two different ways. So A plus B is formed by putting the tail of one vector on the head of the other vector and then drawing the vector that connects the tail to the head. Okay. What about subtracting vectors? So let's look at b minus a, right? Can draw the same sort of diagram. So this is a, this is b. Okay. So what is b minus a? Well, minus a is just the a vector pointing in the opposite direction. So the minus sign just changes, flips the direction of the a vector. So minus a is going to be looking this way, right? So this is minus a. And then we're all set up to draw a vector from their head to tail now. So we can draw a vector from tail to head. So this vector here will be b minus a. Okay? So how do we say that? The vector b minus a is obtained by putting these two vectors a and b tail to tail. But b minus a then will point from the head of vector a to the head of vector b. Okay? Points from the head of vector a to the head of vector b. Okay. So I'm showing you here then that vectors are these objects that have a length and a direction. They satisfy the usual rules of algebra or arithmetic in that it's commutative, a plus b is b plus a. It's associative over addition, and it's distributive with k a scalar. So k, a plus b is ka plus kb. I also show you how to add vectors. You add vectors by putting them head to tail. And I also showed you how to subtract vectors. You subtract vectors by flipping the direction of the negative vector, so that if they're tail to tail, then b minus a is the vector which is head to head that points from a, the negative one, to b. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. So we've talked about vectors, but in order to do algebra on vectors, you need to have a coordinate system. So the standard coordinate system is called Cartesian coordinates. It's the simplest coordinate system to use. In that coordinate system, you have, in 3 dimensions, you have axes that are mutually perpendicular. So on a 2-dimensional board, you can draw it like this. This will be the x direction, this will be the y direction, and this will be the z direction. If we have a vector, we can draw a vector with the base at the origin. So here's a vector. We want to know what point, what is it pointing to. This point here, this is our vector A, and we can call this point here A1, comma, A2, comma, A3, right? What that means is that if we drop this point onto the xy plane and then go over to the x-axis, go over to the y-axis, then this height here is A3, right? This is what our A3 is, the height above the xy plane. This length here is A2. and this length here is A1. Okay, so now we have a vector A. When you put the base at the origin, it points to A1, A2, A3. Remember, a vector doesn't have any particular location in space. So how do we write this vector A? We use what are called unit vectors. So we put our unit vectors, I show you them here. These are unit vectors. That means they have a length of 1 that point in the direction of the 3 axes. So the one that points in the direction of the x-axis is given the name of I. The one that points in the direction of the y-axis is given the name of J. And the one that points in the direction of the z-axis is given the name of K. I, J, and K are the unit vectors. It actually originates from quaternions, if you ever heard that word before. So how do we write a vector? We write the vector A then as the x component, A1 times I, plus the y component, A2 times J, plus the z component, A3 times K. Okay? So that's the coordinate representation of an arbitrary vector A. So how do you add vectors using Cartesian coordinates? Well, let's say we have a B vector of the same type. So we want to add A plus B. Then we would add the components. So it would be A1 plus B1 times I plus A2 plus B2 times J plus A3 plus B3 times K. Okay, so very simple to do vector addition when you have the vectors, when you have the components of a vector. What about scalar multiplication? So we can have K, a scalar, times a vector. All you do then is you multiply each component by K. So we would have K times A1 times I plus K times A2 times J plus K times A3 times the unit vector K. So here K is a scalar. This K here is the unit vector. So don't be confused with that notation. Sorry, should have chosen a different constant. Okay, one other thing we should know, what is the length of a vector? So the length of the vector is represented by this absolute value sign. This is the length of A, right? If you use Pythagorean theorem in three-dimensional space, this would be A1 squared plus A2 squared plus A3 squared, and then the square root. Okay? So that would be the length of a vector. Okay. There's two vectors that are widely used once you have a coordinate system. One vector is called the position vector. The position vector locates a point in space. So if you have some point x, y, z, the position vector, when you place the tail at the origin, then locates that point in space, points to that point. So we're going to call that vector in general, we're going to call the position vector r, and that will simply be xi plus yj plus zk. So that locates the point x, y, z in space. In addition to the position vector, we have something that's called the displacement vector. So let me draw a diagram here. If we have our axis, right, If we have two vectors, so two position vectors, say one here and one here, maybe this one is R1 and this one is R2. You might want to know what is the vector pointing from one of these vectors to the other one. So let's say R2 minus R1 would be this vector here is R2 minus R1. So R2 minus R1 is called a displacement vector. So let me write that here, displacement vector. And can be very useful because, say you have a physical problem, maybe you have two masses, one at position R1, the other at position R2. The force between the masses depends on the vector that's pointing from one mass to another mass. So you need to use the displacement vector. The displacement vector is simple to write. So R2 minus R1, right, will just be x2 minus x1 times I plus y2 minus y1 times j plus z2 minus z1 times k. Okay? So let me review what I've talked about. We're talking about Cartesian coordinates, the standard x, y, z coordinate system. I introduced unit vectors, I, j, and k, so that we can write a vector A in terms of its coordinates, A1 and A2 and A3, as A1i plus A2j plus A3k. Then you can add two vectors by adding their components. A1, A2, A3 are called the components of A, so we can add their components. We can multiply a vector by a scalar by multiplying the components by the scalar. Furthermore, the length of the vector is just the square root of the sum of the squares of the components. I also introduced two important vectors. One is called the position vector. It locates a point in space. And one is called the displacement vector, which is the difference between two position vectors. That gives you the vector pointing from the head of one of the position vectors to the head of the other one. Very useful in many, many physical problems. Okay, I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So we've talked about adding vectors. Now we have to need to discuss how do you multiply vectors. There are two types of ways of multiplying vectors. The first one I want to talk about is called the dot product. Sometimes it's called the scalar product. And that's because the multiplication of two vectors results in a scalar. So let's look at the vectors. Say A, we're going to write in component form, is A1i plus A2j plus A3k. And B, the same form, B1i plus B2j plus B3k. So the dot product then is written as A dot B is a scalar product, so the result is a scalar. And quite simple. You multiply the components, A1, B1, and A2, B2, and A3, B3, and then add them. So A1, B1 plus A2, B2 plus A3, B3. Okay, and that's a scalar now, right? Because there's no vector here on the right-hand side. So what is the algebra of this dot product? It's easy to see that multiplication commutes. So A dot B is equal to B dot A. And it's easy to see that multiplication distributes over addition. So A dot B plus C is equal to A dot B plus A dot C. And then when you multiply a vector by a constant, one can also see that A dot a constant, let me call the constant D, say. A dot D times B equals D times A dot B is equal to D times A dot B. Okay? So that's the definition of the dot product, and we see its algebra. There's another way of defining the dot product that's a little bit more geometrically. So if we look at two vectors, so here's one vector, and here's a second vector. Okay? So let's say this vector is A and this vector is B. We can define a coordinate system to compute the dot product. So you're given vectors and you're free to choose any coordinate system you want. So let's choose the coordinate system that is where the x-axis is just along the A vector. And then the y-axis is perpendicular. Okay? We choose this coordinate system, and then we can try to compute A dot B. So we have these components. So what are the vectors in terms of the components? Well, A vector, right, is along the x-axis, and it has a magnitude of A. So this is the length of A, and it's along the x-axis. So we have the I vector. Okay. What about B? Right. So we can find the two components of B. We can drop here. We can use some trigonometry here. So this is an angle theta. So the base here is the length of the hypotenuse times the cosine of the angle. And the height here is the length of the hypotenuse times the sine of the angle. So B is equal to the length of B times cosine theta times I plus the length of B times sine theta times J. Okay? So by having two vectors, two arbitrary vectors, we can impose a coordinate system where x-axis is along one of the vectors and the vectors lie in the xy plane. Then we get this component forms of A and B, and we can compute A dot B. So then A dot B is just the magnitude of A times the magnitude of B times cosine theta. Right? Plus the 0 times B sine theta, because the J component here is 0. The Y component is 0 for A. So this is the dot product of A and B. And you see that this is independent of coordinate system. So this is true in any coordinate system. A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Okay. There's 2 points I would like to make here. What happens if A and B are parallel? So if A is parallel to B, right, that means that B is a scalar constant times A. If A and B are parallel, B is a constant times A. Then A dot B is going to be the magnitude of A times the magnitude of B, right? The angle here is 0 and cosine theta. Cosine of 0 is 1. What if A is perpendicular to B? Then theta is pi over 2, and cosine of pi over 2 is 0. So that means for 2 perpendicular vectors, A dot B is equal to 0. Okay, let me review. I'm introducing what's called the scalar product. Most frequently it's called the dot product. It takes 2 vectors, A and B, and we write A dot B. We say A dot B, and that is just the product of the components summed over all components. So 3 terms in the dot product. It's a scalar. There is no vectors on the right-hand side. From this definition, the dot product is commutative. It's distributive over addition, and a scalar can be multiplied against any vector. Doesn't matter. Finally, we can have a geometric definition of the dot product. A dot B is the length of the vector A times the length of the vector B times the cosine of the angle between them. What that means is that if A is parallel to B, meaning that A is equal to a scalar times B, then A dot B is just the length of A times the length of B. And if A is perpendicular to B, then A dot B equals 0. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. We've talked about the dot product or the scalar product. So in this video, I want to talk about the cross product or the vector product, because the cross product results in a vector. So let's start with 2 vectors. So we have the vector A, which is A1I plus A2J plus A3K. And we have the vector B, which is B1I plus B2J plus B3K. And I want to form the cross product of A cross B. The cross product is a vector, and it's quite a bit more complicated than the dot product. The way to remember what the vector is to use a 3x3 determinant. So what you do is you write this where the first row of the determinant is the unit vectors I, J, and K. The second row of the determinant are the components of A, so A1, A2, and A3. And the third row of the determinant is the components of B, so B1, B2, and B3. So this 3x3 determinant. And that's how you remember the cross product. You can compute the determinant. You can write it out in long long form. So you eliminate the first column and the first row. So that will be multiplied by I. And then you get A2B3 minus A3B2. A2B3 minus A3B2. And that goes in that's the component along the x direction, multiplied by the I unit vector. The second one, you eliminate the second column and the first row. That one has a minus sign, so we end up with A3B1, so plus A3B1 minus A1B3, and that goes in the j direction. And then the k direction we get by eliminating the first row in the third column, and then we get A1B2 minus A2B1, and that goes in the k direction. Okay? So this somewhat complicated expression, which is just a 3x3 determinant, defines the cross product. Okay. There's a cross product satisfies certain properties similar to the dot product. The main difference here is that if we look at A cross B and commute A and B to B cross A, how does it change? Well, B cross A means we change the rows of this determinant. You may remember from the theory of determinants that when you interchange rows of a determinant, you change the sign. So this gets a minus sign. So A cross B is equal to minus B cross A. Okay. We can also look at a geometric definition of the cross product. So let's look at two vectors. So vector A, say, I'll draw it here, and a vector B, can draw it here. In order to figure out the cross product, we can impose a coordinate system on here. So I'm going to use the same trick I used for the dot product. I'm going to put the x-axis along A and the y-axis perpendicular. So as before, A here is going to be the magnitude of A times the I unit vector, and B is going to be the magnitude of B times the cosine of this angle. So the angle between A and B, the acute angle between A and B is theta. So it's the magnitude of B times the cosine of theta times I, plus the magnitude of B times the sine of theta times J. Okay? Then we can compute A cross B. But in order to get a result which is independent of coordinate system, I'm going to compute the magnitude of A cross B. So what is the length of this vector? Okay? We can do it from the magnitude of this determinant, or else we have the expression here, so we might as well use it. Here, A2 and A3 are 0, so all we have is A1. And here, all we have is B1 and B2. So we only have the term with A1 and B1 and B2 in it, which is only single term, which is this one. Okay? So only one term in this expression. So the magnitude then is just going to be A1 times B2, which is going to be equal to the x component of A, which is the magnitude of A, times y component of b, which is the magnitude of b times sine theta. Okay? And this is a coordinate independent expression. So it doesn't matter how I defined the coordinate system here. A cross b magnitude, the length of A cross b is just the length of A times the length of b times the angle between A and b, independent of coordinate system. So this is in general true. Okay, one thing missing. In which direction does A cross B point? Okay, given A and B. To do that, we have something called the right-hand rule, R-I-G-H-T, hand rule. Okay? The right-hand rule, you have to take your right hand, okay? You point your fingers in the direction of A to determine the direction of A cross B. You point your fingers of your right hand in the direction of A. You curl your fingers in the direction of B, and then you get the direction of A cross B, which will be coming towards you. Okay? So the direction of A cross B is towards you when you use your right hand. So you should try that. You should lift up your right hand, put your fingers in the direction of A, curl your fingers in the direction of B, and then the thumb will point in the direction of A cross B. Okay, it should be towards you. One more comment that I would like to make. What happens if A and B are parallel? So if A and B are parallel, B is a constant times A, then theta equals 0 and sine theta equals 0. So if A is parallel to B, then A cross B equals 0. Okay? So that's a big difference between the cross product and the dot product. If A and B are perpendicular, then A dot B equals 0. But if A and B are parallel, then A cross B equals 0. Okay, so let me summarize. The cross product is sometimes called a vector product because the cross product gives you a vector. You can compute the cross product, A cross B, from this 3 by 3 determinant. That's how you remember the cross product. The magnitude of the cross product of A cross B is the length of A times the length of B times the sine of the angle between them. And finally, you need to use the right-hand rule to determine the direction of A cross B. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. In this lecture, I want to show you how vectors can be used to describe objects in three-dimensional space. In particular, in this lecture, I'll talk about lines, and in the next lecture, I'll talk about planes. This is called analytic geometry. So how do we describe a line in three-dimensional space? So we have some axis. Right, this is our x, y, z axis. And then we have some line in three-dimensional space. So here's some line, okay? We want to locate a point on this line using a position vector. So here is a position vector. So this is r. So we locate a point on the line using this position vector. So we would like to know how to express r. So we can have another point on the line. So let's call this point r0. So it has position vector r0. And to get to r, we draw another vector that looks like this, right? So that r0 plus this vector that points along the line gives us r. So how do we model this vector that points along the line? Well, we can call it a u vector. U will stand for velocity times t, say. So as we vary the parameter t, then we can move anywhere we want on this line. Okay? So the equation for the line then will be the position of a point on the line is equal to the initial position plus the u, the velocity vector, times t. Okay? So this is actually a particle then moving with velocity u. That describes a particle moving with velocity u. So this u then can be determined as a displacement vector between 2 points on the line, right? So if you take any 2 points on this line, you can construct a u as the displacement vector between those 2 points. And then t is a parameter here. So this is called the parameterized version of the line. So we can write this in component form. In component form, the I vector, the x component, would be x equals x naught plus, and if u is u1i plus u2j plus u3k, it would be x equals x naught plus u1t, y equals y naught plus u2t, and z equals z naught plus u3t. Okay? Taking these together, we can eliminate t, and we get a non-parametric form for this line in three-dimensional space. Eliminate t, we get x minus x naught divided by u1, and that's equal to y minus y naught divided by u2, and is also equal to z minus z naught divided by u3. So that would be a non-parametric form for the line, because there's no t here. T is the parameter. Okay, so let's use this model for the parametric form for a line in three-dimensional space. Very easy to remember. Its position vector is equal to its initial position vector plus the velocity vector times time. Okay? Let's solve this problem that I've written on the light board. Find the parametric equation for a line that passes through 2 points. The 1, 2, 3, right? X, Y, Z coordinate is 1, 2, 3, and 3, 2, 1. Then after we find the parametric equation, then we're going to determine the intersection point of the line with the z equals 0 plane. Okay, so how do we find the parametric equation? So we need some initial points, so we might as well take r naught equal the position vector of the point 1, 2, 3. So that would be I plus 2j plus 3k, right? Then we need a velocity vector. So the velocity, the magnitude doesn't matter. It's the direction that's important. And the direction you find by a displacement vector between 2 points on this line. We have these 2 points. So we can take the velocity vector to just be the displacement vector between this 3, 2, 1 point and this 1, 2, 3 point, which would be 3 minus 1, which is 2 in the I direction, plus 2 minus 2, which is 0 in the j direction, plus 1 minus 3, which is minus 2 in the k direction. Okay, then putting it together, we have r is equal to r naught plus ut, right? So we get r equals r naught plus u times t, so 1 plus 2t times I, r naught plus u times t. There's no j in u, so plus 2j. And then 3 minus 2tk plus 3 minus 2tk. Okay, so this gives us then the parametric equation for the line in three-dimensional space. So r is any point on the line, and we can get to any point by varying the parameter t. So part B is determine the intersection point of the line with the z equals 0 plane. That means we're interested in when the position vector has 0 in the z component. Okay, that would be the intersection point. So this is A. And then B, we want 3 minus 2t equal to 0, which implies that t is equal to 3/2. Okay? So when t equals 3/2, the line goes through the xy plane. And then the intersection point then, so the intersection point will be xy, right? Will be the value of the x component and the y component when t equals 3/2. So 1 plus 3, 2 times 3/2 is 3, so 1 plus 3 is 4. So this will be the point x equals 4, and then y is always equal to 2. Okay, that's a 2. So this is the intersection point of this line with the z equals 0 plane. So let me summarize. Using vectors, we can do some analytic geometry. The simple problem here is to use vectors to describe, to give a mathematical formula for a line in three-dimensional space. We do that by means of this parametric equation, where the position vector of a point on the line is equal to the position vector of an initial point on the line plus the velocity times t. Okay? The velocity has an arbitrary magnitude or length, but the direction is specified by the displacement vector between 2 points on this line. Then we have a non-parametric equation for the line. And by using a parametric equation, we can answer a simple question such as which point does this line go through when it crosses the z equals 0 plane? And that's what I do in this problem. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So in this video, let's talk about the analytic geometry of planes. So these are a description of planes in three-dimensional space. To determine a plane, you need 3 points that are not collinear. And those 3 points will have 3 position vectors. So let me call the position vectors R1, R2, and R3. Okay. From 3 position vectors, we can construct 2 displacement vectors. The displacement vectors will then lie in the plane. So those displacement vectors can be, say, S1 equals R2 minus R1, and S2 equals R3 minus R2. Okay? So now from the 3 position vectors, we have 2 displacement vectors that lie in the plane. Their cross product of 2 vectors that lie in the plane will be perpendicular to the plane. Okay? So then we can construct a vector now that is perpendicular to this plane. So let n then be perpendicular or normal to the plane. And we can construct n by just taking the cross product of the displacement vectors. Okay? So now we have a vector which is perpendicular to the plane. So that means the dot product of n with any vector that lies in the plane is going to be 0, right? So if we have a vector perpendicular to the plane, the dot product of that vector with any vector that's lying inside the plane is 0. That gives us an equation. So we have n dotted into any vector which lies inside the plane. So that means r is the position vector for any point that lies inside the plane. And it has to be a displacement vector to lie in the plane. So we need to subtract this from one of R1, R2, or R3. You can choose any one and you'll be fine. But let's, for sake of argument, just choose R1. And because the normal vector, right, the perpendicular vector, is perpendicular to this displacement vector, then the dot product will be 0. Okay? That's the equation for the plane. Okay, what type of equation is that? Well, this r, right, this r is just the displacement vector for any point in the plane. So any point in the plane we're going to call x, y, z, right? So r is the position vector, sorry, for any point in the plane. So r is going to be xi plus yj plus zk. Okay. The normal vector we obtain by S1 cross S2. So we're going to calculate what the normal vector is. But for sake of argument here, let's say we calculate it, and we're going to call that simply AI plus BJ plus CK. Okay? That will give us n dot r, and then we need n dot r1, so we can just call n dot r1, this is a scalar, so whatever that is, we'll just call it d. And so putting this together, we have n dot r equals n dot r1. N dot r will be ax plus by plus cz. And that's equal to n dot r1, which is d. Okay? That's a equation for a plane in three-dimensional space. The important thing here is that these coefficients, a, b, and c, are just the components of the normal vector to the plane. Okay? And this gives us then an equation satisfied by any point x, y, z that lies inside of the plane. To make all of this concrete, let's look at an example. So I want to find an equation for the plane defined by 2, 1, 1, 1, 2, 1, and 1, 1, 2. So 3 points are given. And then we're going to find the equation for the line formed by this plane and the z equals 0 plane. So when two planes intersect, you get a line. So let's solve this A part first. So we have three position vectors, right? We know how to determine R1, R2, and R3 from these points. But what we want then are two displacement vectors. So let's write down the displacement vectors. So we have S1. Let's say it's R2 minus R1. So it will be 1 minus 2 is minus 1, so minus I. And 2 minus 1 is plus 1, plus j. And 1 minus 1 is 0. So the first displacement vector, this is a vector that lies in the plane, is minus I plus j. The second displacement vector we can get from the position vector corresponding to this point, R3 minus R2. That would be 1 minus 1 in the I direction would be 0. 1 minus 2 is negative 1, so that's in the j direction. Plus 2 minus 1 is 1, and that will be in the k direction. Okay? These two vectors then lie in the plane, and then their cross product is normal to the plane. So we can find the normal vector n by the cross product of these two vectors. So S1 cross S2. It doesn't matter what direction n is in. So we can do S1 cross S2 or S2 cross S1. Doesn't make any difference. We can use the determinant to compute this. So this would be I, j, k. S1 is minus 1, 1, 0. And S2 is 0, minus 1, 1. Okay? And we can calculate this 3 by 3 determinant. This is the cross product. So it's I. We eliminate the first row in the first column. So I times 1 minus 0, so just I. And then it's j, 0 times 0 minus minus 1, or plus 1, so it's plus j. And then it's k, minus 1 times minus 1 is plus 1 minus 0, so that's just plus k. So this vector I plus j plus k then is perpendicular to the plane. And then finally, we can use this n dot r minus r1. So the normal vector dotted into a displacement vector in the plane is supposed to be 0. That's equivalent to n dot r, right, equal to, so we can do just directly do n dot r. Let me write that here. We can directly do n dot r equals n dot r1, right? So this one is our, so r is our xi plus yj plus zk. So n dot r will be x times 1, so x plus y plus z will be n dot r, right? Because n is just has components 1, 1, and 1. So this is n dot r, and that's supposed to be equal to n dot r1. So r1 is the position vector of 2, 1, 1. So n dot r1 will be 2 plus 1 plus 1 is 4. Okay? And that's the equation then for the plane. So this equation, this plane here then goes through these 3 points, which you can see, right? So 2 plus 1 plus 1 is 4. 1 plus 2 plus 1 is also 4. And 1 plus 1 plus 2 is also 4. Okay? And this is an equation for the plane. That's part A. Now for part B, find the equation for the line formed by this plane and the z equals 0 plane. For part B, all you have to do is then take z equal to 0. And then we get a line in the xy plane. With z equals 0, then we'll get y equal to minus x plus 4. Okay? And so that's the intersection of those two planes. It gives us a line. Okay, let me summarize. We're trying to describe a plane in three-dimensional space using vectors. The plane is given by 3 points. Those 3 points, we can write 3 position vectors, right? So R1 here, for this example, would be 2i plus j plus k, right? 3 position vectors. And then from 3 position vectors, we can compute 2 displacement vectors. The displacement vectors lie in the plane. So to construct a normal to the plane, we just need to take the cross product of the 2 displacement vectors. Once we have a normal to the plane, then the dot product of the normal to the plane to any displacement vector that lies in the plane is going to be 0. So by the condition that it's any displacement vector, that means we can put in an r here, which denotes the position of any point in the plane. Okay, so r is xi plus yj plus zk, and we end up with an equation ax plus by plus cz equals d, where a, b, and c are the components of the normal vector to the plane. And here's the fully worked example. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. In this lecture, I want to introduce 2 mathematical objects that are widely used in applied mathematics. The reason that we need that at this point is because I'm going to use them to derive vector identities in the next lecture. So the first one is the Kronecker delta. So what's the definition of the Kronecker delta? It has a symbol delta. That's a small delta. And it has 2 indices, I and j. We're talking about 3-dimensional space. So I and j can take the value of 1, 2, or 3. So for instance, delta 1, 1, or delta 1, 2, or delta 1, 3, or delta 2, 1, etc. And then this has 2 distinct values. It will be equal to 1 in the case when I is equal to j. So delta 1, 1 is 1, delta 2, 2 is 1, and delta 3, 3 is 1. And it's equal to 0 if I is not equal to j. So something like delta 1, 2 or delta 1, 3 would be 0. That's the Kronecker delta. The other symbol is the Levi-Civita symbol. That's an epsilon. This is an epsilon. That has 3 indices, I, j, and k. Of course, you don't have to call the indices I, j, and k. You can call them L, M, and n. You can call them anything you want. But here I'm using I, j, and k. Again, I, j, and k can take values 1, 2, or 3. This one has 3 possible values. So it will be a 1 if this I, j, and k pair is one of the following. It can be 1, 2, 3. Or it can be what's called a cyclic permutation of 1, 2, and 3. So that means that we always keep the same order. So 1, 2, 3, 1, 2, 3, 1, 2, 3. But we start with 2, so it would be 2, 3, 1. Or we start with 3, so it would be 3, 1, 2. Okay? Then it gets the value of 1. So in 3 cases, with 3 numbers in these indices, it gets the value of 1. It gets the value of -1 if I, j, and k are in non-cyclical order. So that means we go backwards instead of forwards. So we have 3, 2, 1. We can start with 3, 2, 1. And then we can go 2, 1, 3. And finally, we can go 1, 3, 2. Okay? But I can take one of 3 values, j can take one of 3 values, and k can take one of 3 values. So this symbol can take 3 times 3 times 3 is 27 different values, 27 different values. Here we've only talked about 6, so that means the remainder of 21 are going to be this third case, which is 0. And it's hard to see, but the remainder of 21 means that either I equals j, or j equals k, or k is equal to I. And those are all the other cases. So that means the number repeats in one of these indices. Okay. In addition to these 2 symbols, to make our algebra cleaner, we're going to use something that's called the Einstein summation convention. This is the famous Einstein of E equals mc squared fame, among other things. What is the Einstein summation convention? What it says is repeated indices are summed over. Repeated indices are summed over. So if we wanted to sum, say, from I equals 1, 2, 3 of delta I, right? This notation means delta 1, 1 plus delta 2, 2 plus delta 3, 3. In the Einstein summation convention, we would just write delta I. Okay? So instead of saying, putting the summation symbol explicitly in this convention, if the index is repeated, so if there are 2 i's in the index, it means by default you're summing from I equals 1, 2, 3. Okay? The purpose of that convention is that you don't have all this algebra where you have to keep carrying all these summation signs. The story is that Einstein's printer actually invented it, so he doesn't have to carry summation signs. But it turned out to be very handy, and everybody uses it. So this means, like I said, delta 1, 1 plus delta 2, 2 plus delta 3, 3. All of those have a value of 1, so this is 1 plus 1 plus 1, so this is 3. Okay? Let me give you another example. If we look at epsilon I, j, k times epsilon I, j, k, we're under the Einstein summation convention. So that means we're summing from I equals 1, 2, 3, j equals 1, 2, 3, and k equals 1, 2, 3. Okay? So there's a lot of terms here. There's, in fact, 27 terms here, right? But most of them are 0. So which ones are not 0? For instance, if we look at epsilon I, j, k, if I, j, and k are 1, 2, 3, then that one is not 0. So this could be epsilon 1, 2, 3, epsilon 1, 2, 3. Or epsilon 231 times 231 is not 0. Epsilon 312 times epsilon 312 is not 0. So we have a bunch of terms. Only 6 of them are not 0, right? Only 6 of them. The other ones are 0 times 0. So in these 6 of them, we have 3 of them are 1 times 1, and 3 of them are minus 1 times minus 1. Minus 1 times minus 1 is also 1. So there's 6 terms here. So this is a 6. Okay? I hope, well, when you do the problems, you'll get a feeling for this Einstein summation convention. You'll get a feeling that when you contract 3 indexes, means you have 27 terms, okay? But most of them will be 0. Okay, to do the homework, you're going to need an identity. Let me write that down here. If we look at epsilon I, j, k times epsilon L, M, N, we have 6 indices here. None of them are repeated, so none of them are what we say contract. There's no summation over any indices. So the right-hand side will depend on all 6 indices. But there's a identity here, which is, I won't prove, but is a very beautiful identity. It relates the Levi-Civita symbol to the Kronecker delta. This is a 3-by-3 determinant. So the first row we can construct as delta I, L, I from the first symbol and L from the second, and then delta I, M, I from the first symbol and M from the second, and then delta I, N. And that's the first row of the matrix. The second row we take from J, so we would have delta J, L, delta J, M, and delta J, N. And the third row we take from K, so we'd have delta K, L, delta K, M, and delta K, N. And this 3-by-3 determinant is equal to epsilon ijk, epsilon lmn. A little bit challenging to prove. I think if you wanted to prove this, you would prove it based on symmetry, that somehow the symmetry in the indices on the left is equal to the symmetry of the indices on the right. But I think there's no point in asking you to prove this. What I do ask you to prove is how does this identity collapse when we sum over some of these indices? So what would epsilon ijk, epsilon I, M, N equal? So we sum over the first index. That expression is going to be used by me in the next lecture. So I hope you will look at the problems and figure out these identities when you contract the index. Okay, the last thing I want to do is relate this to the dot product and the cross product. The dot product, A dot B, let me just write that as AI BI, because this will be what I commonly do later. What this means, AI BI, we're going to be working under the Einstein summation convention. So that means A11 plus A1B1 plus A2B2 plus A3B3. That's the dot product, right? The other one is the cross product, is a little bit more tricky. So let me write that here. If we look at A cross B, that's a vector, right? So how do we get a vector here? In order to get a vector, we can't just look at A cross B. We have to look at a component of A cross B. So I'm going to write A cross B sub I. So that means the ith component. So if I equals 1, that will be the first component of A cross B. If I equals 2, it will be the second component. And if I equals 3, it will be the third component. Okay. I claim that you can write this using the Levi-Civita symbol as epsilon, where the first index is the component you're looking at, and the next two indices, I, J, K, are contracted with the index of A. A gets the J, the second index, and B gets the K. Okay? This will be the main use of the Levi-Civita symbol. So the ith component of A cross B is epsilon ijk, aj, bk. J and k are summed over. So let's see if that makes sense. Okay? Let's see if that makes sense by seeing how does this work if I equals 1. Okay? So for instance, A cross B index 1, so the first component, right? So that means I equals 1, so it's epsilon 1 j k a j b k. And we're summing over j and k. So remember, the Levi-Civita symbol will be 0 if any of these indices are the same. So there are only two possibilities now when those indices are not the same. So j can be 2. So 1, 2, and then k is 3 times A, 2, B, 3, plus, or j can be 3 and k can be 2. So epsilon 1, 3, 2, A, 3, B, 2. Okay, almost done. Epsilon 1, 2, 3 is plus 1. Epsilon 1, 3, 2 is a non-cyclic permutation of 1, 2, and 3. So that's a minus 1. So this is then equal to A, 2, B, 3 minus A, 3, B, 2. And if you remember your cross product, that is exactly the first component of A cross B. Okay, so let me summarize. In this lecture, I introduced the Kronecker delta, delta ij, and the Levi-Civita symbol, epsilon ijk. And I tell you I'm going to be using the Einstein summation convention so that if an index is repeated, it will be summed over. We'll only see cases where an index is repeated twice. Okay? Indices will be repeated twice. We have this identity of which relates the Levi-Civita symbol to the Kronecker deltas. This will be useful in deriving some of our results, particularly when the first index is contracted. So epsilon ijk, epsilon imn. Finally, under the Einstein summation convention, A dot B is just written as AI bi. And A cross B, the ith component, can be written in terms of the Levi-Civita symbol. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So we learned about the Kronecker delta, the Levi-Civita symbol, and the Einstein summation convention. The purpose is to prove some vector identities. These vector identities are useful when you manipulate equations such as occurs in fluid mechanics or in electricity and magnetism. So I'm going to talk about 4 vector identities In the lectures, I'll prove 2 of them and then ask you to do 2 of them as problems. So let's go through them. There's 2 types of vector identities. There's scalar vector identities, where the left-hand side is a scalar and the right-hand side is a scalar. And there are vector identities, where the left-hand side is a vector and the right-hand side is a vector. So when 2 vectors are equal, it means that all of their components are equal. So that's essentially 3 equations, but we can solve them as a single equation. So let's go through them. The scalar triple product then is a scalar vector identity. It says that A dot B cross C, so B cross C is a vector and A is a vector, so A dot B cross C is a scalar. That's equal to B dot C cross A is equal to C dot A cross B. So the equality is basically a cyclical rotation of ABC. So A, B, C, B, C, A, C, A, B. Okay? The vector triple product is also having to do with 3 vectors, but this is a vector identity. Here, A cross B cross C, so B cross C is a vector, and A cross a vector is a vector. It says that A cross B cross C is equal to A dot C, a scalar, times B, a vector, minus A dot B, a scalar, times C, a vector. Okay? That's the vector triple product. The third identity is the scalar quadruple product. That's a scalar vector identity. Quadruple means that there are 4 vectors involved. Here, A cross B dot C cross D. So it's a vector dot a vector, which is a scalar. That's equal to A dot C, which is a scalar, times B dot D, which is also a scalar, minus A dot D times B dot C. So A dot C, B dot D, minus A dot D, B dot C. Okay? So all these have some type of symmetry if you look at them carefully. The 4th one on this list, there are also other ones, but I'm going to just discuss these 4. The vector quadruple product is a vector identity. Quadruple, so it has 4 vectors. It's A cross B cross C cross D. So that's a vector cross a vector is a vector. That's equal to A cross B dot D, that's a scalar, times C, a vector, minus A cross B dot C, a scalar, times D, a vector. Okay. How do we prove these identities? We need a toolbox, which we already developed. So let's go through what we will need in our toolbox. If we look at the Levi-Civita symbol, epsilon I, j, k, we're allowed to cyclically permute these indices. So this is equal to epsilon jki and is equal to epsilon kij. Okay? So that's kind of an operation we're allowed with this Levi-Civita symbol. That's one of the elements of our toolbox. The next element will be what happens if we contract one of these indices. So epsilon I j k times epsilon I m n, right? So we're working under the Einstein summation convention. So that means where I is repeated, so that means we say that I is contracted if an index repeats. That means we're summing over I. So we're summing over I equals 1, 2, 3. So there are 3 terms here, right? That's the summation. This reduces to products of Kronecker deltas. So as a problem, you're supposed to prove this. This is equal to delta Jm, delta Kn, right? minus delta Jn delta Km. Okay? This is a very important identity that we'll use in the proof of these vector identities. So how do you remember this? So we're only contracting the first index. Usually, I like to always put the contracting index in the first slot. I can do that by using this cyclical identity for the indices. So we contract the first index, and then we have delta Jm Kn. So you see second index, third index, and then minus Jn Km. So second index, third index, second index. Okay, so that's how you can remember that identity. Okay, another identity is delta ij a sub j under the Einstein summation convention. So this is sum from j equals 1 to 3. The Kronecker delta then is 0 unless j is equal to I. So that picks out a sub I. If you wrote out all three terms, you would see that this is the identity. It actually doesn't matter whether j is the second index on the Kronecker delta, or this was delta ji, since delta ij equals delta ji. But it looks prettier if we contract the second index, that's all. Finally, what I've talked about already, we can write A dot B using the Einstein summation convention is just AI BI, right? So sum over I, so A1 B1 plus A2 B2 plus A3 B3. So the dot product can be written in terms of these index symbols. And the other product is the cross product. So A cross B. But you have to say what component you're looking at. So I use this bracket symbol and put a subscript I here. So that means we're looking at the ith component of A cross B. This can be written very nicely in terms of the Levi-Civita symbol. This is epsilon. The ith component you put in the first index of the symbol, and then two other indices, here I call them jk, they're going to be summed over. The second index will correspond to A, so this will be AJ, and the third index will correspond to B, and that will be BK. Okay? So this cross product can be written in terms of A cross B, the ith component is epsilon ijk aj bk under the Einstein summation convention. So you can show that as a problem. Okay? And that's all the tools we need. So let me summarize. These are four sometimes useful identities when you're dealing with the vectors of electricity and magnetism, the electric field, the magnetic field, or the equations of fluid mechanics, where the velocity field then is a vector. And then I want to at least show you how such identities can be proved using the Kronecker delta, the Levi-Civita symbol, and our Einstein summation convention. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. In this video, I want to show you how to prove the scalar triple product identity. It's A, so three vectors, A, B, and C. A dot B cross C is equal to, then you can do a cyclical permutation of A, B, and C. So you can move B in the front, B dot C cross A, and then you can move C in the front, C dot A cross B. So I'll show you, I'll step you through the proof of this using the Levi-Civita symbol. So proof. We start with the left side. So A dot B cross C. We write that using the Einstein summation convention. So this would be AI. And I'll go slowly in this first equality so you can see all the steps. So we're using the Einstein summation convention. So this is B cross C, the ith component. So we're summing now over the I equals 1, 2, and 3. We can then write the cross product using the Levi-Civita symbol. So this would be AI. And then B cross C ith component will be epsilon I, J, K, B, J, C, K. Okay? So now we've broken down this scalar simply in terms of the components of A, B, and C and this Levi-Civita symbol. So here we're summing over I, we're summing over J, and we're summing over K. So there's 3 summation signs here which we don't write because we're using the Einstein summation convention. Okay, now we're trying to get to B dot C cross A. So I would like to have the B in front. So these things commute. So I write B, J here. But now I want to move these indices so that J then gets the front index. So remember that epsilon ijk is equal to epsilon jki as long as we keep the cyclic order the same. So I put J in the first index, so that becomes epsilon jki. And we want here a CA, so it will be CKAI. Okay, so all I've done here to get to this step here, we know that numbers commute, so I'm allowed to change the order of the symbols for A, B, and C. But the big step here is that epsilon jki is equal to epsilon ijk. If we look at this, this is just a dot product. So this is bj times, if I use the same notation, C epsilon jki ckai is C cross A, and it's the J component. Okay? Finally, this then is the dot product, Jj. So this is B dot C cross A. Okay? So that got us from A dot B cross C is equal to B dot C cross A. Okay. I'll show you how I would actually do it in the next identity. So we want to get from B dot C cross A equal to C dot A cross B. What I would do then is I would start with B dot C cross A. And then I would do it all in one step. So the dot product would be BI. And then against the ith component of C cross A, so I would write epsilon I, and then JK, C, J, A, K. So I would jump a step, right? And then we would use the cyclical nature. So I would want C in the front. So we would have CJ. And then I would have an epsilon. So I would have epsilon jki. And then I want an A and a B, so I would have an A, K, B, I. Okay? And then immediately I would see that this would be epsilon jki akbi is the jth component of A cross B. So we would have Cj times the jth component of A cross B. So that would immediately give us C dot A cross B. Okay? So I would skip another step. Okay? So that's how I would typically prove this. Here I make it, add a couple of extra steps so that you can see what I'm doing. Okay. That's the proof of the scalar triple product. Another way of looking at the scalar triple product is by considering A dot B cross C. B cross C is a determinant, right? We've learned how to write a cross product as a determinant. This is equal to A dot the determinant, where we have the unit vectors in the first row, I, J, K, the B components in the second row, B1, B2, B3, and the C components in the third row, C1, C2, C3. So what is this A dot, this determinant? We would have, that would be A1 times the ith component, right, plus A2 times the jth component, plus A3 times the kth component, which then works out to the 3 by 3 determinant, A1, A2, A3, just dotting A into these I unit vectors, B1, B2, B3, and C1, C2, C3. So the scalar triple product is actually just this 3 by 3 determinant. And this identity here is basically just the cyclical permutation of the rows of the determinant. If you keep the rows in the same cyclical order, then the determinant doesn't change. Okay, that you have an identity with the determinants. And that's what this relationship is saying. Okay, this 3 by 3 determinant is actually a volume. And it's the volume of this parallelepiped. So the volume here is just this 3 by 3 determinant, which is just A dot B cross C. Okay? And this could possibly be negative, so it's actually the absolute value. Okay? You can, when you learn what a determinant is, you learn that the 2 by 2 determinant can represent an area, and the 3 by 3 determinant can represent a volume. Okay, let me summarize. In this video, I'm trying to show you how one proves these vector identities. We're looking at the scalar triple product, which is sometimes a useful vector identity. It also is a useful quantity because it represents the volume of a parallelepiped. In the proof, then, I show you how to use the Einstein summation convention, and I show you how to manipulate the Levi-Civita symbol. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. In this video, let's prove the vector triple product. This is a vector-vector identity. So it's A cross B cross C, 3 vectors. equals a dot c, which is a scalar, times b, which is a vector, minus a dot b times c. So let's work the proof. We start with the left-hand side. So a cross b cross c. And we're going to prove this for each component. So we're going to prove this, say, for the ith component of that vector. We can write this using the Levi-Civita symbol. So it's the ith component. So we can use epsilon I, j, k. And then we have an a, j. And then we have the kth component of b cross c. So let me write that as b cross c. And we'll consider here then the kth component. So we're writing this first cross product here using the Levi-Civita symbol. And then this second cross product we can write again using the Levi-Civita symbol. So we have our epsilon I, j, k, a, j. And then the kth component of b cross c will be epsilon k. And then I'll use lm, say. And we'll have a b sub l and a c sub m. OK. The next manipulation I need to do is to put these Levi-Civita symbols together as a product. Here we're summing over k on one of the indices of the Levi-Civita symbol. So I'm going to want to put k as the first index. So I can write this as epsilon k ij using the cyclical property of the Levi-Civita symbol. And then epsilon k lm of the second one. And then we have an a, j, b, l, c, m. Now we use the identity that if we're summing over one index of a product of Levi-Civita symbols, then we can write that as the product of Kronecker deltas. So the product here would be delta IL, delta JM, minus delta JL, delta IM, times AJ, BL, CM. Okay? I'll continue up here. What do we do next? Well, we're going to, we have a delta IL, and that can contract the BL. And we have a delta JM, and that can contract the CM. So I'm going to try and keep the I and J, and then contract the L and M. So if we do the first one, delta IL times BL is BI. So we'll get AJ, BI. And delta JM, CM is CJ. So we have a CJ. And then minus, now I'm going to contract the L. So we have AJ again. And then we'll have delta JL, BL will be BJ. And delta IM, CM will be CI. Okay? So we used the Einstein summation convention, and we contracted the Kronecker delta times one of these components of the vectors. Okay, so now we don't have any Levi-Civita symbols. We don't have any Kronecker deltas. We want to make sense out of this. So remember, we're looking at the ith component. So I is the only index which is not summed over. So I can rewrite this. This is AJCJ times BI, right? And this one is AJBJ times CI. AJCJ is just A dot C. And then BI is the ith component of the vector B. Minus AJBJ is A dot B. And CI is the ith component of the vector C. Okay, so we're basically done. We've proved that the ith component of A cross B cross C is equal to the ith component of A dot C times B minus A dot B times C. So if that's true for I equals 1, 2, and 3, then what we've proved then is that the vector itself, A cross B cross C, is equal to A dot C times B minus A dot B times C. That's the proof. Okay, so let me summarize. To prove the vector triple product identity, we prove it for the ith component. We replace the cross products using the Levi-Civita symbol. We have to do that twice. Then we manipulate the indices so that we remember that if we contract the first index with the other two indices still free, then we can write that as the difference of the products of two Kronecker deltas. Then we go ahead and apply the Kronecker deltas, the sum of the Kronecker deltas with the components of the vectors. And then we can replace them. So I choose to keep I and J and replace L and M. You don't have to do that, but that's what I chose to do. And then the end result is J is then summed over, but I will never be summed over because we're looking at the ith component. And then rewrite it in terms of vectors, and the identity falls out. I enjoy doing these. I give you a couple to do. I hope you think it's also something that's fun to do. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. In this video, I want to introduce the very, very important concept of scalar and vector fields. Everything we do from this lecture forward will use the concept of fields. And that's basically what we're interested in as engineers and scientists. We're interested in phenomena that vary in space and vary in time. Some of them are scalars, some of them are vectors, and then we represent those phenomena using this concept of fields. So we need a position vector R. So R is the standard position vector. That will locate where you are in space, that you're considering the measure of that thing that you're measuring at that point in space. We need to know where we are in time, so t is the time. And then there are two types of fields. There are scalar fields and vector fields. So for a scalar field, as an example, say the temperature, okay? We would write the temperature at some point in space located by the position vector R. So that means we've already defined a coordinate system, and then we have a vector pointing to a point in space. That vector is R. So we want to know the temperature in that point in space. And at the time t, this is a scalar, But the R is a vector because we're in a three-dimensional space. So this is the temperature at the position x, y, and z, and at time t. So we usually write, in this instance, we usually write the position vector in terms of the coordinates, x, y, and z. So this is the standard notation. That's a scalar field. We can also have a vector field. And as an example would be the velocity of a fluid. So the first example could be the temperature of a fluid. The second example could be the velocity of the fluid. So the fluid is flowing, so it has a certain velocity. The velocity can depend on where you are in the fluid, the spatial variable, and it can also depend on time. So we write the vector field as u, which is now a vector, at the point in space denoted by r at time t. Okay, so again, we've defined a coordinate system. And then this is a vector. So it has a first component of velocity, which is at x, y, z, and at time t in the I direction, plus a second component of velocity at x, y, z, and t in the j direction, plus the third component of velocity at x, y, z, and time t in the k direction. Okay? So you see when you expand this thing, it's quite long, but the notation is quite compact. Okay? How do you find like velocity field? How do you find the temperature field? Usually you find it through a governing equation. Those are called partial differential equations. And these are what we say PDEs, right? PDEs, the plural of PDE. For instance, for a velocity field, it could be what's called the Navier-Stokes equations. Okay, a system of equations that I got my PhD by solving numerically. For the electric and the magnetic field, it could be Maxwell's equations. Okay, these are both for vector fields. The Navier-Stokes equation is for the velocity of a fluid. The Maxwell's equations is for the magnetic field, which is a vector, and the electric field, which is a vector. Or it could be something called the Schrödinger equation. This is an equation for what's called non-relativistic quantum mechanics. The chemical engineers need to learn about this. And it's for a scalar field that's called the wave function. Okay. Let me give you now an example of a vector field. Let me write it down here on the bottom. Let's write down a vector field, B, which is a function of only two coordinates, x and y. So we're in the xy plane. So the position vector is two-dimensional. And I will write that as minus y times I plus x times j divided by x squared plus y squared. Okay? So this is a vector field. It's only a two-dimensional vector field, but it is a vector field. And it actually has a physical significance. This is proportional to the magnetic field circling an infinite a wire containing a current, an infinite length wire containing a current. And the wire is pointing in the z direction. So this is a vector field. So it's interesting to see how do you visualize this vector field. So you can visualize it by at every point in the two-dimensional xy plane, you can draw an arrow in the direction of B, and the length of the arrow can give you an idea of the magnitude of B. Let's look at the graph. So in this graph, the current carrying wire is coming out of the graph, and this is the circulating magnetic field around the wire. The visualization uses arrows, and the arrows point in the direction of the magnetic field, and their length is proportional to the strength of the magnetic field. Okay, so in this video, I introduced the concept of fields. These are extremely important when you're modeling physical phenomena. You need to know how things vary in space and time. The scalar field is just a scalar that depends on space and time. A vector field is then a vector that depends on space and time. Everything, or almost everything moving forward, then we'll discuss how do we do vector calculus with fields. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So this is a video that you need to watch if you know nothing about matrices. If you've taken my Matrix Algebra for Engineers course, or you have some basic knowledge of matrices and linear algebra, then you can skip this video. So what is a matrix? So let's talk about, let me write down to a matrix. So a matrix can be, can have m rows and n columns, but let me sample you with a 2 by 2 matrix. So a 2 by 2 matrix we can write as elements, so 2 rows and 2 columns. In the first row, I'm going to put A11, that the subscript is going to mean row 1, column 1. A12, row 1, column 2. And then A21, row 2, column 1, and A22, row 2, column 2. And at the same time, we'll need a B matrix. B11, B12, B21, and B22. Okay, then we need to know how to do arithmetic on these matrices. So if K then is a scalar, which means basically a number, if we multiply a matrix by a scalar, then we just multiply all of the elements of the matrix by the scalar. Okay? So that's scalar multiplication of a matrix. On the other hand, we can add two matrices. So if we add matrix A plus B, we add matrices. They have to be the same size. So here they're 2 by 2. We just add them element by element. So we get A11 plus B11 in row 1, column 1. We get A12 plus B12 in row 1, column 2. And then A21 plus B21 and A22 plus B22. So matrix addition is simple. Scalar multiplication is simple. It's more complicated. The more complicated operation is matrix multiplication. So let's learn how to multiply two matrices. So if we have A times B, okay, this one will be then A11, A12, A21, A22 times B11, B12, B21, B22. Okay? The way that you multiply matrices is you go across a row of the first matrix and down a column of the second matrix. So the first element here would go across the first row of the first matrix of the matrix on the left and down the first column of the matrix on the right, and you write A11, B11 plus A12, B21. And that gets the 1, 1 element, the row 1, column 1 element. Okay? For matrix multiplication, you have to have the same number of elements as you go across a row and down the column. So the number of elements in the row is equal to the number of columns of that matrix. And the number of elements down a column is equal to the number of rows. It's a little bit tricky. So you need the number of columns of the matrix on the left has to equal the number of rows of the matrix on the right. In this course, it's all going to be square matrices. Okay? So you can always multiply a 2 by 2 matrix by a 2 by 2 matrix, or a 3 by 3 matrix by a 3 by 3 matrix. Okay, so that's the first element. So the second element, which would be row 1, column 2, you get by multiplying row 1 against column 2. So that would be A11, B12 plus A12, B22. Okay? Then you go down the second row. So you get the second row against the first column would be A21, B11 plus A22, B21, right? And then finally A21, B12 plus A22, B22. Okay? So that's matrix multiplication. If this is the first time you've seen this, it may seem a little bit strange, right? But it shows up when you're solving a system of equations. So if we have a system of equations here, so let me write system of linear equations. So for instance, I'll write them in some matrix form. So we have A11 times x1 plus A12 times x2 equals some right-hand side, B1. So here x1 and x2 are the unknowns. Or we can have A21 x1 plus A22 x2 equals B2. So these are two linear equations and two unknowns. X1, x2 are unknowns. The a's are the given coefficients. The b's are the right-hand side. This one, using matrix multiplication, works out into a matrix equation, A11, A12, A21, A22 times the unknown vector x1, x2 equals the right-hand side, B1, B2. Okay? So this matrix multiplication would be a 2 by 2 matrix times a 2 by 1 column matrix or column vector. Okay? Equals a 2 by 1 column vector. So we can convert systems of linear equations into matrices. Another way of writing that is a matrix A times the unknown x is equal to the right-hand side B. AX equals B. Okay, so this is a quick summary of these objects that are called matrices. They have rows and they have columns. You can multiply a matrix by a scalar by multiplying every element of that matrix by that scalar. You can add two matrices of the same size by adding them element by element. And you can multiply two matrices provided that the number of columns on the first matrix is equal to the number of rows on the second matrix. Matrix multiplication goes across the rows of the first matrix down the columns of the second matrix. Finally, this form of matrix multiplication means you can write a system of linear equations as a matrix equation, usually represented as AX equals B. I'm Jeff Chasnoff. Thanks for watching this video. Welcome to week 2 of Vector Calculus for Engineers. In this week, we'll learn how to differentiate scalar and vector fields. We'll define the partial derivative and use it to derive the method of least squares. We'll derive the chain rule and use it to derive the triple product rule familiar to chemical engineers. We'll define the gradient of a scalar field and the divergence and curl of a vector field. Using the Kronecker delta and Levi-Civita symbol, we'll derive some vector derivative identities. We'll then use these identities to prove the existence of electromagnetic waves from Maxwell's equations. Please join me in this second week of Vector Calculus for Engineers. So let's talk about how to differentiate functions of several variables. This is called the partial derivative. So if we have a function, for simplicity, we can just consider a function of two variables, x and y. We want to differentiate with respect to x only. So that's called a partial derivative. And we write that as the partial of f with respect to x. That's how you say it. That's equal to the limit as h goes to 0 of f of x plus h y minus f of x y divided by h. So that's the formal definition of the partial derivative. The takeaway from this formula is that you're differentiating f with respect to x. That's the usual definition of a derivative of a function of one variable. But here, y then is held constant. So you don't do anything with y. You treat y like a constant, and you differentiate with respect to x. That's how you take partial derivatives. So we can see a simple example. So let's look at, say, f of xy is equal to 2x cubed y squared plus y cubed. And find the partial derivatives of this function. Okay? So what is the partial derivative of f with respect to x? You differentiate this function with respect to x, holding y fixed. So y is treated like a constant. 2 is a constant. So that is just a power law. So it brings down the 3. So we have 6x squared y squared. And the derivative of y cubed with respect to x is 0, because that's like the derivative of a constant. Okay. Do this again. What is the partial derivative of f with respect to y, the second variable? We differentiate f with respect to y, keeping x fixed. So that means x is like a constant. So the y squared becomes 2y. So we have 4x cubed y. And the y cubed becomes 3y squared. Okay, those are the two first derivatives. Then we can do higher order derivatives for partial derivatives also. Here, let's look at the second derivative of f with respect to x squared. So partial squared f with respect to x squared. So we differentiate with respect to x again, keeping y fixed. So that will be 12xy squared. And the partial squared f with respect to y squared, we differentiate f again, keeping x fixed. That will be, the derivative of y is 1, so it's 4x cubed plus 6y. Okay, and so on. That's the idea of taking partial derivatives. Something different here is that there's something called the mixed partial. So if we want to know what is the second derivative, so the partial squared f with respect to x and y, this is called the mixed partial. So the way it's written here, you would have the derivative of f with respect to y, this expression here, and then take the derivative of that with respect to x. So then we would get 12x squared y. Right? Because the derivative of y with respect to x is 0. On the other hand, we could have reversed the order, so we could take the derivative of f with respect to x and then differentiate that with respect to y, and then we get 12x squared y, the same answer. So this is the same as d squared f dy dx. The mixed partials don't depend on the order that you take the derivative. Okay? That's true for all reasonable functions. You can make that mathematical if you impose a continuity on the functions and all its derivatives. Okay? Engineers usually don't need to worry about that. Okay, what can you use these partial derivatives for? One use is the Taylor series. So we can expand functions in terms of their partial derivatives. As an example then, if we want the Taylor series of f of x, y, the right-hand side we will evaluate always at x equals y equals 0, always at the origin. And we want to write this so that the left-hand side, when x equals y, f of 0, 0 is going to be equal to f of 0, 0. So the first term here is f, and that will be evaluated at the origin. The next term is the linear term in x. So the partial of f with respect to x at x equals and y equals 0 has to be equal to this term here. So this term is x, partial of f with respect to x. So I'm going to introduce a notation here that is very common, which is a subscript notation. So f sub x is going to mean partial of f with respect to x. Because it's a little bit messy to keep writing these derivatives. Mathematicians and physicists introduce this subscript notation. So the next term here would be plus x, the partial derivative of f with respect to x, which I write as f sub x. And then the next term would be y times the partial derivative of f with respect to y. So these are the linear terms. And then we could keep on going to get the quadratic term. The quadratic term is going to be 1/2. And then we'll have x squared times the second derivative of f with respect to x, plus a cross term, 2xy, f sub xy, plus y squared f sub y, y. Okay? And so on. So the way you derive the Taylor series here for a function of several variables is very similar to the way you derive the Taylor series for a function of one variable. The way I like to think about it is that the function and all of its derivatives on the left-hand side at x equals y equals 0 is equal to the function and all its derivatives on the right-hand side at x equals y equals 0. Okay, and then you get this expression. You'll start, if you keep going up to higher order terms, what you will find is these binomial coefficients showing up. Okay. Typically, in an application, you only need the linear term. You only need the first order terms. Okay, that's the Taylor series. So let me review what we did here. So I'm asking then, how do you define the derivative for a multivariable function? The way we define it is by a partial derivative. You can take the derivative with respect to one variable, holding all the other variables fixed. That's called partial of f with respect to x. And here we hold y fixed. So you can take derivatives by treating y as a constant. Take derivatives with respect to x by treating y as a constant. You can take derivatives with respect to y by treating x as a constant. Furthermore, there are mixed partials. And the nice thing about mixed partials is it doesn't matter the order that you take the derivatives. Finally, I wanted to give you the taste of a Taylor series of a multivariable function. Sometimes this comes in useful in approximation theory. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. So we just learned about partial derivatives of a function of several variables. You know that one of the main applications of derivatives in a function of a single variable is to find maximum and minimum of functions. It also works for functions of several variables. And I want to illustrate that by example. And the example I'll give is rather a classic example. It's called the method of least squares. If you took my matrix algebra for engineers course, you would have seen this example already using matrices and vector spaces. Here I'll show you how to solve this problem using partial derivatives. So the problem is that you have a bunch of data shown as these dots. So the data we can write as xi, yi. And the xi are supposed to be given, and the yi are supposed to be noisy. And here I equals 1 to n. So we have n data points. Okay? So the key here is that the x's are supposed to be known for the data, right? That's the independent variable. And the y's are the measurements. Those are the dependent variables. And from an experiment, they typically come out with some noise in them. But maybe that the theory is such that this data should fit a straight line, and then you want to draw the best straight line that goes through the data points, typically because you're interested in the slope of the line. So you want to try and compute the slope of the line. So we want to then try to fit a line to the data. So the data is here. The fit then is this line, which I'll call y equals beta naught plus beta 1 times x. Okay? So my claim then is this: the y data are related to the x data. The dependent variable is related to the independent variable by a linear relationship. That's the line. Okay, so how do we find the optimum values of beta naught and beta 1? These are the unknowns here, these two fitting parameters. So we construct a function. So the function I'm going to call f is a function of beta naught and beta 1, the parameters that we want to determine. This is equal to a sum over all the data, so we sum over I, of the function beta naught plus beta 1 xi, right? So the function evaluated at I, that's supposed to be yi. So that's the xi minus yi. So beta naught plus beta 1 xi is the fit y at the value of xi. So that's the line. And the yi then are the purple dots. And the difference between these two, right? So the difference is this length here is the difference between those two. We want the square of all of those lengths to be minimized. Okay, so we want to minimize the square of the sum of all of these lengths, the distance between the data and the line. That's why it's called the method of least squares. Okay. So this is our function, a function of our two parameters, beta naught and beta 1. And we want to minimize the value of f. So just like in a single variable calculus, we can set the partial derivatives of f with respect to each of these two variables equal to 0 to find the minimum. Okay, we know there is a minimum because there's no maximum, because we can make this line as far away from these data points as we can. So we know that there's a minimum, and we can find the minimum by solving the partial of f with respect to beta naught equals 0, and the partial of f with respect to beta 1 equals 0. In just the same way we do in single variable calculus. Okay, so let's take the derivative. So the derivative of this with respect to beta naught gives us, we bring down the 2 and set it equal to 0. So we end up with the sum over I 2 beta naught plus beta 1 xi minus yi equals 0. Then the partial of f with respect to beta 1, we have to apply the chain rule here. So it's the derivative of the outside times the derivative of the inside. The inside then will bring out an xi. So we have the sum over I. So we have 2 times beta naught plus beta 1 xi minus yi times the derivative of the inside with respect to beta 1, which will be times xi, and that's supposed to be equal to 0. Okay. These are supposed to be two equations for the two unknowns, beta naught and beta 1. Can we write it in a nicer way so we can see the two equations? So first of all, that 2 is not important, right? We can divide by 2. So let me get rid of the 2. And then we want to write a something times beta naught plus a constant times beta naught plus a constant times beta 1 equals a constant. So the first equation, we have a sum over I of beta naught. So that means we have beta naught plus beta naught plus beta naught n times. I goes from 1 to n, right? So we're summing beta naught n times. So that first equation, we have an n times beta naught. And then we have a sum over I of xi times beta 1. So we have a plus sum over I xi times beta 1. And then the right-hand side is going to be the sum over I times yi. So the right-hand side is the sum over I times yi. So that's called the inhomogeneous term. So we have the number of data points n times beta naught plus the sum over all of the x variables times beta 1 is equal to the sum over all the y variables. That's the first equation. The second equation, we have a sum over I beta naught xi. So we have a sum over xi times beta naught from this first term. And then the beta 1 term, we have a sum over I xy times xi, or xi squared. So we have a plus a sum over I xi squared times beta 1. And that's equal to the inhomogeneous term. The inhomogeneous term will be, there's a minus yi xi, or xi yi. We bring that to the right-hand side. So we have a sum over I xi yi. Okay? Two equations and two unknowns. Our unknowns are beta naught and beta 1, the fitting parameters. The coefficients depend on the data. There's n data. We can add all of the x's. We can add all of the x's squared. We can add all of the y's. And we can multiply all of the x's and the y's and then add them. So these are all constants depending on the data. Beta naught, beta 1 are the unknowns. I can solve this equation. I've done it multiple times. But there's not enough light board to show you. The way I would solve this equation is to write this as a matrix equation and then invert the matrix and then multiply. But you can try it at home if you desire. But I can write down the answer. So the answer I have written over here, because I won't remember it, is beta naught equals the sum over xi squared, sum over yi, minus the sum over xi yi times the sum over xi, divided by the denominator, which is n times the sum over xi squared, minus the sum over xi, that whole thing squared. And then beta 1 is another complicated expression, n times the sum over xi yi minus the sum over xi times the sum over yi divided by the same denominator, which is n sum over xi squared minus sum over xi squared. Okay, you don't memorize this type of formula. And in fact, if you have a big data set and you wanted to compute this, you would not compute it this way. You would compute it using matrices in the method that I taught you in matrix algebra for engineers. But the two results are exactly the same. And for a very small dimensional data set, you can do it by hand and try it out. I give that to you as a problem, and it will actually be the same problem that you might have done in the matrix algebra course. So you can see it's the same answer. Okay, let me review. This is an application of using partial derivatives to find the minimum of a function. Here, we're minimizing the sum of the squares by determining the parameters beta naught and beta 1. So we set the partial derivatives of this function with respect to beta naught and with respect to beta 1 equals 0. That gives us a system of two equations and two unknowns, which you can solve by any method that you like. Okay, I hope this gives you a taste of using partial derivatives to minimize functions. There's a lot of additional details that I skip in this course because typically they're not particularly useful. But in a math course, sometimes the math professor likes to talk about it. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So everyone knows the chain rule from single variable calculus. We need to develop a chain rule now using partial derivatives. So let's consider a function f, which is a function of two variables only for simplicity. I will write down what's called the total differential of f. So that will be denoted as df. That's going to be the value of f at x plus dx, y plus dy, minus the value of f at x and y. Okay? So it tells you how f is changing when you change both x and y. Okay. Can we write that in terms of partial derivatives? We can if we group these terms a little bit differently. We can write this, say, as f of x plus dx, y plus dy, minus f of x, y plus dy, plus, I can cancel out this f of x, y plus dy term by writing this as f of x, y plus dy, and then minus our f of x, y. Okay? So it's the same expression. The minus f of x, y plus dy cancels the plus f of x, y plus dy. These look like partial derivatives. Okay? So the definition of the partial derivative is that you hold y fixed, and then you take the limit of f of x plus h minus f of x. So this is the same formula for the partial derivative, except holding y fixed at y plus dy. But we're considering dx and dy to be small quantities. They're called infinitesimals. They're as small as we would like them to be. So evaluated at y plus dy and y plus dy is the same thing as evaluating at y. And then f of x plus dx minus f of x is just the partial derivative of f with respect to x times this infinitesimal dx. Okay, so that's from the first term. And similarly for the second term, this is just the partial derivative of f with respect to y times dy. Okay, so you view dx and dy are our h here, and the limit h goes to 0. You just view these things as very small dx's, very small numbers like an h, and one is taking the limit in the mind. Okay, so this is df. So how does this help us with the chain rule? Well, let's say, for instance, f is a function of x, which is also a function of t, and a function of y, which is also a function of t. So we want to, this is now, f is now can be viewed as a multivariable function of x and y, or it can be viewed as a single variable function of t, right? So f can be viewed as just a function of t. So we can ask, what is the derivative of f with respect to t? Okay, so that's the normal single variable derivative. Well, we know what df is, so this is a delta f in the numerator. We can divide through by a dt in the denominator, a delta t, right? And then if we divide this expression by dt, we get partial of f with respect to x dx dt plus partial of f with respect to y dy dt. And that's the chain rule for partial derivatives. So it's a little bit different, right, than for normal regular derivatives. You have two terms. So usually for a chain rule, you like to think about canceling the numerator and the denominator. You can't do that here, right? You have to first differentiate f with respect to x, and then you take the derivative of x with respect to time. And then you have to add that to differentiating f with respect to y, and then take the derivative of y with respect to time. So you have two terms, a little bit different. Let me show you a particular example. It's called the material derivative. It is what you get in considering the fluid mechanics, the equations governing the velocity of a fluid flow. It shows up then in the governing equation, which is the Navier-Stokes equation. The idea here then is that you have, following a fluid particle, you have its velocity, dx dt, x is the position of the fluid element, the fluid particle, is equal to the velocity, which is both a function of time, varying in time, but it's also a function of position, which depends on time, okay? Because the particle is flowing in the fluid. So when you derive the Navier-Stokes equation, you need to derive the acceleration of this fluid particle. That would be the second derivative of its position with respect to time, d squared x dt squared. In order to differentiate the right-hand side with respect to t, we need to use the chain rule. So it's the partial derivative of u with respect to t. That's the first variable. And then plus the partial derivative of u with respect to x times the derivative of x with respect to t. But dx dt is equal to u, so this is partial u with respect to t plus u times partial of u with respect to x. And that's called the material derivative. Okay, two terms, partial u with respect to t plus u partial u with respect to x. When you generalize this to 3 dimensions, you get the first two terms in the famous Navier-Stokes equation for fluid flow. A very important equation for, say, mechanical engineers or aerospace engineers. Okay, so let me summarize. I'm talking about the chain rule for functions of more than one variable. To get to the chain rule, I considered the differential df, which I show you is equal to partial f with respect to x dx plus partial f with respect to y dy. So that if f is a function of both x and y are a function of time, then we can consider what is the derivative of f with respect to time. This is the single variable derivative. It's equal to partial f with respect to x dx dt plus partial f with respect to y dy dt. This is the chain rule. Then I showed you an application of the chain rule for computing the first two terms in the Navier-Stokes equation. That's called the material derivative. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. So we learned about the chain rule, and when I derived the chain rule, we did some differentials. There's another use of differentials to derive the triple product rule. The triple product rule comes up a lot in chemistry when you discuss thermodynamic quantities. So someone like a chemical engineer would need the triple product rule. But it's also something that I find to be rather cool. So I wanted to spend a lecture or 2 lectures on this, actually. So in this lecture, I'll derive the triple product rule. And in the next short lecture, I'll give you an example using the ideal gas law. OK, so what is the triple product rule? We assume we have 3 variables, and I'll call them x, y, and z, but they're related. OK, so you can write then a function f of x, y, z equal to 0. So that gives you the relationship between the 3 variables x, y, and z. Since they're related, you ought to be able to solve for x, or solve for y, or solve for z. So for instance, you can write x, which is a function of y and z. Or you can write z as a function of x and y. OK? Let's take the differential of these expressions using the partial derivatives, like I did in the lecture on the chain rule. So we have the differential dx is equal to the partial of x with respect to y times dy plus the partial of x with respect to z times dz. Okay? And then we also have the differential of z, dz, is equal to the partial of z with respect to x, dx, plus the partial of z with respect to y, dy. Okay? All's good, I think. Now what I want to do is to eliminate dz from this first equation using the second equation. Okay? Because I don't want dx, dy, dz. I only want to have 2 variables. So if we do that, we end up with dx equals partial of x with respect to y, dy, plus partial of x with respect to z, times dz, which is partial of z with respect to x dx, plus partial of z with respect to y dy. Okay? The next obvious thing to do is to group the dx terms and the dy terms on the same side. So if we put the dx on the left side and the dy on the right, the dx will end up with a 1 here, and then minus dx dz, dz dx, times dx. And then we have the dy on the right, so we have dx dy. We put the dx on the left, the dy on the right. So we have dx dy here, and then plus dx dz, dz dy, plus dx dz, dz dy, and that's multiply dy. Okay. Now the key here is that we have x, y, and z variables with one relationship between them, given by this function of x, y, z equals 0. Because there's only one relationship, it means we can vary 2 of these variables independently. Okay? We can vary any 2 of these variables independently. So that means we can vary x independently, we can vary y independently. So dx and dy are independent variables that can take any values. So in order for this equality to hold, the terms in the parentheses must be 0. Okay, so let's start with the first term in parentheses. So that means dx dz, dz dx is supposed to be equal to 1. Dx dz, dz dx equals 1 in order for the first parentheses to be 0. This means that dz dx is the multiplicative inverse of dx dz, right? So dz dx is 1 divided by dx dz. That makes a lot of sense, right? You change the numerator, you flip the numerator and the denominator, and it's the reciprocal, okay? So that's a relationship that makes sense to us. Dx dz, dz dx equals 1, okay? What about the second relationship? The second relationship says dx dy is equal to minus dx dz dz dy, okay? But let's put everything on the same side. So we have a dx dy. To put the dz dy on the left, we can use this first identity and take the reciprocal. So this one is equivalent to dx dy. We move the dz dy to the left, it becomes dy dz, so dy dz. And then we move the dx dz on the right to the left, so it becomes dz dx. And what we have left is a minus 1. That's called the triple product rule. Okay, this is the triple product rule. Okay, let's look at that carefully. Dx dy, notice the y matches. Dx dy, dy dz, notice the z matches. Dz dx, dx dy, dy dz, dz dx equals minus 1, minus 1. That always amazes me, you know. I mean, if these were normal derivatives, derivatives of a function of single variable, you would be very happy to cross out dy, dy, dz, dz, dx, dx, and get plus 1. But partial derivatives don't work that way. Partial derivatives are not delta x divided by delta y, like a single variable derivative. They behave differently. So this triple product rule, you don't get plus 1, you get minus 1. Okay, let me review. So the triple product rule is when you have two variables that have a single relationship, and you can write that relationship, say, as f of x, y, z equals 0. We didn't actually use that formula. But what it means is that you can solve for x, so x is a function of y and z, or you can solve for z, so z is a function of x and y. When we look at these differentials, dx, dz, we can vary these things, two of the variables at least independently. The third one depends on the other two. But we can look at dx and dz, and we can use dz to eliminate dz in the dx equation. So we end up with an equation that just has dx and dy. Since x and y can be varied independently, these terms in the parentheses must be identically 0. The first one gives us the reciprocity relationship. So I don't think I can spell this, but reciprocity relation, which is that dx dz is equal to 1 over dz dx, which makes a lot of sense, easy to remember. And then using that relation, we can work the second parentheses, and then we get the triple product rule. Dx dy, dy dz, dz dx equals not plus 1, but minus 1. Doesn't make any sense, but it's correct. I'm Jeff Chasnov. Thanks for watching. In the next video, I'll work an example from real chemistry or physics called the ideal gas law. See you in the next video. In the last lecture, I derived the triple product rule. So we didn't really have a chance to fully digest it. So let me show you a simple example where it applies. That's the ideal gas law. Many of you might have seen this in a chemistry course. This is PV equals nRT. So P is the pressure of the gas, V is its volume, T is its temperature. So those are the variables. N is the number of moles, and R is the ideal gas law constant. Okay? So the N and R are constants. So P, V, and T are variables. So if you remember when I derived the triple product rule, I said that there's a function of the variables, P, V, and T, which is equal to 0. That function would simply be PV minus nRT, and that's 0. Okay? So there's a relationship, one relationship between the three variables, PV and T. So we can write P as a function of V and T. We can write V as a function of P and T. Or we can write T as a function of P and V. Okay? So one of these variables can be written as a function of the other two. So we want to see what these functions are. So here, P equals a function of V and T. So P is equal to solving the ideal gas law for P. We would get nRT divided by V. V is a function of P and T. So solving the ideal gas law for V, we would get V equals nRT over P. And then T is a function of P and V, so we would get T is equal to PV over nR. Okay? Okay, so let's compute this triple product. So the triple product would be, recall what the triple product rule is. So triple product rule would be that the derivative of P with respect to V times the derivative of V with respect to T times the partial derivative of T with respect to P should equal to -1. Okay? That's the triple product rule. Remember, the V's and the T's and the P's don't cancel. We get -1. So let's compute these derivatives and see if it works. So the partial derivative of P with respect to V is, this is V to the -1, so minus V to the -2, so minus nRT over V squared. The partial derivative of V with respect to T, it's linear in T, so it's just nR over P. And the partial derivative of T with respect to P, it's also linear in P, so it's just V over nR, right? So remember, when we take the partial of P with respect to V, we hold T fixed. When we take the partial of V with respect to T, we hold p fixed. And when we take the partial of t with respect to p, we hold v fixed. Okay? Sometimes you write that explicitly, but we won't do that here. So let's take the product now to get the triple product. So we have dp dv times dv dt times dt dp equals minus nRT over v squared, nr over p, and v over nr. Okay? Some of these things have to cancel, right? So this squared here cancels this v. This nr cancels this nr. So we end up with minus nRT over p times v. Okay? nRT over pv. But pv is equal to nRT. That's the ideal gas law. pv equals nRT. So this is minus 1. We're stuck with that minus sign. Okay? A demonstration of the triple product rule for the case of the ideal gas law. So let me review. I like teaching the triple product rule because it gives a demonstration of differentials in the proof as well as partial derivatives. And it shows you that these partial derivatives are tricky items. Okay? They're not like usual derivatives of a function of single variables. It's not a delta p divided by delta v where you can cancel the delta v's and the delta p's. They're a different animal. Partial of p with respect to v has a meaning that you keep partial of p with respect to v has the meaning that you keep t fixed. Partial v with respect to t has a meaning that you keep p fixed. And partial t with respect to p has a meaning that you keep v fixed. That's a different animal than a function of a single variable and a normal derivative. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So we're going to talk about the gradient today. The gradient takes the partial derivatives and puts them in vector form. So it shows up in all the fundamental equations of nature. So how do we get to the gradient? Let's start with a function of 3 variables. The gradient is intrinsically a 3-dimensional object. So we have a function of x, y, and z. And if we look at the differential of f, so what is the change in f when we change x and y and z an infinitesimal amount? That's our df. And remember, we wrote this in terms of partial derivatives as partial of f with respect to x times dx plus partial of f with respect to y times dy plus partial of f with respect to z times dz. Now I want to put this in vector notation. We can do that if we make use of the dot product. This is equal to the dot product of 2 vectors. The first vector is df dx along the I direction, the x direction, times the I unit vector, plus df dy times the j unit vector, plus df dz times the k unit vector. This vector dotted into dx times the I unit vector plus dy times the j unit vector plus dz times the k unit vector. Remember, the cross terms are all 0. I dot j is 0, I dot k is 0, j dot k is 0. And the I dot I is 1, j dot j is 1, and k dot k is 1. So when you take the dot product, this is the expression. So now we have the dot product of two vectors. This first vector is what's called the gradient. So we write that as the gradient of f. That's the definition of the gradient. And that's dotted. This second vector, remember our r was xi plus yj plus zk. So this is just what we call dr. So this is the infinitesimal vector dr. Okay, so we have defined the gradient. This then is the definition of the gradient. What is the meaning of the gradient? So this function is maximum when del f is parallel to dr. So you get a change of f by varying r. So if you want to get the maximum change of f, you have to vary your motion in the direction of the gradient. So the gradient gives you the direction. This is a vector. The direction of the gradient gives you the direction of the maximum change of f when you move a little bit dr. Okay? That's because this dot product is maximum when del f is along the direction of dr. Okay. Another way of writing the gradient is to a formal notation. We write this del all by itself as a differential operator. We can write that as I times d dx plus j times d dy plus k times d dz. That's maybe something you never saw before. This is called a differential operator. It's useful sometimes in doing some algebra with these gradient. Okay? I should say that this has a name. This operator goes by the name of del. D-E-L, del. So the gradient of f is sometimes called del f. Del f. Okay, let's look at an example. So let's say that f of xy equals xyz. F of xyz, I should say, equals xyz. Let's compute the gradient of f. So del f is going to be the partial of f with respect to x, which is yz, in the I direction, plus the partial of f with respect to y, which is xz, in the j direction, plus the partial of f with respect to z, which is xy, in the k direction. Okay? A very simple computation of del f, or the gradient of f. Okay, so let me summarize. We're trying to now put partial derivatives in a vector. That's this del operator, also called a nabla symbol. If you use LaTeX, you need to use nabla. But in spoken language, we call it del, after the Greek letter. It puts the partial derivatives in a vector form. This is a differential operator form. But when you act del on a function, then you get partial of f with respect to x times I plus partial of f with respect to y times j plus partial of f with respect to z times k. And then I worked an example. Okay, we'll be seeing a lot more of the del operator in this course. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. In this video, I want to talk about the divergence of a vector field. The divergence is a very important operation. In particular, it's fundamental to Maxwell's equations, which every electrical engineer needs to know. So let's start with a vector field. So we have a vector field U, which is a function of U1 of x, y, and z. We don't have to worry about the time dependence here because we're only taking spatial derivatives. So u1i plus u2 of x, y, and z, j plus u3 of x, y, and z, k. Okay, so that's our vector field. And then I want to define the divergence of u as using this del operator. The divergence of u is what we call del.u. So del.u is the divergence of u. This is using a differential operator with a dot product with a vector field. What does this look like? This is I d dx plus j d dy plus k d dz dotted into u1i plus u2j plus u3k. Okay? So only the I.I contributes, and the J.J contributes, and the K.K contributes. The ddx acts on u1. The ddy acts on u2, and the ddz acts on u3. So this becomes du1 dx plus du2 dy plus du3 dz. That's the divergence. So del.u is a scalar field, right? U is a vector field. Del.u is a scalar field, and it's equal to the first component of u differentiated with respect to x, holding y and z fixed, of course. The second component of u differentiated with respect to y, and the third component of u differentiated with respect to z. Okay, let's look at an example. What is del dot r? So r then is the position vector, right? This is del dot xi plus yj plus zk, right? And then this is equal to, we differentiate the first component with respect to x. So it's partial of x with respect to x, plus the second component with respect to y, partial of y with respect to y, plus the third component with respect to z, partial of z with respect to z. Each of these is 1, so we get 3. So del dot r is equal to 3. Okay, let's work a second example. What is del dot r divided by r cubed? So r cubed means the length of r cubed. And here, because we're dividing by the length of r cubed, we must have r, the length of r cannot be 0. Okay? That's a very important constraint here. So as long as the length of r is not 0, let's find the divergence of the vector r divided by its length cubed. It's actually very easy to do this if we're in the correct coordinate system. We'll learn about spherical coordinates. That's the system you should do this in. But we're only working here in Cartesian coordinates, so it's a little bit more messy. So we need to know what is this vector here in terms of Cartesian coordinates. I should point out the reason I'm doing this example is because this is the electric field from a point charge. So this is something you see if you study electricity and magnetism. Certainly as an electrical engineer, you do that. So let's look at this. So this quantity here, let me change the color. This r divided by r cubed, if we write this in Cartesian coordinates, this is a vector. The first component, x is r is xi plus yj plus zk. So this is xi divided by r cubed. So the length of r is x squared plus y squared plus z squared to the 1/2 power. And then we're cubing it, so that's to the 3/2. Okay? That's the first component. Plus the second component will be yj over the same denominator, x squared plus y squared plus z squared to the 3/2. And the third component then would be zk over x squared plus y squared plus z squared to the 3/2. Okay? Now we have to take the divergence of this. That means we need to take the partial of the first component with respect to x and add it to the partial of the second component with respect to y, and add that to the partial of the third component with respect to z. So there's a certain symmetry here. So if we do one of them, we ought to be able to figure out the other ones. So let's see how to do that. So let's do the first one. So the partial with respect to x of x over x squared plus y squared plus z squared to the 3/2. What do we do here? We use the quotient rule. So it's the derivative of the top times the bottom, right? The bottom, I can write it out, but I know that's just r, the length of r cubed. So the derivative of the top is 1. The derivative of x with respect to x is 1 times the bottom, which is r cubed, minus the top times the derivative of the bottom. The top is x. The derivative of the bottom, using the chain rule, is 3/2 x squared plus y squared plus z squared to the 1/2 times the inside is 2x. So I don't have enough room to write massive expressions, so let me try and do this in my head. If you have a piece of paper, you can do it longer form. So we're doing the top times the derivative of the bottom. So the 3/2 times the 2 gives us a 3, and we have an x. So we have 3x squared. The top times the derivative of the bottom, times, this became x squared plus y squared plus z squared to the 1/2, so times r, over the bottom squared. So the bottom squared is x squared plus y squared plus z squared cubed, which is r to the 6. Okay. Hopefully that is correct. It has the right dimensions. This is a length cubed, and this is a length cubed, and this is a length to the 6. So the whole thing has a dimension of 1 over length cubed, which the derivative of this would have. So I think it's correct. So that's d dx, and then d dy would be exactly where we change x to y by symmetry would be exactly the same thing, except that this x here would be replaced by y. And then d dz of the third component would be the same thing, but this x would be replaced by z. So if I put that together, we get the divergence of r over r cubed would be 3 of these things. So I can leave it like this. So 3 of these things minus 3 of x squared plus y squared plus z squared times r divided by r to the 6. And this one here becomes 3r cubed minus, this is r squared, the length of r squared, times the length of r is the length of r cubed. So minus 3, the length of r cubed, divided by r to the 6. And sorry, what we already got here is 3, the length of r cubed, minus 3 times the length of r cubed. That's a big 0, right? That's a big 0. A well-known result. Takes quite a bit of work, but it's the divergence of this vector field is 0. The divergence of the electric field from a point charge is 0. Del dot E equals 0. It's one of Maxwell's equations. As long as you're not at the location of the point charge, which here will be the origin. So the point charge is sitting at the at r equal to 0. So this is invalid for r equals 0, but if r is not equal to 0, the divergence of this vector field of a point charge equals 0. Okay, so let me review. So the main point of this lecture is to define the divergence. The divergence uses this del operator. So del dot u equals du1 dx plus du2 dy plus du3 dz in Cartesian coordinates. And then I just showed you 2 applications. Del dot r is equal to 3, and del dot r over the length of r cubed is equal to 0 as long as r is not 0. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So in the last video, I talked about the divergence of a vector field. The divergence, we'll see later, typically means that you have a source of something. So things are going out. For a curl, if a vector field has a non-zero curl, it usually means that there's some swirling motion, some vorticity, we say, in the vector field. Okay, but let's go to the mathematical definition. So we have a vector field, U. So again, this is U1 of x, y, and z. We don't need to worry about time dependence in the I direction, plus U2 of x, y, and z in the j direction, plus U3 of x, y, and z in the k direction. So the curl of this vector field is the del operator cross u. Okay, so the divergence of a vector field was del dot u, the scalar product. The curl of the vector field is del cross u, the vector product. So we can compute this using the 3 by 3 determinant. So this is I, j, k. Now we have the del operator, which is the derivatives, d dx, I, d dy, j, and d dz, k. So that d dz. So that goes in the second row. And then in the third row we have u. So we have u1, u2, and u3. So this 3 by 3 determinant. So let's write that out. I'm going to need more room. So we have I. So we eliminate the first row and the first column. So we have du3 dy minus du2 dz, and that's in the I direction. Then we eliminate the first row and the second column. So because it gets a minus sign, we have du1 dz minus du3 dx, and that's in the j direction. And then eliminate the first row and the third column, and we get plus du2 dx minus du1 dy. And that goes in the k direction. Okay? So the cross product, as always, is a little bit complicated. But here we have the cross product of this differential operator, del, with the vector field u, and we get this expression. So let's see if we can work a couple of examples here. So let's prove a certain result. So prove that the curl of a gradient is equal to 0. Okay? So the gradient of a scalar field is a vector field, and the curl of that gradient, I want to compute that. So what is this equal to? We can write down we can, of course, use this formula, but I'd rather do it from scratch. So if we do that from scratch, we have del cross the gradient of f is the determinant I, j, k, d dx, d dy, d dz, and the gradient of f. So the gradient of f, if you remember, is the partial of f with respect to x times I plus the partial of f with respect to y times j plus the partial of f with respect to z times k. So we're looking at this determinant. We can compute that. So the first component, I component, is the second derivative of f, so d squared f with respect to y and z, minus d squared f with respect to z and y. And this is in the I direction. So we see this is a mixed partial with different order, but we have equality of mixed partials. So this is 0. So this first component here is 0, right? Because the derivative with respect to y and z doesn't matter the order that you do it. The next piece then will be the j component. So that will be d squared f dz dx minus d squared f, this one, dx dz. And that's in the j direction. And again, this is mixed partials, and we have the equality of the mixed partials. So this is, again, 0. Then the last component will be in the k direction, will be d squared f dx dy minus d squared f dy dx. And this is in the k direction. And again, because of the equality of the mixed partials, this thing is going to be 0. So we have 0 plus 0 plus 0. So this is the 0 vector, right? That's a 0 vector because del cross del f is a vector. So this is a 0 vector. But I don't write hats over 0. So you have to know whether it's a vector or a scalar. Okay. The second one that is sometimes used. So this was the curl of a gradient is 0. The second one is the divergence of a curl. So prove the divergence of a curl equals 0. Okay? This 0 here is a scalar. So the divergence of a vector field is a scalar. And this is the divergence of the curl of a vector field. So we can use our del cross u here to compute this. So I'll do that directly. So del dot del cross u is equal to the derivative of the first with respect to x. So it's going to be a big salami. So the derivative of the first with respect to x, the derivative of the second with respect to y, and the derivative of the third with respect to z. So I think I can fit this here. We can do that. The derivative of the first with respect to x is d squared u3 dx dy minus d squared u2 dx dz. So that's from the first piece here. Let me put a parenthesis on it, though we don't need it. Plus the derivative of the second with respect to y. So plus d squared u1 dy dz minus d squared u3 dy dx plus the derivative of the third with respect to z. So that would be d squared u2 with respect to z dx minus d squared u1 with respect to z dy. Okay? We have 6 terms here. 3 of them have plus signs. 3 of them have minus signs. Let's look at them. We have a d squared, right? This square here corresponds to the partial, right? A little bit off there. That's a square. Partial squared u3 with respect to x with respect to y. Here we have a minus partial squared u3 with respect to y and with respect to x. So the plus cancels the minus. We have the equality of mixed partials. We have a minus d squared u2 with respect to x and z. And then we have a plus d squared u2 with respect to z and x. They cancel. And finally, we have the partial squared u1 with respect to y and z. And then we have minus partial squared u1 with respect to z and y. So equality of mixed partials, those two cancels too. So we have 6 terms, 3 positive, 3 negatives. They all cancel, and we get a nice 0 here. That's a scalar 0. Okay, so let me review. We have the curl of a vector field is defined as you would expect, how you define a cross product, where now the del is a differential operator, taking the second row. You can expand that, and you get this long expression. And then there are 2 identities that will come in very useful. One is that the curl of a gradient is 0. And the second is that the divergence of a curl is equal to 0. These 2 identities show up all the time when you're manipulating equations. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So in this video, I want to talk about the Laplacian. We've talked about the gradient, the divergence, and the curl already. They all use this del operator, which is a differential operator. The Laplacian is written as del squared, which comes from this differential operator dotted with itself. These unit vectors are orthonormal. So this is just the derivatives d squared dx squared plus d squared dy squared plus d squared dz squared. So the sum of the second partial derivatives. This is called the Laplacian operator. It can act on both a scalar field or a vector field. So for a scalar field, we would have del squared f would be d squared f dx squared plus d squared f dy squared plus d squared f dz squared. Okay? What about if del squared, the Laplacian, acts on a vector field? So for a vector field, we could write del squared u. How you interpret this is that del squared acts on each component of u. So this would be del squared u1 times I plus del squared u2 times j plus del squared u3 times k. Okay? Why is the Laplacian so important? It's because it shows up in a lot of PDEs. So let me show you some PDEs. So the PDEs this is a partial differential equation. I talk about PDEs in my differential equations for engineers course. Let me give you some 3 representative PDEs where you have the Laplacian. The first one is simply del squared scalar field equal to 0. That's just called the Laplace equation after the Laplacian and after the mathematician Laplace. The next one would be the wave equation. The wave equation is the second derivative of some scalar times dt squared, and that's equal to c squared times the Laplacian of the scalar. So that's the wave equation. Okay, it's called the wave equation because the solution is going to be waves. It can govern things like the music that's made from a guitar string, for instance. It also governs electromagnetic waves, and in fact, we'll derive this equation for the electric field and the magnetic field. The third equation, which I want to present, is the diffusion equation, which is a first derivative with respect to time, d phi dt, equals a diffusion constant times del squared phi. So this is the diffusion equation. Okay, so that governs the diffusion of a dye, say, in some fluid, such as water. This is an equation which I actually solve in my course, Differential Equation for Engineers. Okay, so let me give you an example then of the Laplacian acting on a scalar field. A rather simple example. What would be the Laplacian of the scalar field given by x squared plus y squared plus z squared? Okay? Very simple. This is just the second derivative with respect to x. Would be the y is held constant, so that would be 2x would be the first partial with respect to x, and 2 would be the second, plus the second partial derivative with respect to y is also a 2, plus the second partial derivative of z squared with respect to z is also a 2. So this is simply a 6. Okay? So let me review. In this video then, I introduce another differential operator, which is just the del operator dotted with itself. It's called the Laplacian. It's the sum of all the second derivatives in Cartesian coordinates, okay, in Cartesian coordinates. It can act on a scalar. It can act on a vector. And it acts on a vector by acting on the components of the vector separately. You see a term like this in the Navier-Stokes equations, which is the equations governing fluid motion. It shows up in many other PDEs, including the Laplace equation, wave equation, and diffusion equation. It also shows up in the Schrödinger equation for quantum mechanics. Okay, and this is an example of how you compute the Laplacian given some scalar field. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. In this video, I want to introduce to you the more widely used vector derivative identities. They're used when you manipulate equations to put them into a more convenient form. We'll use them to derive the wave equation for electromagnetic radiation, which is light. But here, I just want to show you the equations and read them to you so you know what they are. So the first two we already derived. Del cross del F equals 0, and del dot del cross U equals 0. This is the curl of a gradient of a function equals 0. This is the divergence of the curl of a function equals 0. Let me write the next vector identity. So this second vector identity is del cross U equals del dot U minus del squared U. Or another way of reading it is the curl of U is equal to the gradient of the divergence of U minus the Laplacian of U. Let's write the third vector identity. Okay, so this third vector identity is del dot Fu equals U dot del F plus f del dot u, or the divergence of a scalar field f times a vector field u is equal to the u dot, the gradient of f, plus f times the divergence of u. So this is a scalar field identity. The left-hand side is a scalar field. The right-hand side is a scalar field. Let me write the fourth one. Okay, in this vector identity, we have del cross fu equals del f cross u plus f del cross u. Or another way of reading it is the curl of a scalar field times a vector field is equal to the gradient of the scalar field, the cross product of the gradient of the scalar field with the vector field, plus the product of the scalar field times the curl of the vector field. Now let's do the fifth one. Okay, this one is a bit complicated. It's del u dot v, so it's the gradient of the dot product between two vectors, so that's a vector. This is vector u dot del times v plus v dot del times u plus u cross del cross v plus v cross del cross u. So 4 terms on the right-hand side. Quite complicated. This one you may not have seen before, so I should write this. U dot del. What is u dot del? So u dot del is a dot product between u and this derivative operator, differential operator. It would be u1 d dx plus u2 d dy plus u3 d dz. And that can act then on either a scalar field or a vector field. If this acts on a vector field, then it acts on all the components of that vector field. Very important because it shows up in the Navier-Stokes equations for fluid flow. Okay, so we got 1, 2, 3, 4, 5 identities. Let me write the 6th one. Okay, this vector identity is del dot u cross v, or the divergence of the cross product between two vector fields. That's a scalar. That's equal to v dot del cross u, or the dot product between v and the curl of u, minus u dot del cross v, or the dot product between u and the curl of v. Notice there's a minus sign here because u and v are not symmetric in this expression. U cross v is equal to minus v cross u. Okay, and then one more. Okay, another difficult one. This is a del cross u cross v. So this is the curl of a cross product between two vectors. That's a vector. This has a very 4 terms in the expansion. So u times del dot v, or the vector field u times the divergence of v, minus v times del dot u, plus v, which is a vector here, dot del u minus u dot del v, where we use this u dot del. Okay, so this is 1, 2, 3, 4, 5, 6, 7, plus another one, 8 different vector identities. They all find some use at one point when you study, say, advanced electricity and magnetism. We'll use one of these identities to derive the existence of light from Maxwell's equations. Okay, in the next video then, I can step you through how one derives these types of identities and then give you some problems to do at home where you can practice. If you're really keen, you can derive all of them from the techniques I'll teach you. But typically, You don't memorize these things, though it's nice to know that the curl of a gradient is 0 and the divergence of a curl is 0. But the other ones you would typically look up in a textbook as you need them. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So in the last video, I introduced 8 of these vector derivative identities. You may be wondering, how do you prove identities like that? In this video, I want to show you at least how to prove one of them. I'll give you a couple of them to do as problems. We need some tools before we go into a proof. So let me show you the sort of identities you need to do a proof of these vector identities. One is that you need to know how to write the curl of a vector field. We're going to be using the Levi-Civita tensor and the Kronecker deltas in these proofs. This is a vector. So typically when you're dealing with a vector quantity, you need to look at its components. So the ith component of the curl of U, we can write using the Levi-Civita tensor as epsilon I, j, k. The first vector here is the del operator, and that takes the second index. So that should be d, dx, j, and the second vector is u, and that takes the third index, so that would be u sub k. Okay? So this is how you write the curl using the Levi-Civita tensor. And remember that we have the Einstein summation convention, so we're summing over both j and k. So j equals 1, 2, 3, k equals 1, 2, 3. Okay. How about the dot product, the divergence, I should say, of u? Well, this would be dui dxi. And here we're summing over I. So that would be du1 dx1 plus du2 dx2 plus du3 dx3, which is the divergence. That's a scalar. Okay? What else do we use? Well, if we have the Kronecker delta, delta ij, times a uj, what would that be equal to? Summing over j. So delta ij is 0 unless j is equal to I. So 3 terms here in the sum. All of them are 0 unless j equals I. And then this would then be u sub I. Okay, so when you contract a Kronecker delta with a vector, then you pick out the component corresponding to the index. Okay, these Levi-Civita tensors you have to be able to manipulate. So they have 3 indices, and they're cyclical, right? So epsilon ijk is equal to epsilon jki is equal to epsilon kij. So sometimes you have to commute these indices. And then if you don't keep them cyclical, so epsilon ijk, and you want to know what happens if you just switch I and j, so epsilon j, I, k, then you get a sign change. Okay, you get a sign change. Finally, the identity that you need when you have 2 cross products in the expression, you will get 2 Levi-Civita tensors together, and they most likely will be contracted. That would end up with an epsilon I, j, k times an epsilon I, mn. So then we're summing over the first index of the Levi-Civita tensor. So I equals 1 plus I equals 2 plus I equals 3. This becomes products of the Kronecker delta. This is something you were supposed to prove when you did the week on vectors. This will be delta Jm delta Kn minus delta Jn delta Km. Okay? So if you want, you can remember this. It's just Jm Kn, and then minus where the order is switched, Jn Km. Okay? So that will turn out to be useful in some of the proofs of those vector identities. Okay, so let's prove one of them. So this is the one I want to prove. Okay, so let's prove that del dot u cross v equals v dot del cross u minus u dot del cross v. Okay, so here we go. Let me try to explain every step in the proof. I need to use a bit of the light board here. So let me start down here. So we start with the left-hand side. So del dot u cross v. This expression is a scalar, okay? So we can just write this just as the scalar, as one number, right? If you were proving a vector identity that was a vector, then you would have to look at the ith component and prove it for the ith component. But this is a scalar, so we can continue. So I need to write this dot product. So this is the derivative d dxi times the ith component of u cross v times the ith component of u cross v. So the ith component of u cross v is the Levi-Civita tensor of I, j, k, and then u, j, v, k. Okay? Right, we're summing over I, we're summing over j, and we're summing over k. So this is a scalar. To get to this result, then, we need to use the product rule for the derivative. So this is equal to epsilon ijk times the derivative of the first, which would be duj dxi plus epsilon ijk, derivative of the first times the second. So this is equal to the derivative of the first times the second plus epsilon ijk times the first times the derivative of the second. Okay. Now we're trying to get this as v dot something and u dot something. So v dot something. So I want to pull out the v. So v sub k. And then I'm going to be dotting that into a curl. So I want this k index in epsilon to move to the first slot so that v will be dotted into that curl. So I can use ijk and move those things cyclical. So I can write that as epsilon of k ij. And then we have a duj dxi. Okay. This second piece is going to be u dotted into something. So it's a minus sign, so I have to show you where the minus sign comes from. So first, let me leave the sign out of this. So I'm going to have a uj, and then I'm going to have epsilon, and let me write the index later, and then we'll have a d, v, k, d, x, I. Okay? So the first index of epsilon has to be j, and then what about the second index? So the second index for this to become a curl should be I, corresponding to the derivative, and k, corresponding to the vector. So that would be del cross v, as in this, this first tool here that we're using. Okay, so we got from epsilon ijk to epsilon jik. We get there by switching j and I, so that gives us a minus sign, right? So epsilon jik is equal to minus epsilon ijk. Okay, we're almost done. So this is just the dot product of v, and this epsilon kij duj dxi is just the curl of u, del cross u. And then minus, then this is the dot product of u. And this term here then is just the curl of v. Okay, and that's what we wanted to prove. So let me just go through the steps quickly here. So we start with the left-hand side, del dot u cross v, and we write that in our component notation using the Einstein summation convention. Okay, and then once we have it in this notation, then we can manipulate the vectors by taking derivatives, right? These are just normal partial derivatives. So we use the product rule here. And then we have to pull everything back together again. So the main step here is that we needed to distribute the derivative using the product rule, but we need to figure out how to do that properly. So we do that in this second step here. And then we have to change, make sure that we've got the dot products and the curls correctly. And then we get a minus sign here because of the indices of these Levi-Civita tensors get switched non-cyclically. And then we can pull out our final expression. Okay? I really enjoy doing these proofs. I don't know if students enjoy this as much as I do. But in any case, if you like it, you can try all of them, do all 8 using this type of notation. It's kind of a game. It's kind of a puzzle. If you don't like it, at least become familiar with how it all works. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. In this video, I want to show you how important these vector derivative identities can be. I want to derive the existence of electromagnetic waves. So electromagnetic waves are light waves, radio waves, X-rays. And the first time that we learned that these were waves consisting of electric and magnetic fields is during Maxwell's time, when Maxwell completed the formulation of the equations that are now known as Maxwell's equations. So in free space, meaning that there's no charges, there's no currents, Maxwell's equations can be written in terms of the electric field E and the magnetic field B. So the divergence of the electric field is 0, and the divergence of the magnetic field is 0. Then the curl of the electric field is equal to minus the partial derivative of B with respect to time. And the curl of the magnetic field is equal to the product of these two constants, mu naught and epsilon naught, times the derivative of the electric field with respect to time. So epsilon naught is called the permittivity of free space. It's associated with the electric field. And mu naught is called the permeability of free space. It's associated with the magnetic field. These are the form of the equation in the so-called SI units, which are typically learned by engineers. Okay, so to derive electromagnetic waves, what I need to do is to condense these equations into a single equation for the electric field. So how can we do that? Well, if we consider, so this is the third equation. We look at the third equation, del cross E equals minus dB dt. We want to eliminate B in favor of E. And to do that, we can use this fourth equation that the curl of B is related to E, the derivative of E. So we need to get the curl of B on the right-hand side of this third equation. So to do that, we can take the curl of both sides of this equation. So we would like to write the equation del cross E is equal to minus del cross dB dt. Okay? This is just derivatives, right? This is d dx, d dy, d dz. This is d dt. So we can switch the order of derivatives because the mixed partial derivatives are equal. So we can write that as minus d dt of del cross B. Okay? So all I'm doing then is equating the mixed partial derivatives. So each term has a time derivative and a spatial derivative, and I just changed the order here. If you don't believe me, you can write out the components and see that's all I'm doing. Okay, the del cross B we can now replace with the right-hand side. The left-hand side is one of these vector identities. So it's the curl of E. So what is the vector identity? We can remember what the vector identity is. So the curl of a vector field has two terms. It's equal to, you can look it up, right? So it's the gradient of the divergence of E, and then minus the Laplacian of E. Okay? That's one of our vector identities. Okay, so we're using this vector identity on the left-hand side. We need to, we can make use then of the Maxwell's equations. So the divergence of E equals 0. So this del dot E is just 0, right? Which is very nice then. So we just have one piece. And then if I write this, then we have minus the Laplacian of E on the left-hand side. And that's equal to minus d dt times del cross B. So we can use another, the fourth Maxwell's equations here to eliminate B. So del cross B is mu naught epsilon naught dE dt. Okay. Two minus signs. Mu naught epsilon naught is a constant. The time derivative of the time derivative is a second derivative. So I can clear the minus signs, and then I can put the time derivative on one side. So then we get d squared e dt squared, right? And then divide through by 1 over mu naught epsilon naught. So 1 over mu naught epsilon naught. And then we have the Laplacian del squared E. Okay? This is a wave equation. Okay? This is one of the PDEs that I wrote when we started talking about the Laplacian. This one is the wave equation. We won't do that in this class, but this wave equation emits waves as solutions. And this term here is the square of the speed. So this 1 over mu naught epsilon naught is c squared. So the speed of the wave is 1 over the square root of mu naught epsilon naught. Okay? Usually the speed of light is called c. This is the speed of electromagnetic waves. And then from measurements on in statics, electricity, and in magnetism, you can have these numbers, and you end up with then about 3 times 10 to the 8th meters per second as the speed of light. Okay? An amazing result when it was first discovered by Maxwell. By these equations for electric fields and magnetic fields, he was able to derive a wave equation and then calculate the speed of light. Okay, so let me review. The purpose of this lecture is to demonstrate the usefulness of these vector derivative identities. And in particular, starting from the field equations for electricity and magnetism, called Maxwell's equations, using this del cross E vector identity, we can derive the existence of waves that have the wave speed of light. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. Welcome to week 3 of Vector Calculus for Engineers. In this week, we'll learn about 2- and 3-dimensional integration and curvilinear coordinates. We'll learn how to compute double and triple integrals. We'll define polar coordinates in 2 dimensions, derive the gradient, divergence, curl, and Laplacian operators, use polar coordinates to derive Newton's law for a central force, and derive the change of variables formula for double integrals. We'll then learn about some important 3-dimensional coordinate systems, cylindrical coordinates and spherical coordinates. These are useful for representing physics that have cylindrical or spherical symmetry. Please join me in this 3rd week of Vector Calculus for Engineers. So we've talked a lot about differentiation with partial derivatives. In multivariable calculus, you also need to do integration. So in single variables, you just have an integral over one variable. But here we have to worry about integrating over 2 or 3 variables. So we have 2 types of integrals. We have the double integral. So we will write that as an integral over some area of a function of 2 variables, dx, dy. Or we will integrate over a volume. So we'll write that as a triple integral over a volume of a function of three variables, x, y, and z, dx, dy, dz. Okay, I think to illustrate this, I should do an example. So let me show you what the problem is we're going to solve. So compute the volume of the surface z equals x squared y above the xy plane with base given by the unit square with vertices 0, 0, 1, 0, 0, 1, and 1, 1. So we can draw a picture of the base. So this is the xy plane. So the base is just a square. So it's just this square. And the surface is z equals x squared y. So we want to find essentially what is a volume of the between the surface x squared y and this square in the xy plane. Okay, so a double integral then can be interpreted as a volume, just like a single integral is the area under the curve. The double integral is the volume under this function f of xy. Okay, so how do we set this up? So I'm going to show you two ways of doing this. So in the first way, we're going to do a double integral of the function, which is x squared y. And we can integrate dx, dy. X goes from 0 to 1. Y goes from 0 to 1. So when you write this integral, the meaning is you do the first integral dx first. So the dx, the first infinitesimal element dx, means that the first integral corresponds to integrating x dx. And the second integral corresponds to integrating dy. And in a case like this, you just do them sequentially. So first you integrate over x, keeping y fixed. So if we integrate this over x, we still have 0 to 1. And then we integrate x squared, keeping y fixed, will be x cubed over 3. So x cubed y over 3. And that will be as x goes from 0 to 1. And then we'll have a dy integral left. So this is the value of x now. We integrated x. So the lower limit will be 0. The upper limit will give us a y over 3. So this will be an integral from 0 to 1, y over 3 dy. Then this is y squared over 2. And we plug in the upper limit 1, which will be 1/6. Okay? I hope you can do that in your head. So I'm going to try and save some space here. So y squared over 2 will give us 1/6. So that's the first way. The second way, instead of integrating x first, we could integrate y first. So we could have the integral from 0 to 1, 0 to 1, x squared y. But now we integrate dy dx. Okay? What would this be? So now we integrate y first, keeping x fixed. So it becomes y squared over 2. So the outer integral is 0 to 1. And then we have an x squared y squared divided by 2 between the limits 0 and 1 and dx. So now this limit here corresponds to the limit of y. The lower limit will be 0, so the upper limit will be x squared over 2. So this is the integral from 0 to 1 of x squared over 2 dx. This becomes x cubed over 2 times 3, which is 1/6 in the upper limit and 0 in the lower limit. So again, we get 1/6. Okay? So this first one is integrate x first. The second is integrate y. In this particular problem, we can actually shortcut this. We have integral from 0 to 1, 0 to 1, say x squared y dx dy. Because these limits don't depend on x and don't depend on y, my preferred method for doing this integral would just be to do these two integrals separately. So the x squared dx is the inner one, the y dy is the outer. So you can write this as 0 to 1 y dy times 0 to 1 x squared dx. So when the limits don't depend on x and y, and x squared y is separable into a function of x times a function of y, then you can factor the integral. Okay? So this would be my choice. So the integral of y dy is y squared over 2. So that would give us a 1/2. And the integral of x squared dx is x cubed over 3. So that would give us a 1/3, which is a 1/6 again. Okay. So let me summarize. We want to generalize then single variable integrals to functions of 2 or 3 variables. These are called double integrals and triple integrals. A double integral is going to be over some area. A triple integral is going to be over some volume. Here I give you what is possibly the simplest type of integral to do. How do you integrate some function? Here I call it z equals x squared y above a square in the xy plane. So I set it up as a double integral of the function dx dy. The limits here corresponding to the limits of x and the limits of y. To do this type of integral, all you do is you do one at a time. So you integrate x first, keeping y fixed, and then you integrate y. And the second one, I integrated y first, keeping x fixed, and then I integrated x. And then in the third one, I show you that this type of integral is actually factorable, so it factors into 2 single variable integrals. In all cases, we get the answer of 1/6. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. So let me do another example of a double integral in this lecture. Compute the volume of the surface z equals x squared y, the same surface as last time, above the xy plane with base given by a right triangle with vertices 0, 0, 1, 0, and 0, 1. So the difference here is that the base is a right triangle. But that makes the integral somewhat more complicated. And let me show you how that works out. So we should draw the base. So here's x and y, and 1 and 1. So the rectangle, not the rectangle, the triangle looks like this. We have 2 choices of how to integrate this. We can integrate x first and then y, or we can integrate y first and then x. So let me kind of sketch what we're doing here. So if we integrate x first, then we're going to be integrating along this direction first. So strips along x, and then we integrate along y. So if we integrate along x first, we have to specify the limits of integration. Here we're integrating x from 0 to this line. So we're going to have to know what is the x value on this hypotenuse of the triangle. So this is equal to x is going to be 0 when y equals 1, and x is going to be 1 when y equals 0. So this is 1 minus y. So the double integral here will be integrating over x squared y. We integrate x first, and then y. And the limit of integration for x is that we start from x equals 0, and then we integrate to the hypotenuse, which is 1 minus y. And then finally, we do the y integral, which will be from 0 to 1. Okay? So the more difficult aspect of this formulation of integrating over the triangle is that now the inner limit depends on y. So you can't write this integral as a product of an x integral and a y integral. You have to do the x integral first, plug in the limits, and then do the y integral. We could have integrated along y first, so let me draw the picture for that. So x and y, and again we have our triangle, right? 1 and 1. Now we're going to integrate along y first, so let me draw the first direction of integration. We need to specify the limit that we integrate along y. So we're integrating from y equals 0 to this value of y. This value of y here is equal to 1 minus x. Okay, sometimes it won't be so symmetrical, but you need to specify the limits of the y integration. So here we're integrating x squared y, first dy, and then dx. And the y limit is from 0 to 1 minus x. And the x limit then goes from 0 to 1. Okay? Both of these integrals will give the same solution. Okay, so let's choose one of them and do it. I think I want to integrate the second one because then it's a y dy, so it becomes a y squared. If we integrate the first one, we have an x squared dx. We have to deal with an x cubed. So a little bit easier to do the second one. So let's go ahead and do that. So we have the double integral from 0 to 1, 0 to 1 minus x, x squared y dy dx. Integral from 0 to 1. So we integrate dy. That becomes y squared over 2. So I can factor out a 1/2. And then we have x squared y squared, right? Y squared over 2. That goes from 0 to 1 minus x dx. So the value of y goes from 0 to 1 minus x. We can substitute that in. So 1/2, the integral from 0 to 1 of x squared times 1 minus x squared, right? Minus 0. The lower limit here is 0. And that will be dx. Okay. We just have a single variable integral left. I think the easiest way to do that is just to expand this out into a polynomial. So 1/2 the integral from 0 to 1. So this is, the first term here is 1. So x squared minus 2x minus 2x cubed plus x squared plus x to the 4th dx. Okay, we can integrate the polynomial, and then we can put in the limits right away. The lower limit will be 0. The upper limit is just 1, so it's just the constants here. So we can do that without writing too much. So the integral of x squared is x cubed over 3. So that will give us a 1/3. Minus the integral of x cubed is x4 over 4. So that will give us a -2 over 4, which is -1/2. And then the integral of x fourth is x to the 5th over 5. So that will give us plus a 1/5. Okay? We can put this under a common denominator. So that would be 5 times 2 times 3, which is 10 times 3, which is 30 times 2 would be 60. So 1 over 60. And then this 1 then would be 2 times 5 would be 10. And then minus, this 1 is 3 times 5, so minus 15. And then this 1 is 3 times 2, so plus 6. So this is minus 5 plus 6 is 1. So this will just be 1 over 60. Okay? So let me review the main point here. We have a base now to integrate over, where we have to take into account that the limits are not pure numbers, right? When we integrated over a square, we were just integrating from 0 to 1 and 0 to 1. Now we need to integrate to this hypotenuse. We can do the integral in 2 different ways. The x integral first, and then the inner limit will depend on y. Or we can do the y integral first, and then the inner limit depends on x. Otherwise, you just follow the same procedure of integrating the inner limit first, holding the variable of the outer limit fixed, and then finally integrating the outer limit. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. So we're working on polar coordinates. In the first video, I derived the gradient operator, the del operator. And then in the last video, I looked to see how you can take the divergence and the curl of a vector field. In this video, then, I want to look at the Laplacian operator. Okay? So the Laplacian operator is what we write as del squared, which is essentially the dot product of the gradient with itself. So we're going to do this without a function that it's operating on. We're just going to work the differential operator by itself. This would be r hat d dr plus theta hat 1 over r d d theta. And that's dotted against itself. So r hat d dr plus theta hat 1 over r d d theta. And that will give us this del squared operator. OK, so again, we have 4 terms. Let's start with the r hat term. So the r derivative doesn't affect r hat and theta hat. They only depend on theta. So the first term here will be r hat dot r hat is 1. So that will simply be the second derivative with respect to r. Okay. The next term is going to be r hat dotted theta hat, which is 0. So the second term here will be a 0. And then we go to the dd theta term, the theta hat term. Now we have to worry about that the unit vectors depend on theta. The first term here, we have a theta hat dot r hat would be 0. But now r hat depends on theta. And in fact, dr hat d theta is equal to theta hat. So when this derivative acts on r hat, we get theta hat. And what we have left over then is a 1 over r ddr. OK? Because then we have a theta hat dot theta hat, which is 1. Finally, on this last term here, again, theta hat depends on theta. But d theta gives us a minus r hat, which is perpendicular to theta hat. So that term is 0. So this derivative then just works on the derivative term. Theta hat dot theta hat is 1. So we end up with plus 1 over r squared, 1 over r times 1 over r, times the second derivative with respect to theta. OK? So 3 terms. This term, d squared dr squared plus 1 over r ddr, that reduces to one term if we write it as 1 over r ddr r ddr, right? The derivative of the first times the second gives us 1 over r, 1 over r ddr, plus the first times the derivative of the second. The r cancels the r, and we get the second derivative here. And then the last term here is 1 over r squared d theta squared. That's the differential operator that's called the Laplacian. OK, how does the Laplacian actually work? So if we were going to take the Laplacian of something, we could take the Laplacian of a scalar field, right? Laplacian of a scalar field. That's fine. We can just apply this directly. Or we can take the Laplacian of a vector field. The Laplacian of the vector field is equal to the Laplacian of this u r hat plus u theta hat. And then we have to take the Laplacian of this first term and the Laplacian of this second term. The difficulty here is that these unit vectors then depend on theta. So when you differentiate with respect to theta, you have to take that into account. So this can turn out to be a very complicated expression. So let me summarize. In this series of 3 lectures then, I've been working with polar coordinates. We define what polar coordinates is. Many of you do that in a high school course. But what we've done now in these lectures is talk about the gradient operator. And then we did the divergence and the curl. And finally, we talked about the Laplacian operator. The Laplacian is very important. It shows up in fluid mechanics. It shows up in electricity and magnetism. And it shows up in quantum mechanics. I'm Jeff Chasnov. Thanks for watching. And I'll see you in the next video. So when you have a double integral, maybe in Cartesian coordinates, it's very complicated to do. But in polar coordinates, it will be much simpler to do. So to do that, we need to change variables in the integral from a double integral in Cartesian coordinates to a double integral in polar coordinates. So that's called a change of variables formula. In order for you to have a better understanding of how it works when we have double and triple integrals, I thought I would have an extra video and show you how it works for single integrals, something you know in single variable calculus, and it's called substitution. Okay, so let's work the change of variables formula for single integrals. So let's say in general we're doing an integral from some initial value of x naught, to some final value of xf of some function f of x dx. And maybe f of x is difficult to do in this variable x, and we want to change variables. So that's what we call substitution in single variable calculus. So we let, say, x equals some function of s as a new variable, and then dx is equal to u prime of s ds. So that's the typical substitution formula. So then we get I is equal to the integral. So instead of f as a function of x, we have f as a function of u of s. So f becomes a function of s, and dx becomes u prime of s ds. And in the case where u, say, is an invertible function, then we need to change the limits of integration. So x naught, the initial value of s, then would be the inverse function u inverse of x naught, and the final value of s would be u inverse of x f. Okay? This is the standard substitution. So there are three pieces here. The first piece is the integrand. So instead of having the integrand as a function of x, we now made the integrand a function of s. And that's usually the reason to do this in single variable calculus, because f of x is too complicated to integrate, so we do a substitution. The second piece is this u prime of s ds. That's a transformation of the dx. So in the double integral, we're going to have to transform dx dy. Okay, it's a little bit more complicated than just transforming dx. And then finally, the third piece is changing the limits of integration. In the double integral, we're integrating over some area. We're going to have to figure out how to change the limit of that. So this is how it works for single variable calculus. I think to be more explicit, I can look at a particular example. So let's calculate, say, the area of a circle using one integral. Let me draw the graph. So instead of finding the area of a whole circle, we can find the area of a quarter of a circle and multiply by 4. So let's say this is the quarter of a circle. So the radius can be capital R. Okay, this is our x. This is our y-axis. This function. This is a function of x. So we can x squared plus y squared equals r squared. So y here is equal to the square root of r squared minus x squared. Okay. If we want to integrate to find the area here, we can do a Riemann sum that looks something like this. Okay, so how do we write the integral? So if we want to find the area of the circle, so let me write that A of the circle, it's 4 times the area of this quarter circle, so it's 4 times, and then it's the integral of the y of x dx. So it's the integral of the square root of r squared minus x squared dx. And then x goes from 0 here, right, up to capital R, the radius. Okay, so it's this integral to do. Typically, then you would do this integral through a substitution. Here, I can just let x equals r cosine theta. Okay, it's kind of like a polar coordinate for x. And then dx will be minus r sine theta d theta. So that will be our substitution. So then we will get the area of the circle is equal to 4 times the integral. So r squared minus x squared is r squared minus r squared cosine squared theta, r squared minus x squared, square root. Dx is minus r sine theta d theta, right? And then the limit, so when x equals 0, then what is the value of theta? Then theta, when x equals 0, theta will be pi over 2. So the lower limit is pi over 2. When x is equal to capital R, cosine theta will be 1, so theta will be 0. So the limits here kind of get flipped. But the minus sign will flip it back. So if we write this out, we can factor out an R here. We can factor out an R. The minus sign can flip the limits. So we have R times an R. So we have 4R squared. And then we have the integral from 0 to pi over 2. And we have the square root of 1 minus cosine squared theta times sine theta d theta. Okay, it's just an exercise in single variable calculus. This is sine theta, so this is 4r squared times the integral from 0 to pi over 2 of sine squared theta d theta. And this integral has to be 1/4 times pi, because we know the area of the circle is pi r squared. Okay? You can look up this integral, or you can do it using the double angle formula. Okay, so this was what you already know from single variable calculus. You know it's called substitution. Here I'm going to claim that I'm going to call this a change of variables formula. The important thing here that we're going to have to carry over for the double integral and then the triple integral is that this dx gets transformed to u prime s ds, right? So s then becomes the new variable. So we need to consider now, in the double integral case, how to transform dx dy. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. So in this video, let me give you an example of the use of polar coordinates. That's for calculating Newton's laws of motion when you have a central force. Newton's law is F equals ma. A central force means that you have you define your coordinate system so that the force is basically pointing from the object to the origin of the coordinate system. So I can draw a graph of that. So we have our x and y axis. We have some mass right here. And then there's a force then. There's the position vector of the mass here. This is r. And then the force then is along r from the mass to the origin. So a physics problem would be a planet revolving around the sun, but for any calculation where you have some force that's always pointing in towards some point, then that would qualify as a central force. The main derivation here will be the conservation of angular momentum in this problem, but you'll see how one can manipulate variables when you use polar coordinates. So here we need to write r. So what is r? Remember that we have our unit vector, r hat. So the position vector is the length of r, the length of this vector, times r hat, the unit vector. Okay? What we're going to want to do then is to do Newton's equation, which will be this equation, Newton's equation will be m times the second derivative of the position vector with respect to time, which I'll write that using this dot notation. So that means the second derivative of r with respect to time. This will be mass times acceleration, and that will be equal to the force. Okay, Newton's equation, F equals ma. Okay, so what we need to do here is to take the time derivatives of r. To do that, we need to know how to take the time derivatives of unit vectors. So let me do that first. If we wanted to know what the time derivative of the unit vector in the r direction is, remember that the unit vectors are functions of theta, right? So this angle here is theta. Then we have to use the chain rule. So the chain rule would say we have to differentiate r hat with respect to theta, and then we differentiate theta with respect to time. These are all ordinary derivatives. And remember from the last video, I said dr hat d theta was equal to theta hat. So this one then is d theta dt, which I'll write as theta dot, and then dr hat d theta is theta hat. Okay. The other derivative of the unit vector that we'll need is d theta hat dt. So again, that's d theta hat d theta times d theta dt. And d theta dt is theta dot. D theta hat d theta is minus negative sign times r hat. Okay? We'll make use of these derivatives of the unit vector. Okay. This is our position vector. Now I want to start differentiating it. So let's differentiate r with respect to time. So we have r dot, right? So we have to differentiate the right-hand side with respect to time. We need to use the product rule. So it's the derivative of the first times the second. So it's the length of r times r hat plus the first times the derivative of the second. The derivative of the second, dr hat dt, is theta dot theta hat. So we have r plus r times theta dot times theta hat. Okay? That gives us the velocity, right? So the velocity of this mass here in polar coordinates is going to be r dot r hat plus r times theta dot theta hat. Okay, so you see that we're starting to get something a bit more complicated than what we would get in Cartesian coordinates. And the complication is coming from the fact that these unit vectors are functions of theta. Okay, let's continue. So now we want the second derivative. So we have r double dot, so the d squared, the second derivative of r with respect to time. Again, we need the product rule. So we have the first term gives us a derivative of the first times the second, plus the first times the derivative of the second. So the first times the derivative of the second, dr hat dt is theta dot theta hat. So it's r dot theta hat. So we get two terms from this r dot r hat. Then we differentiate the second piece. So now we have three terms to differentiate. So we have the first one is r dot theta hat. R dot theta hat. The next one is r times theta double dot times theta hat. And the last piece is r theta dot times d theta hat dt. So d theta hat dt is minus theta dot r hat. So we have minus r, and then we have a theta dot squared r hat. Okay? 1, 2, 3, 4, 5 terms here. We can group them. So we have the r hat term. So we have r double dot minus r theta dot squared times r hat. And then we have the theta hat term. So we have plus, this is r dot theta dot plus r dot theta dot. So we have two of them plus r theta double dot. So we can write that as r theta double dot plus 2 r dot theta dot times theta hat. Okay? So this is the second derivative, Okay? Now let's concentrate on a central force. So if we have a central force, that means the force is in the r hat direction. The force is pointing towards the origin. So let's write F then. Let's make it actually an attractive force. So let's call that minus F, which could depend on r and theta, right? It could depend on r and theta. But let's assume that it only depends on the distance to the origin. Okay, so I want to specialize on a central force that depends just on the distance to the origin. And it's in the negative r hat direction. Okay, so let's look at a central force that looks like this. So now we're writing Newton's equation. So mr double dot is equal to this central force, right? So we have, I can write it out. So mr double dot would be m times r double dot minus r theta dot squared, right? R hat plus m times r theta double dot plus 2r dot theta hat equals the force minus f of r hat. Okay? You have a vector equation. So the r hat component on the left is going to be equal to the r hat component on the right. The theta hat component on the left is going to be equal to the theta hat component on the right, which is 0. So this is two equations. This is m r double dot minus r theta dot squared equals minus f of r. Okay? And this is the equation m r theta double dot plus 2r dot theta dot equal to 0. Okay? separates into two equations. This second equation is actually conservation of angular momentum. We can multiply this equation by r. Okay, so we'll just multiply this whole equation by r. And then we see that this is r squared theta double dot plus 2r plus 2r r dot theta dot. You can view that as a derivative. So what that equation says, so from this equation, we have d dt of m r squared theta dot equals 0. Okay, you can verify that. The derivative of the r squared terms gives you 2r r dot theta dot, which is the second term multiplied by r. And the derivative of the theta dot term gives you m r squared theta double dot, which is this first term multiplied by r. So this is a conservation law. This expresses conservation of angular momentum. Conservation of angular momentum. Okay? And this is the angular momentum. So if this one is what we usually call L, then this equation says the time derivative of L is 0. So we get L is a constant, right? Doesn't change in time. A conservation law. Okay, so let me summarize. The purpose of this lecture is to show you a very important use of polar coordinates. And that's to consider Newton's equation when you have a central force. Many sort of engineering problems when you're pulling an object into some point and causing it to rotate. This is a central force. The physics problem is the planetary motion problem, among other problems. So the main difficulty here is that when we take these time derivatives, these unit vectors depend on theta. So that's why the equation becomes much more complicated. But the beauty is that in the end, you say that you have a conservation law, which you cannot see if you use Cartesian coordinates, and it leads to a very important law, which is called conservation of angular momentum. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So in the last video, I stepped you through the change of variables formula for single integrals. You know that as substitution. Now we want to see how to do that for double integrals, and then it will generalize also to triple integrals. So we're looking at an integral over some area of some function of two variables, and then it's dx dy. Okay? So the main part of the difficulty, we can change variables. Let me do that first. We can let x, and here I'm just going to keep the same name for the variable because it's easier to remember the change of variables formula. So we let x equals now a function of two variables, s and t, and we let y equals another function of two variables, s and t. So that will be the form of the change of variables. And the key point here is we know that we can convert f then to some function of s and t just by substituting x and y. We can try and figure out how to change the limits of the integration. Here it's some dx dy space. Here it will be in, this is some xy space. Here it will be in some st space. Changing the limits might be difficult, but not in the problems that we do in this course. The main difficulty here will be this bit. How do we change this infinitesimal area, this dx dy, to some infinitesimal area in the st space? Okay. It's a bit challenging to prove what that change of variables formula is. And I won't do that in this course. You can go online and look it up. I think it's more important to remember what it is, because it shows up all the time when we're changing from, say, Cartesian coordinates to polar coordinates in 2 dimensions, or we'll also do 3-dimensional transformations to what are called cylindrical and spherical coordinates. So what is the change of variables formula for the dx dy? It's dx dy equals the absolute value of the determinant of a matrix that's called the Jacobian matrix times then ds dt. Okay? That's the change of variables formula for this integration area dx dy. So what is the Jacobian matrix? What is this matrix? Here, for a double integral, it's a 2-by-2 matrix. For a triple integral, it would be a 3-by-3 matrix. So the Jacobian is sometimes written as, in this notation, partial of x comma y over partial of s comma t. The matrix is a 2-by-2 matrix consisting of partial derivatives. So it's dx ds dx dt, and then dy ds dy dt. Okay? Because it enters as a determinant, we could also take the transpose of this matrix. It doesn't make any difference. The determinant will have the same value. But this is the standard form for writing the Jacobian. Okay. This is still a little bit abstract, so let's look at an example. Let's compute again the area of a circle. So we can do a full circle now. Okay, so we're looking for the area of a full circle. This is of radius r. Okay. The area of the circle is going to be, we can write it as a double integral simply of dx dy. Okay, so we just break up the circle into little pieces. In Cartesian coordinates, this is challenging to do, but it's a relatively easy thing to do in polar coordinates. So let's change variables here to polar coordinates and see how that works. So we're going to let x equals r cosine theta and y equals r sine theta. Okay? Now we need the Jacobian matrix. So the Jacobian matrix is this 2-by-2 matrix, which is the partial of x with respect to r, right? So we're changing variables from xy to r and theta. So the Jacobian matrix is partial of x with respect to r, which is cosine theta, partial of x with respect to theta, which is minus r sine theta, partial of y with respect to r, which is sine theta, and partial of y with respect to theta is r cosine theta. So that's the Jacobian matrix. So now our change of variables formula will be dx dy, right, is equal to the absolute value of the determinant of the Jacobian times dr d theta, right? And the determinant of this matrix will be r cosine theta times r cosine theta, so r cosine squared theta minus r sine theta times sine theta. So r cosine squared theta plus r sine squared theta, which is r. And r is the length of the vector, so it's positive. So this becomes r dr d theta. Okay? So that's the change of variables formula for dx dy. You have this extra factor of r from the determinant of the Jacobian. Okay, so we're ready to integrate. So we have the area of the circle is equal to this double integral of dx dy. So this is r dr d theta. R is the radial variable in polar coordinates. It will go from 0 to capital R. Theta is the angular variable in polar coordinates. That will go from 0 to 2 pi once around the circle. Okay? This integral factors. So this becomes 0 to 2 pi d theta, 0 to r dr. The first one gives us 2 pi. The second one gives us capital R squared divided by 2. So we get the result that we expect, that the area of the circle is pi r squared, capital R squared. Okay? So let me review. The difficulty of the change of variables formula in a multi-dimensional integral. Here it's a double integral, but this, what I did here, works equally well for a triple integral, is that when you change variables, so here from xy to s and t, here from xy to r and theta, when you change variables, you have to change dx dy equal to ds dt, and then you have a factor which tells you how to transform the length. So this is essentially related to the area of a rectangle, and then the right-hand side is the area of a parallelogram. And the area of the parallelogram gives you this determinant. Determinant is known to represent the area of a transformation of the parallelogram, essentially. So determinant of this Jacobian, the Jacobian is this matrix of partial derivatives. Okay? So given a transformation, a real transformation here, x equals r cosine theta, y equals r sine theta. By taking partial derivatives, we can compute the Jacobian. And then by taking the determinant of that Jacobian, we can get the correct transformation for dx dy. Okay. In this course, we'll do this for polar coordinates. And then in 3 dimensions, this will be a 3 by 3 matrix. We'll do this for cylindrical and for spherical coordinates. And that's kind of standard. And then we will just write down what the formula is for dx dy dz then in cylindrical and in spherical coordinates. And probably I give that to you as a problem when we talk about that subject. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So we've already discussed polar coordinates. This is the 2-dimensional circular type of geometry. A circle is a cross-section of a cylinder. So if you wanted to extend polar coordinates to the 3rd dimension, it would be called cylindrical coordinates. So here I've shown you a graphical representation of cylindrical coordinates. This is the position vector It's not that straight, but it's the position vector pointing to this point here. Then we can identify this, the x, y, z coordinate of that point using 3 different variables. Here it would be rho, which is the length. If you project that point onto the xy plane, it's the length from the origin to the projection on the xy plane. And then the angle that projection makes with the x-axis is phi. In polar coordinates, we call that this r and theta because that's kind of the standard in 2 dimensions. When we go to 3 dimensions now, we're calling this rho and phi. And then the third coordinate is z, the vertical height above the xy plane. Okay? And that specifies this coordinate. So this is just polar coordinates. Instead of r theta, we use rho phi. Polar coordinates expanded into the third direction. The position vector then is written as rho times rho hat. So rho hat is the unit vector in the direction of rho plus z times z hat. Z hat was our k in Cartesian coordinates. And the third unit vector then is phi hat, which is in the direction of increasing phi. So the change of variables formula from Cartesian coordinates to cylindrical coordinates is x equals rho cosine phi, y equals rho sine phi, and z still is the Cartesian coordinate z. You can compute the Jacobian here to get the change of the dx dy volume element, a change of variables formula. And if you do that as part of your problems, you get dx dy dz. Well, it's actually, we did it already for polar coordinates. It would just be rho, d phi, dz, because the z coordinate doesn't add anything to this. Okay. We need the differential operators in cylindrical coordinates. It's a lot of work. It requires doing a chain rule multiple times. So let me just write down the formulas and explain to you what they are. Okay, so the del operator in cylindrical coordinates is 3 terms, rho hat dd rho plus phi hat 1 over rho dd phi plus z hat ddz. So there's this extra factor of 1 over rho. Remember that both rho hat and phi hat are functions of phi. So when you differentiate, you always have to make sure you differentiate the unit vectors. Okay, let's look at the Laplacian now. Okay, so this is the Laplacian operator, a bit more complicated. 1 over rho dd rho of rho dd rho. So this has both a first derivative in it and a second derivative in it, plus 1 over rho squared d phi squared, and then plus d squared dz squared, because the z unit vector is fixed, doesn't depend on phi. So if you wanted to solve a PDE that has some sort of cylindrical geometry associated with it, such as the electromagnetic field inside a cylinder cavity, then you would need this form of the Laplacian. Okay, now let's look at what do you do if you have a vector. So our vector A, say, has components in the rho direction, the phi direction, and the z direction. So I'll write that as A rho times rho hat plus A phi times phi hat plus a z times z hat. So a rho is a function of rho, phi, and z. A phi is a function of rho, phi, and z. And az is a function of rho, phi, and z. So now I want to talk about what is the divergence of A in cylindrical coordinates and what is the curl of A in cylindrical coordinates. So let's have a look at that. Okay, so this is the divergence of A, and this is the curl of A. You see how the expressions are quickly becoming complicated. So the divergence of A is 1 over rho dd rho, rho times the component of A along the rho hat direction, A rho, plus 1 over rho dA phi d phi, plus dAz dz. Okay. The curl is more complicated. So the del cross A, the component in the rho hat direction, is 1 over rho dAz d phi minus dA phi dz, plus the component in the phi hat direction is dA rho dz minus dAz d rho, plus the component in the z hat direction is 1 over rho dd rho, rho a phi minus 1 over rho dA rho d phi. Okay? Quite complicated. So I'm capable of deriving these things, but I wouldn't want to. They're very messy. They're in the textbooks. When you need them, when you're solving a problem that has a curl of a vector field or a divergence of a vector field in the problem, and the geometry of the problem corresponds to cylinders, then you pull out your textbook and you look up these formulas. Okay? Same for the Laplacian and the gradient operator. Okay, this is cylindrical coordinates. Next up will be spherical coordinates. I'm Jeff Chasnov. See you in the next video. So in the next 2 lectures, I want to introduce spherical coordinates to you. We already did cylindrical coordinates, so that's the circle extended into the z direction, which is the cylinder shape. Now we're going to consider spherical coordinates, which is the geometry associated with a ball, right, with a sphere. So r is our position vector here. It has a length of r. And the other 2 coordinates is theta, the angle this position vector makes with the z-axis, and then phi, which is the angle that the projection of this position vector onto the xy plane, the angle it makes with the x-axis. So here we have x, y, z then, in spherical coordinates will be r, theta, and phi. Okay? The position vector can just be written as r hat. R hat is the direction of the position vector. So what is the transformation here? Well, we have x. So r sine theta projects onto the xy plane, and then cosine phi projects onto the x-axis. So this will be r sine theta cosine phi. Y, you project onto the xy plane, r sine theta, and then project onto the y-axis, which will be sine phi. And then z will be r, instead of sine theta, it will be r cosine theta. So projection onto the z-axis. Okay, so this gives us our change of variables formula. We also have the integral, the infinitesimal volume, dx, dy, dz, you can compute the 3 by 3 determinant of the Jacobian here, and you get r squared sine theta dr d theta d phi. So that's how you do the change of variables in spherical coordinates. Okay, now let's look at the unit vectors. Okay, so how do you write the unit vectors? The relationship between the unit vectors in spherical coordinates and the unit vectors in Cartesian coordinates. It's these rather complicated expressions. These are 3 by 3 matrices. If you know some matrix algebra, you can represent this as a matrix product. Then you can invert the matrix, and then you get I, j, k in terms of r hat, theta hat, and phi hat. So occasionally, these expressions need to be used. So I write them here. They're in the lecture notes. And you never memorize these things. These are things that you look up when they're needed. Okay, then in the next lecture, we're going to be talking about the differential operators. So in order to do that properly, we need to differentiate these unit vectors. Remember that the I, j, k vectors are fixed in space. Their derivatives are 0. But the r hat, theta hat, phi hat vectors depend on the angles. They depend on theta, and they depend on phi. So let's have a look to see if we compute the derivatives. Let's have a look to see what it looks like. Okay, so here are the derivatives of the unit vector. So again, r hat, theta hat, and phi hat depend on both theta and phi. So we need partial derivatives. So the partial derivative of r hat with respect to theta is theta hat. The partial derivative of theta hat with respect to theta is minus r hat. And the partial derivative of phi hat with respect to theta is 0. The partial derivative of r hat with respect to phi is sine theta phi hat. The partial derivative of theta hat with respect to phi is cosine theta phi hat. And the partial derivative of phi hat with respect to phi is minus sine theta r hat minus cosine theta theta hat. You can derive all of these from these expressions for the unit vectors. Okay, so in part A, I define what the spherical coordinate system is. Instead of x, y, z, we're using r, theta, phi. R is the length of your vector. Theta is the angle with the z-axis. Phi is the angle of the projection of the vector on the xy plane with the x-axis. This is the change of variables formula. This is how you do triple integrals. You transform dx, dy, dz to r squared sine theta, dr, d theta, d phi. R squared sine theta then is the determinant of the Jacobian. We also have the unit vectors, and we have the derivative of the spherical coordinate unit vectors. Everything's in the notes. When you need them to solve problems, typically, you look them up. It's very hard to remember these formulas. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. In the last video, we learned the basics of spherical coordinates. In this video, I want to show you how the differential operators are written in spherical coordinates. They're very complicated to derive, so I just want to write them down and then explain them to you. So let's just remember spherical coordinates, we've moved from x, y, and z coordinate system, the Cartesian coordinate system, to r, theta, and phi. R is the length of the vector, theta is the angle with the z-axis, and phi is the angle of the projection of the vector on the xy plane with the x-axis. Okay, so let me write down the differential operators. So the first differential operator is the gradient, the del operator. That takes the form r hat ddr plus theta hat 1 over r dd theta plus phi hat 1 over r sine theta dd phi. The del operator then is the kind of the basis of all the remaining calculations. The calculations are complicated because r, theta, and phi are all functions of the angles. Let's look at the next differential operator. So this is the Laplacian operator, del squared. You see it's getting quite complicated. The first piece is the derivative with respect to r, the second the derivative with respect to theta, and the last one the derivative with respect to phi. The derivative with respect to r, if you use the product rule here, you see it has a first derivative and a second derivative, and the same with the derivative with respect to theta. You may think this is so complicated, why would I ever need this? In fact, if you're a chemical engineer, you will need to learn how to do some quantum mechanics. If you want to solve the hydrogen atom, which is 1 proton and 1 electron, you do it in spherical coordinates, and you need to use the spherical coordinate form of the Laplacian. Okay, the next two sort of operations that I want to write are the divergence of a vector field and the curl of a vector field. To write that, I need to introduce a vector field. So let's introduce the vector field A. So it has 3 components. The components now are in the r hat, theta hat, and phi hat directions. So we write this as A sub r times r hat plus A sub theta times theta hat plus A sub phi times phi hat. And now we want to apply the del operator to this vector field. We're going to look at del dot A, and we're going to look at del cross A. Very complicated expressions. Let me write them down now. Okay, so this is del dot A and del cross A in spherical coordinates. You see how messy it is. Let me just step through it. So del dot A is a scalar. So it's 1 over r squared ddr of r squared a sub r. A sub r is the r hat component of A, plus the angular part, 1 over r sine theta dd theta sine theta a sub theta is the theta hat component of A, plus 1 over r sine theta dA phi d phi. A phi is the phi hat component of A. Okay, the curl is even more complicated. So it's a vector. Del cross A is a vector. There's a r hat component, a theta hat component, and a phi hat component. And then we have the differences here on the as part of the components of this vector. A very complicated expression. Okay, the good thing about this is that you usually only use these expressions when you have a lot of symmetry in your problem. So many times only A sub r is not 0 and the other 2 components are 0. So then you have a great simplification. But nevertheless, these are the general forms. You never memorize something like this. It's in the notes. If you ever need it in your engineering courses, you would go to your textbook or your notes and you would look it up. Okay, so let me summarize. This is the second part of my lecture on spherical coordinates. I'm trying to show you then how these differential operators are written in spherical coordinates. The gradient operator, the del operator, the Laplacian operator, and then how can we write the divergence of a vector field in spherical coordinates, and how can we write the curl of a vector field in spherical coordinates. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. Welcome to week 4 of Vector Calculus for Engineers. In this week, we'll learn how to compute line and surface integrals. We'll learn how to define line integrals. We'll use line integrals to compute arc lengths and to derive the work-energy theorem of physics. We'll then define surface integrals. We'll use surface integrals to compute surface areas. We'll also define the mass flux of a fluid flow and the flux of an electric or magnetic field through a surface. Please join me in this 4th week of Vector Calculus for Engineers. In this video, I want to define a line integral of a scalar field and show you how to convert a line integral into an ordinary one-dimensional integral. So we'll be working in the plane. A line integral means we have some curve. Say we'll call that curve C. We have a coordinate system, an xy coordinate system. We'll be working in the xy plane. So this is x and this is y. We can represent a point on this curve then by a vector. We'll call that r. To do a line integral, we break up this curve into small pieces. We'll call these small pieces ds, length ds. And then the definition then is in terms of a Riemann sum. So we're going to write the integral along the curve of some function of r ds. What that means in terms of the Riemann sum is that we broke this curve up into these small elements of length ds. Everywhere on the curve, we have some value of the function f of r. We're going to just take the average in these small elements, and then we're going to sum up all of the values of f times all of the lengths ds over the whole curve C that we specify. So that's a Riemann sum definition of the line integral. Okay. What is this ds, right? If we have our ds here, small element ds, this ds consists of a dx and a dy. And we have Pythagorean's theorem, so that ds then is going to be equal to the square root of dx squared plus dy squared. Okay? That will be our ds in terms of the Cartesian dx and dy. Okay, so there are 2 methods of doing this type of integral. The first method, let's say that this curve is specified by a function. So y equals some function of x, right? So it's a curve of y versus x. Then dy here, is going to be equal to y prime of x dx. And our ds then is equal to the square root of dx squared plus dy squared, which will be y prime of x dx squared. And you see that the dx squared then we can factor out. So that becomes the square root of 1 plus y prime of x squared dx. Okay? So we can do the whole integral then in terms of x. And we get this integral then over the curve of f of r ds becomes an integral then from the initial value of x to the final value of x on the curve of f. R then is the point, will be the point x, and the y coordinate, which will be y of x given in terms of x. And the ds then is the square root of 1 plus y prime of x squared dx. A one-dimensional integral. Okay? So provided we know the functional form for the curve, y equals y of x in the xy plane, then the line integral of f along that curve, the integral along the curve f of r ds, can be written in terms of a one-dimensional integral in x. F of x y, which is a function of x, times the square root of 1 plus the derivative of y with respect to x squared dx. Okay? That's the first method. The second method for computing this type of line integral is if this curve is parameterized. So a parameterization of the curve would say that x then is some function of t for this curve, and y is also some function of t. Okay? So then what is dx and dy? In that case, then dx is equal to dx dt times dt. I'm going to use the notation x dot for dx dt. So dx dt times dt. And dy then is dy dt, or y dot, times dt. Then our ds in the line integral is the square root of this squared plus this squared, which will be the square root of x dot of t squared plus y dot of t squared. And then both terms have dt in them, so then dt. Okay? So we can write our element of the curve ds in terms of x dot squared plus y dot squared square root dt. Okay. So again, the integral along the curve f of r ds. Then in terms of the parameter t is equal to the integral from the initial value of t to the final value of t, so the start of the curve to the end of the curve, of f of r, so that would be f of x of t, y of t, right? So a function of t, times ds. So ds here will be the square root of x dot of t squared plus y dot of t squared square root dt, a one-dimensional integral. Okay, let me summarize. I'm defining the line integral of a scalar field. F of r is our scalar field as a Riemann sum. So you have a small element of length ds and a value of f on that element. We multiply them together, the length times the value of f, and then we sum over all of the elements on the curve. And that's the definition of this integral. Okay. To do this integral, we show that ds is just the square root of dx squared plus dy squared. And there's two possible ways to do this integral. One, if we know that y is a function as a function of x, so we have the curve y equals y of x, then the integrals can be done in x from the initial value of x to the final value of x of f of x times of f of x, y of x, so y is supposed to be known as a function of x, times this factor square root of 1 plus 1 prime of x squared dx, a single variable integral. The other way of doing it is if the curve is parameterized. So x is a function of time or t. It doesn't have to be time, but any parameter t. Y is a function of t. Then we can write dx as x dot dt, dy equals y dot dt. And ds then becomes the square root of x dot square plus y dot square times dt. Then using our parameter t, we can integrate through this line integral starting at t naught, ending at tf, and then having f, which now is a function of t, times this factor dt. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. One of the interesting applications of the line integral of a scalar field is to compute the arc lengths of curves, or if you have a closed curve, to compute the perimeter. So the arc length P of a curve C is given by P is the integral over the curve of ds. So we're just adding up all of the little lengths of the curve. So here the function is just equal to 1. As a reading problem, I ask you to prove that the circumference of a circle is 2 pi times the radius, the well-known result, by computing this type of integral. Here I want to tackle a more challenging problem, which is the perimeter of an ellipse. It turns out that there is no closed form formula for the perimeter of an ellipse, like 2 pi r. So we'll end up with an integral that is actually a very famous integral. So let's set up the problem for the ellipse. So we're looking at an ellipse. We'll choose in the xy plane. So we have our ellipse here. The major axis will be have a length a, and the minor axis will have a length b. The equation for the ellipse is well known. It's x over a squared plus y over b squared equal to 1. And there's a number that characterizes an ellipse that's called the eccentricity, e. So e is equal to the square root of 1 minus b over a squared. So here a is supposed to be larger than b. And this is called the eccentricity. OK. So we're going to then compute the perimeter of the ellipse, this arc length. We're going to do that then by parameterizing the ellipse. So the parameterization of the ellipse is going to be x equals a cosine theta, y is equal to b sine theta, right? So x over a squared is cosine squared theta. Y over b squared is sine squared theta, and that's equal to 1. So this parameterizes the ellipse, and theta then goes from 0 to 2 pi. OK, what is dx then? Dx is equal to minus a sine theta d theta, and dy is equal to b cosine theta d theta. So our ds then is the square root of dx squared plus dy squared, right? And what does that work out to? That's equal to the square root of a squared sine squared theta plus b squared cosine squared theta. And then we have a d theta squared, so square root of that gives us a d theta. Okay, how do we manipulate this? Well, I would like to see the eccentricity in this formula, right? This is going to be what we integrate over. So let me put it up here. So our ds then, so this is a b over a, so I should factor out an a. So we have an a. And then I want to somehow combine terms, so I would like to write everything in terms of cosine. So we have square root. So that will be sine squared theta. So instead of sine squared theta, we can write 1 minus cosine squared theta for sine squared theta. And then we factored out an a, so we have a b over a squared plus b over a squared, and also a cosine squared theta, okay, and times d theta. Okay, so we're looking for the eccentricity. So we have a cosine squared here and a cosine squared here, and we're looking for a 1 minus b over a, so I can write that as a. And then we have a square root. We have a 1. And then we have we want a 1 minus b over a, so we can say minus here. And then we have a 1 from we're going to multiply by cosine squared theta. So we have a minus cosine squared theta. And then we have a plus here and a minus here, so that would be a minus b over a squared. And that whole thing then is multiplying cosine squared theta d theta. Okay, a little bit messy math to do in my head, but it's okay. We can then replace this by our eccentricity. So this becomes a times the square root of 1. The eccentricity is the square root of this thing, so 1 minus e squared cosine squared theta d theta. Okay, we're almost done. We put that together. Then the formula for the perimeter of an ellipse is the integral over the curve ds is then going to be, in terms of the parameter, theta goes from 0 to 2 pi. And then our ds is a, which comes out of the integral, times the square root of 1 minus e squared cosine squared theta d theta. And that is usually, so cosine squared theta goes between theta equals 0 and pi over 2. It goes from 1 to 0. Then from pi over 2 to pi, it goes from 0 to minus 1, but we're squaring it. And then it goes from minus 1 back to 0 when it goes from pi to 3 pi over 2. And then from 3 pi over 2 to 2 pi, it goes from 0 back to 1. So there's kind of like 4 equal contributions to this integral. So you usually then multiply by 4, so 4 times a, and then you write this as an integral from 0 to pi over 2 of root 1 minus e squared cosine squared theta d theta. Okay? And then one more thing. It doesn't matter whether this one is cosine theta or sine squared theta. Cosine squared theta or sine squared theta. It's the same integral. Cosine squared theta goes from 1 to 0. Sine squared theta goes from 0 to 1. So it's exactly the same value. So usually when you look at this, say, on Wikipedia, you would see a sine squared rather than a cosine squared. That's a formula for the perimeter of an ellipse. It turns out not to be able to do this integral analytically. And this integral then has actually a very nice name. I'm going to squeeze the writing of the name in here. This is called the complete elliptic integral of the second kind. Okay? The complete elliptic integral of the second kind. Okay, that opens up a lot of questions. What's the incomplete elliptic integral? What's the elliptic integral of the first kind? There's a lot of math in this formula. But this comes from just computing the perimeter of an ellipse. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. Most of the physical problems that we define in terms of line integrals are actually line integrals of a vector field, not of a scalar field. So in this video, I want to first define what does it mean to take the line integral of a vector field, and then I'll work some simple examples. So let's draw our curve. So that's our curve C. Now the curve is going to be directed, so it will have some direction. On this curve, we have a well-defined vector field. So let's say the vector field may be, say, pointing something like this on this curve. So this could be our vector field U. And at the same time, we have an element of the curve, say, pointing along the direction of the curve always. And this element here we're going to call dr. So the line integral of this vector field u along the curve, we're going to write as the integral along the curve of u dotted into dr. So it's basically saying that you have to take the component of u along the curve to do the line integral. But this is actually can be written in terms of a scalar, a line integral of a scalar field. If we say that dr, right, is equal to some tangent unit vector times ds, right? So we can define this vector dr of the small element as in the direction of the curve with the unit vector t hat, the tangent unit vector, times some length ds. Then this integral becomes the integral over the curve. Dr now is t hat ds, so it's u dot t hat times ds. And that's just the line integral of a scalar field. But here the scalar field is our vector field dotted into the tangent unit vector to the curve. Okay? How do we compute such an integral? Usually we do it by parameterizing the curve. So we let r vector be a function of time. So then that dr becomes dr dt dt. And then this integral along the curve of u dot dr becomes the integral from the initial parameter t0 to the final parameter tf. So sometimes this is time, sometimes it's some other type of parameter, of u now evaluated at r, which is evaluated at t, dotted into dr dt, and then integrated dt. That's how we would usually compute the line integral of a vector field. Okay, let me work then two examples. So I want to compute the line integral of the r vector field, so the position vector, which is xi plus yj, in the xy plane along two curves from the origin, 0, 0, to the point 1, 1. In the first curve, we're going to go first along the x-axis and then along the y-axis to get to 1, 1. So this is xy. In the second curve, we're going to go directly from the origin to the point 1, 1. Okay, so let's do the first one. We have two line integrals here, right? The first along the x direction, the second along the y direction. So in the first integral, we're going to have dr then is going to be equal to dx times the I unit vector. In the second integral, along the y direction, we're going to have dr equal to dy times the j unit vector. So putting then doing these line integrals, we have the line integral along this curve of r dot dr then is going to be the integral along x. So x goes from 0 to 1. Since dr is along the I direction, it just picks out the xi vector from r. So this will be just x dx. Then the integral along the y direction will be dr is dyj. So r dot dr there will just pick out y. So that will be, as y goes from 0 to 1, y dy. So this is 1/2 x squared over 2, evaluated between 0 and 1. This one is also 1/2, and then the sum is 1. So this line integral is 1, both of them consisting of 1/2. Okay, what about the second curve? So curve number 2. What is r here? We can parameterize r as some t times I plus j, right? So it's going along this diagonal. So the x value is always equal to the y value. And then t goes from 0 to 1. So this point here is just the I unit vector plus the j unit vector. So that's the parameterization of the curve. So then dr is simply I plus j dt. Okay. Then we have our integral then, our integral along the curve of r dot dr. So t goes from 0 to 1. So the integral from 0 to 1 of r dot dr. So we have I dot I is 1, j dot j is 1. The cross products are 0. So we end up with 2t dt. And that's t squared over 2. The 2's cancel from 0 to 1. And again, we get just 1. Okay? So using these two curves, we get the same result. The line integral of the position vector from the origin to the point 1, 1 along the first curve, along the x-axis, then up the y-axis, is 1. And the same way if we just went from the origin to the point 1, 1 directly. Two different parameterizations of our curve. We did the integral and we got the same result. So let me summarize. To define a line integral of a vector field, we can define it in terms of a line integral of a scalar field, except that when we write it as the integral along the curve u dot dr, what we mean is the integral along the curve of u dotted into the unit tangent vector of the curve times ds, which is the line integral of a scalar field. Okay, to actually do this integral, we usually parameterize r, and then we write dr vector as dr dt vector times dt, and then do this dot product. Here I give you what are essentially two very simple examples. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. In the previous few videos, we talked about line integrals. In the next few videos, I want to talk about surface integrals. We'll begin with the surface integral of a scalar field. We have some surface in 3 dimensions. The surface itself is a 2-dimensional object. We have a scalar field defined on the surface. The surface integral of the scalar field will be obtained by a Riemann sum, where we break the surface into small surface elements ds. We multiply each element by the average value of the scalar field, say f of r, on that surface element. And then we sum over all of those surface elements. So we'll denote that by the surface integral of f, the scalar field, evaluated at r, integrated over the surface. Okay. So how do we actually compute such an integral? We have to do a parameterization of the surface. To parameterize a surface, we'll parameterize it by parameterization of r. We need 2 variables, which I'll call u and v, to parameterize. So that will be x, which will be a function of u and v in the I direction, plus y, which is a function of u and v in the j direction, plus z, which is a function of u and v in the k direction. From this parameterization of the surface, we construct the surface element, ds, so the area of this small element. We can get that by small variation in r. We use the partials with respect to r, so partial of r with respect to u, and cross it against partial of r with respect to v. This is a vector which represents the area of this small parallelogram. So we take the absolute value of that, and then we'll need a du and dv. So this, using the cross product and the partial derivatives, this term here then is the element of surface area ds. It's the area of a tiny parallelogram that we get when we vary r with respect to u and r with respect to v. Okay. Let's look at a particular case. What happens if z then is a function of x and y? So we specify the surface above the xy plane, given by z as a function of x and y. Here our parameters then, instead of u and v, our parameters will be x and y. So our r then is going to be equal to x times the unit vector I plus y times the unit vector j plus z, which is a function of x and y, times the unit vector k. So that will locate then a position on the surface. To compute this surface integral, then we need the partial derivatives. So we have the partial derivative of r with respect to x will be the derivative with respect to x will be I. The derivative of y with respect to x is 0. And the partial derivative of z with respect to x will be partial of z with respect to x times k. Similarly, partial of r with respect to y, the derivative of x is 0. The derivative of y is 1. So that will give us j plus partial of z with respect to y times k. Now we want to determine ds. So we need this cross product. So the cross product of partial of r with respect to x, which is a vector, crossed into partial of r with respect to y, is this 3 by 3 determinant, right? It's I, j, and k. Partial of r with respect to x, so that would be 1 I plus 0 j plus partial of z with respect to x k. And then partial of r with respect to y is 0 I plus 1 j plus partial of z with respect to y. Okay, so what is this? This 3 by 3 determinant. So it's I times a 2 by 2 determinant here. So negative partial of z with respect to x times I plus j times this 2 by 2 determinant with a negative sign. So it will be minus partial of z with respect to y times j plus k times this 2 by 2 determinant, which is 1, so plus k. So that gives us our dr dx cross dr dy. The ds then is the length of this vector times dx dy. So if we put that together, then we have the integral over our surface of f of r ds is going to be a double integral over the area that we're integrating in the xy space. So let me just say integral of a. And then we have our f of r. So r is depends on x, y, and z, right? So we can write x, y, and z here. X, y, and z, which is a function of x and y, right? Times ds. So our ds here is the magnitude of this vector. So it is the square root. So the k component has 1, so it's 1, plus the x component, say, so we square this. So it's partial of z with respect to x squared plus partial of z with respect to y squared from the j component, square root. And then finally dx dy. Okay? So then this gives us a formula for integrating a scalar field over a surface in the case where the surface is specified by z, which is a function of x and y. So we integrate over x and y. We have our scalar field, which is specified once you know the x and y value. And then we have our ds, which has to be calculated by taking the partial of z with respect to x and the partial of z with respect to y. So let me summarize. I'm defining what it means to take the surface integral of a scalar field. As always, we define it in terms of a Riemann sum. To actually do the integral, we have to somehow parameterize the surface. If we parameterize the surface with two variables u and v, then we have to have our ds coming from essentially the area of this little parallelogram, which is given in terms of the cross product of the two partials of r and the length of that vector. In the case where we have a surface which is on top of the xy plane, so that the height is parameterized in terms of x and y, then we can derive a formula for this surface integral as an integral over dx and dy. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. In the last video, I defined the surface integral of a scalar field. If the scalar field is just 1, then the surface integral gives us the area of the surface. So I want to use the machinery of surface integrals to derive the surface area of a sphere. We all know it's 4 pi r squared, where r is the radius of the sphere. So we're going to parameterize the sphere using spherical coordinates. So x is r sine theta cosine phi, y is r sine theta sine phi, and z is r cosine theta. Capital R is fixed, so the sphere is a fixed radius, capital R. So this is a parameterization of the sphere in terms of the angles theta and phi. So our r then, which is a function then of the parameters theta and phi, is equal to x r sine theta cosine phi in the I direction, plus y r sine theta sine phi in the j direction, plus r cosine theta in the k direction, the z direction. OK, to find the area of the surface area of the sphere, then we need to compute ds. To get ds, we need the partial derivatives of r. So we have the partial of r with respect to theta. To begin with, the derivative of sine theta is cosine theta. So r cosine theta cosine phi I. The derivative of sine theta is cosine theta, so plus r cosine theta sine phi j minus r sine theta k. Okay? The other partial derivative is partial of r with respect to phi. That will be minus r sine theta sine phi I. The derivative of sine phi is cosine phi plus r sine theta cosine phi j. And the k component doesn't depend on phi, so we get 0. OK, now we need to take the cross product of these two partial derivatives. So the cross product of partial of r with respect to theta times partial of r with respect to phi. That's equal to a 3 by 3 determinant. So we have the I component. Then we have the j component. And then we have the k component. Okay? So partial r with respect to theta, the r component is r cosine theta cosine phi. So we have an r cosine theta cosine phi. The j component is r cosine theta sine phi. So we have an r cosine theta sine phi. And the k component is minus r sine theta. So minus r sine theta. Okay? Partial of r with respect to phi. The I component is negative r sine theta sine phi. The j component is r sine theta cosine phi, r sine theta cosine phi. And the k component then is 0. Okay. So we need to compute this. So let me put it up here. So we have our dr d theta cross dr d phi. So the I component will be this 2 by 2 determinant here, deleting the first column and the first row. So 0 minus minus. So we have an r squared sine squared theta cosine phi, r squared sine squared theta cosine phi. That's the I component. The j component is cross the second column, first row, and then with a minus sign. So we go the other direction. So capital R squared sine squared theta sine phi plus r squared sine squared theta sine phi j. And then the k component is going to be this 2 by 2 determinant. So r cosine theta, r squared cosine theta sine theta cosine squared phi plus r squared cosine theta sine squared phi. If you let me do some algebra in my head, we have a cosine squared phi plus a sine squared phi. So then we'll end up with an r squared cosine theta sine theta plus r squared cosine theta sine theta, because the cosine squared phi sine squared phi is 1. And that's the k direction. Okay, what we need then is the magnitude of this. So we have the length of this vector, dr d theta cross dr d phi. What are the common terms here? There's an r squared, which is common. And then each term, these have a sine squared theta, sine squared theta, sine theta. So there's also a common sine theta. So we can factor them out. So we have an r squared sine theta. And then whatever is left over. So we need to square the components, add them, and then take the square root. So we have a sine theta cosine phi left over. So when we square them, we end up with sine squared theta cosine squared phi. Then we have sine theta sine phi left over. So when we square it, we have a sine squared theta sine squared phi. Finally, we have a cosine theta left over, only a cosine theta. So that becomes a cosine squared theta. And then this factor is supposed to be to the 1/2 power. So we squared the components, added them, and took the square root. OK, this actually simplifies. So we have sine squared theta times a cosine squared phi plus sine squared phi. That's 1. So this will give us sine squared theta. And then sine squared theta plus cosine squared theta is 1. So remarkably, this whole term in the parentheses is 1. The square root of 1 is 1. So this gives us r squared sine theta. Okay? So what we've done then is derive ds. Let me put that in red. So our ds here then is the length of this vector, r squared sine theta, times d theta d phi. And that's an important result that we'll use later when we talk about the fundamental theorems of vector calculus. OK, now we have the remaining work to do. So the surface area of the sphere is the integral of our ds over the surface of the sphere. So this is going to be a double integral. So we have a double integral of r squared sine theta d theta d phi. Theta goes from 0 to pi. Phi goes from 0 to 2 pi. We need to do this integral, which is not very difficult. So this separates. So this is an integral. This is an r squared comes out. And then an integral from 0 to 2 pi of d phi times an integral from 0 to pi of sine theta d theta. The integral d phi from 0 to 2 pi is 2 pi. The integral of sine theta d theta from 0 to pi, if you do that, you get cosine. This will give you 2. So 2 times 2 pi is 4 pi times r squared. And we get the result that we know the answer to. The surface area of a sphere of radius capital R is 4 pi r squared. Wow, a lot of work to get an answer that we know already. But I show you then the machinery, and we also get the very nice result that the surface element of a sphere is r squared sine theta d theta d phi. We'll make use of this one later. So let me summarize. We're computing the surface area of a sphere by doing a surface integral. It's a surface integral of a scalar field, but the scalar field is just 1. So that then we end up getting the surface area of we summing up all the ds's to get the surface area. We parameterize the sphere using spherical coordinates. We compute ds as r squared sine theta d phi. We integrate ds, and we get 4 pi r squared. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. We've already talked about the surface integral of a scalar field. In this video, I want to define the surface integral of a vector field. So let's say that this is our surface, and we have a vector field u defined on the surface. The surface integral of the vector field we'll define as the integral over the surface of u dotted into a vector ds, but the vector ds is just going to be the normal vector to the surface, which I'll denote as n hat times the scalar ds that we've seen already for the surface integral of a scalar field. So the key here is that to define the surface integral of a vector field, we take the dot product of the vector field with the normal unit vector to the surface that I denote as n hat. Okay, to show you how that works, I wanted to do two examples. The vector field we're considering is going to be just the position vector r. So the u here is just going to be r. That's xi plus yj plus zk in Cartesian coordinates. And we'll consider two types of closed surfaces. The first surface will be a cube that's centered at the origin with a side length of L. And the other closed surface will be a sphere that's centered at the origin with the radius capital R. So let's go through these two examples. So the first example will be the cube. So let me draw a miniature cube here. Okay. Try my best to draw a cube. Okay, so it has 6 sides. It's centered at the origin. It turns out that the surface integral over each of the sides is the same. So we only need to do a surface integral over one of the sides and then multiply by 6. The 6 sides are denoted as x equals plus or minus L over 2 as the two sides that are at x, at the fixed positions at x, or y equals plus or minus L over 2, or z equals plus or minus L over 2. So those are the 6 sides. The one I want to do is the side at x equals plus L over 2. At that side, our position vector, which is the vector field that we're integrating, is going to be x is fixed, so it's L over 2i. But the y and z will vary, so it's y times j plus z times k. Y and z vary on that face. On the other hand, our ds for that face, the normal vector, so say this is the face at x equals plus L over 2. So this is the normal vector. The normal vector is just going to be pointing in the x direction, so that's just the unit vector I. So the ds here then is going to be I ds. Okay? So our integral over that single surface at x equals plus L over 2 is supposed to be r dot ds. So because ds is I in the I direction, r dot ds just picks out the I component of r. So that will become the integral over the surface of L over 2 ds. Okay? And ds, the integral of ds then, is the area of that one surface, which is just L squared. So it's the area of the square of side length L. So the integral ds is L squared. So this becomes L cubed over 2. So then our total integral over all 6 faces of r dot ds, each of them will have this value. So it's 6 times L cubed over 2, which is 3L cubed. Okay? The volume of the cube is just L cubed. So this is actually 3 times the volume of the cube. And we'll actually prove that later when we have our fundamental theorems of vector calculus, particularly the divergence theorem. Okay, so that's the surface integral of r vector over a cube. The second one that I wanted to do was the surface integral of r, the position vector, over a sphere. Let me quickly draw the sphere here. This is radius r. So the position vector r on the sphere has a length capital R and pointing in the r hat direction from spherical coordinates. And then our ds is the normal vector to a sphere is also r hat, the unit vector in the r direction, times the scalar surface element ds. This is particularly easy to do. The integral over the closed sphere of r dot ds then, r hat dot r hat is just 1. So this is just r times the surface integral ds, which is the surface area of a sphere, which we know is 4 pi r squared. So this gives us 4 pi r cubed. Okay? Rather simple calculation. The volume of a sphere is 4/3 pi r cubed. So again, this works out to 3 times the volume of a sphere. Okay? And we'll show that from the divergence theorem. Okay, so let me summarize. We're defining the surface integral of a vector field. To do that, we need to know what the normal unit vector to the surface is. For a cube, it's very simple. It's just the, for a cube centered at the origin, it will just be I, j, or k, depending on the face. For a sphere centered at the origin, it's just r hat. Those are the normal unit vectors to the surface. And then we have to integrate over the surface element ds. So we convert the surface integral of a vector field into the surface integral of a scalar field, where the scalar field is the vector field u dotted into the normal vector to the surface. I worked the example for a cube centered at the origin and for a sphere centered at the origin. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. The surface integral of a vector field is sometimes called a flux integral. And the flux integral usually has some physical meaning. I think originally it came from fluid mechanics, so let me discuss it first in that context. That's called the mass flux. And that has the formula that the integral over the surface of the density of the fluid times the velocity of the fluid dotted into ds. Okay? So let's try and break down what exactly is the meaning of mass flux. So rho is the density. So let me use this brackets to denote the units of rho. So a density has units of mass per unit volume, or here length cubed. That's the density of the fluid, right? The velocity of the fluid has units of length per unit time, so length over time. That's the velocity. And then we're integrating over the surface. So the units of our surface is going to be length squared, right? So an area has units of length squared. So putting it together, the units of our mass flux, the units of this integral, rho u dot ds, then multiplying these three together, the length cubed cancels the length cubed, and we end up with units of mass per unit time. Okay? So the mass flux then is as the fluid flows through this surface, right? It has to, you're dotting with the normal vector to the surface because the fluid is flowing through the surface. The mass flux then is the mass per unit time of the fluid that flows through this surface S. Okay? That's in the context of fluid mechanics. We also have, in the context of electricity and magnetism, we have both the electric flux and we also have the magnetic flux. These flux integrals will be the integral over the surface of the electric field dot ds. And the magnetic flux will be the integral over the surface of the magnetic field dot ds. So these quantities show up in the integral form of Maxwell's equations. So let me give a simple example here. If we have a charge basically fixed at the origin, so a charge Q at the origin, the electric field of that charge is given by the charge Q over 4 pi epsilon naught times r squared. Epsilon naught is a constant in the direction of the radial vector from the origin. Okay, so it's spherically symmetrical electric field. So let's say that we want to compute the electric flux then through a sphere. So we can draw our sphere here, and we have our charge Q then in the center of the sphere, right? So we want to compute then the electric flux around the sphere, closed surface, of E dot ds. What would we get? So now the electric field on the surface has some radius, so I'm going to call that capital R. So the electric field on the surface then is going to be Q over 4 pi epsilon naught r squared. And then the normal vector is r hat here. So the normal vector to the surface is r hat. So we have E dot ds will be r hat dot r hat ds. So r hat dot r hat is 1. So this will be the integral over the surface ds. So let me put an s here to denote that we're integrating over the surface of the sphere. So this is just a constant. So this is Q over 4 pi epsilon naught capital R squared times the surface area of a sphere, which is 4 pi r squared. So it's Q over 4 pi epsilon naught r squared times 4 pi r squared. And then we get just Q over epsilon naught. Okay? So the electric flux due to a point charge Q at the origin across a sphere of radius r is actually independent of the radius of the sphere and is given by the electric charge over this permittivity constant epsilon naught. Okay? That's actually one of Maxwell's equations. Okay, so let me summarize. In this video, I wanted to introduce the physical meaning of a flux integral. This is the surface integral of a vector field. For a mass flux, it's the mass per unit time that passes through the surface. It's given by the integral of rho u dot ds. For the electric flux and the magnetic flux, it's the integral of E dot ds through the surface for electric fields. electric flux, and B dot ds for magnetic flux. Then I worked the simple example of a charge Q at the origin. What is the electric flux through a sphere centered at the origin? It's equal to the charge Q divided by epsilon naught. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. Welcome to week 5 of Vector Calculus for Engineers. In this week, we'll learn the important fundamental theorems of vector calculus. These theorems are an extension of the fundamental theorem of calculus, which relates the derivative and the integral. We'll learn the gradient theorem and the definition of a conservative vector field. We can then use the work-energy theorem to derive the law of conservation of energy. We'll learn the divergence theorem. The divergence theorem will be used to derive the continuity equation of fluid mechanics. We'll then derive Green's theorem and generalize it to Stokes' theorem. The divergence theorem and Stokes' theorem provide us coordinate-free definitions of the divergence and curl of a vector field. Finally, the divergence theorem and Stokes' theorem are used to derive the differential form of Maxwell's equations. Please join me in this 5th and final week of Vector Calculus for Engineers. In this video, I want to start talking about the fundamental theorems of vector calculus. You may recall from your single variable calculus, the fundamental theorem of calculus was the one that told you how you can integrate the derivative of a function, right? The integral of the derivative of a function is just going to be the function itself. So it tells you how to do integrals by doing antiderivatives. So the gradient theorem is a generalization of the fundamental theorem of calculus to vector calculus, to calculus of several variables. So let me see if I can convince you how this works. So remember, if we have a scalar field, I'll call it here phi. So we have a scalar field phi. If we take the differential of phi, we can use the gradient to do that. That's the gradient of phi dot dr. Okay? So the change in phi is the gradient of phi dot dr. So let's look at a line integral of this function. So I want to integrate around some curve. So let's have some curve, call that a curve C, right? And then some origin somewhere. So we have some origin of our coordinate system. So the starting point has some position vector. So let's call that R1. And the ending point has some position vector. I don't think I can draw a straight line here, but I'll try my best. So that one will be R2. So let's integrate this gradient dot dr. So the integral along this curve C of del phi dot dr. Well, this is just the change in phi. So this is the integral along the curve C of d phi. Okay, and that's easy to integrate. That's just the change in phi. So that's phi at the top, which would be position vector R2, minus phi at the bottom, which is position vector R1. Okay? So this is a fundamental theorem in that it tells us that we can do this line integral of a gradient of a function dot dr by just knowing the value of the function itself at the endpoints of the curve, just like the fundamental theorem of single variable calculus, except now that we're in more than one dimension. Okay, there's an important consequence of this. The integral of del phi dot dr along a curve then just depends on the value of phi at the endpoints of the curve. So if the endpoints are at the same point in space, in other words, we're integrating over a closed curve of del phi dot dr, then the difference in phi at the starting point and the end point will be 0 because the starting point and the end point are the same. Okay, this is the basic theory. Let's try and then work an example. So the problem I want to solve using the gradient theorem is to compute the line integral of the position vector r equals xi plus yj in the xy plane from the origin to the point 1, 1. This is exactly the same problem we solved when we did the example for line integrals. I did two paths. I did along the x-axis and then in the direction of the y-axis. And then I did the direct path. And we got the same answer both ways. And it turns out because it's independent of path. So how do we apply the gradient theorem to show that the solution here is independent of the path? We're doing an integral of r dot dr. So we need to write r in terms of the gradient of some function. So I want to write r equals the gradient of some function, right? So that means we're writing that as d phi dx times I plus d phi dy times j. How do we get d phi dx equal to x and d phi dy equal to y? Well, the derivative of 1/2 x squared is x. The derivative of 1/2 y squared is y. So we should be able to add these. So I can write this then as the gradient of 1/2 then of x squared plus y squared, right? So here d phi dx is x and d phi dy is y. Okay, so now we have r is written as a gradient. So I can write, we're computing the line integral of r. So we're computing the integral along this curve of r dot dr, right? And that will, because r then is written as the gradient, that's the integral along the curve of the gradient dot dr. Then we can use the gradient theorem. So this is just the value of phi, which sometimes it's called the potential, the value of the potential at the endpoint minus the value at the starting point. So that's equal to the potential 1/2 x squared plus y squared, evaluated then at the endpoint then, which will be 1, 1, minus the value at the starting point, which is 0, 0. So x equals 1, y equals 1, minus the value at x equals 0, y equals 0. So the lower limit will just be 0. The upper limit then is 1/2 1 plus 1, or 1/2 times 2. So that gives us the value of 1, which if you look back at your notes, that's the same value we computed for this line integral along two different paths. Okay, so let me review. The gradient theorem is the closest to the fundamental theorem of calculus in single variable calculus. It tells us that we can integrate the gradient of a function dot dr along some path, along some curve C. And then if the integrand is del phi dot dr, then this will just result in the value of phi at the endpoint of the path minus the value of phi at the starting point. Because if the endpoint is the same as the starting point, the curve is a closed curve, so the integral of del phi dot dr around a closed curve will be 0. This gives us a quick method of computing a line integral. As long as we can write the integrand in terms of the gradient of a function, then these type of integrals become very, very easy. What mathematicians like to say, trivial. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. In the last video, we learned about the gradient theorem. The gradient theorem is closely related to what physicists called a conservative vector field. When we wrote u equal to del phi, that phi in physics would be related to the potential energy. The u would be related to the field that the potential energy is arising from. Here we're going to treat this as a mathematical object. A conservative vector field will be a vector field that satisfies one of 4 conditions. All of them are equivalent. The first condition is that the vector field can be written as the gradient of some scalar field. Okay, we saw that was useful for the gradient theorem. The second condition is that the curl of the vector field is equal to 0. Okay? Because we've already proved the theorem that the curl of a gradient is equal to 0. So if u can be written as the gradient of a potential phi, then that means that del cross u has to be 0. Okay. The third condition, which is equivalent to these first two, is that the integral of u dot dr along a curve C doesn't matter how you draw the curve C as long as you have the same starting point and the same ending point. So we say that this is path independent. Okay? Another way of saying path independence is simply that the integral around a closed curve of u dot dr is going to be 0. Okay? 4 statements of u being a conservative vector field. It's equal to the gradient of some function. The curl of that vector field is 0. The line integral of that vector field over some curve is independent of the path of the curve as long as it has the same starting point and ending point. And the integral over a closed curve then has to be 0. Okay, let's work a problem having to do with conservative vector fields. Okay. So the problem we want to solve is to let u, the vector field u of xy, equals x squared 1 plus y cubed I plus y squared 1 plus x cubed j. That's our vector field. I want to show that U is a conservative vector field, so it satisfies these 4 conditions. Any one of these conditions is fine. And we want to determine the phi such that U equals del phi. So in general, the easiest way to determine whether U is a conservative vector field is to take the curl of U and see if it's equal to 0. That's just a straightforward calculation. So we have the curl of U is this 3 by 3 determinant. So it's I, J, K. So d dx, d dy, d dz of the x component is x squared 1 plus y cubed. The y component is y squared 1 plus x cubed, and the z component is 0. So this determinant. So the I component then will be d dy of 0 minus d dz of something that doesn't depend on z, so that's 0. The j component will be d0 dx is 0, or the negative of this, minus d dz of this, which depends on x and y, is also 0. So the only thing remaining is the k component here. So we have d dx of this one is the derivative of y squared is 0. So we end up with a 3x squared y squared minus d dy of this first one. So the d dy of x squared is 0. So d dy of x squared y cubed is 3x squared y squared. And 3x squared y squared minus 3x squared y squared then is 0. Okay? So the curl of this vector field then through a straightforward computation is 0. That means it satisfies the condition 2 here. All of these conditions are equivalent, so that U then is a conservative vector field. In part B then, I want to determine the potential function phi such that U equals del phi. So U equals del phi then is 2 equations, right? So it means the x component of U equals the x component of del phi, and the y component of U equals the y component of del phi. So the equations for phi will be the x component of del phi then is d phi dx. And that's supposed to be equal to the x component of U. So that's x squared times 1 plus y cubed. The y component of del phi then is d phi dy. And that's supposed to be equal to the y component of U. So that's y squared 1 plus x cubed. Okay? So to determine this potential function phi, we need to solve what is essentially 2 differential equations. But these are partial differential equations, if you want to be precise. But they're actually rather simple to solve, and in these cases they usually are. The way to solve this is to simply integrate with respect to x holding y fixed. So we take this first equation. So we have phi is going to be the integral with respect to x of x squared 1 plus y cubed dx, holding y fixed, right? So this becomes integral of x squared is 1/3 x cubed times 1 plus y cubed, right? You can see that the partial derivative of this with respect to x gives us x squared times 1 plus y cubed. But if we differentiate this with respect to x to get x squared times 1 plus y cubed, we have a freedom of another function here, which is only a function of y. So the partial derivative of phi with respect to x, the function of y will be 0 if we differentiate with respect to x, and we end up with x squared times 1 plus y cubed. Okay, so we still have an unknown function y here. So we use the first equation. Now we can use the second equation. So we can write d phi dy then. We can differentiate this with respect to y. So 1/3 x cubed will be 0 because it doesn't depend on y. So we have 1/3 x cubed y cubed. The derivative with respect to y will give us x cubed y squared, plus the derivative of f with respect to y, which is f prime of y. And that's supposed to be equal to d phi dy, which is y squared plus x cubed y squared. Okay? X cubed y squared then will cancel x cubed y squared. So that gives us f prime of y equals y squared, right? The derivative of this function with respect to y is y squared. We can integrate then y squared, so that means f of y is going to be 1/3 y cubed plus a constant. Here we have a real constant because the derivative of f with respect to y, the constant will go to 0. Okay, putting it all together, we have phi is equal to 1/3 x cubed times 1 plus y cubed plus 1/3 y cubed plus a constant. Might as well write that neatly. We get 1/3, and then we have x cubed plus x cubed, y cubed plus y cubed plus a free constant. Okay, we've computed this potential function phi so that now u, the u that we were given, is equal to the gradient of this phi. This is a useful calculation because now if we do a path integral of u dot dr, all we need to know is the value of phi at the endpoints. So this is the gradient theorem, equivalent to the fundamental theorem in single variable calculus. So let me review. We say a vector field is a conservative vector field if it's the gradient of some function. If it's the gradient of the function, then the curl of that vector field is 0. The second condition is the one we can use to determine if a given u is a conservative vector field. The consequences of being a conservative vector field is that the integral of u dot dr over some curve is path independent, and that's equivalent to the integral of u dot dr over a closed curve is 0. In this calculation, I show you that to prove that u is a conservative vector field, just show that its curl is 0. And to determine the potential such that u equals del phi, you have to set up the two equations and then do some single variable integration. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. In the last video, I talked about conservative vector fields. The reason we use the word conservative is because the concept of a conservative vector field is closely related to the physics concept of conservation of energy. So let me show you the relationship in this video. So we can begin with the work energy theorem, which we derived previously. We have the integral over some curve of the force dot dr, changes the kinetic energy of a mass, so it's equal to the final kinetic energy of the mass minus the initial energy of the mass. So this is the work done by a force on the mass imports energy to the mass, where the kinetic energy of the mass is 1/2 m times the speed of the mass squared. Okay? Conservation of energy occurs when the force is a conservative vector field. So if F is a conservative vector field, then we can write F equal to the gradient of a potential. And to get the conservation of energy law, we usually introduce a negative sign here. Okay? So what does that give us if we then compute this integral using the gradient theorem? So the integral, the work integral of F dot dr over the curve is equal to the negative of the integral over the curve of del v dot dr. And then using the gradient theorem, that's the negative of the final value of v minus the initial value of v. And then using the work energy theorem, that's equal to the final kinetic energy minus the initial kinetic energy. Okay? Can we put all the initial terms on one side and all the final terms on the other? We have a negative vi and a negative ti on the right. We put that on the left. We end up with the initial kinetic energy plus the initial potential energy. We're going to call v the potential energy, is equal to, put all the finals on the right, the final kinetic energy, and then we have a minus Vf goes to the right, plus the final potential energy. So the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And that's the expression of conservation of energy. Okay? So the kinetic energy is quite simple, 1/2 mv squared. The potential energy depends on the force. So it depends on finding a v such that the force is equal to minus the gradient of v. And v is the potential energy. So to work a problem using conservation of energy, which I asked you to do as one of the reading problems, after this lecture, you need to know what the potential energy of the force is. So the reading problem has to do with gravity. So what I should do in this video then is show you what to find the potential energy of a mass little m in the gravitational field of a mass big M. Okay? And then you can use that in your reading problem to compute the escape velocity for a mass from the surface of the Earth. Okay, so how do we set this up? So we have a mass big M. We'll put that at the origin of our coordinate system. So this will be our mass big M. And then we have a mass little m, we have a vector r from big M to little m, right? And then what is the force on little m due to big M? So the force is the gravitational force. It's a force of attraction, so it's pointing in the negative r direction. So we usually put a minus sign. There's a gravitational constant g. There's the product of the two masses, mm. And then it's an inverse square law. So we can write the inverse square law by writing this as the r vector divided by the length of the r vector cubed. Okay? That's Newton's law of universal gravitation. So that's the force on little m due to big M. We want to know what is the potential energy of little m due to big M. So we have to write this as the negative of the gradient of a potential energy. So to do that, we use the following. So this was one of your reading problems. The gradient of 1 over r turns out to be negative r vector over r cubed. So that was something that you should have done as a reading problem. So then this force we can write as, we have a negative r over r cubed, so we can write that as g m big M, little m big M, and then we have a gradient of 1 over r, right? We can go ahead and pull the gradient out. So this is the gradient, or it's going to be the negative gradient of whatever is left over. So we have a negative g m m over r. Okay? So we can write the force as the negative gradient of some scalar field. So then we get the potential then of the little mass m in the gravitational force of big M is then given by minus g, the product of the two masses, divided by r. Okay? That's the potential energy. Okay. You'll need to use this then in the reading problem. So let me summarize. We talked about a conservative vector field. The reason we use the term conservative is because it's closely related to the conservation of energy that physicists absolutely love. We start with the work-energy theorem. So the work done by a force on a mass is this line integral of f dot dr. And that causes a change in the kinetic energy of the mass, the t final minus t initial. So if f is a conservative vector field, then we write f equals minus del v, and we call v the potential energy of the mass in this force field. Because then if we do calculate the work, then we can write it in terms of the potential energy. We can integrate this work integral. And the end result is that the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. We have conservation of energy. We can use the conservation of energy law if we know the potential energy of a given force. Here I look at the force due to a mass big M on a mass little m. The potential energy of little m in this force field is given by minus g little m times big M divided by r, a scalar field. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. In this video, I want to prove the divergence theorem. This is another fundamental theorem of vector calculus. It's called the divergence theorem because it tells you that a volume integral over the divergence of a vector field is equal to the surface integral over the surface that encloses that volume of the vector field dotted into ds. Okay, I should point out that this is a fundamental theorem because what it does is it's reducing a triple integral here, which is a volume integral, into a double integral, which is a surface integral. So just like the fundamental theorem of calculus reduces a single integral into just a valuation of the function itself. Okay, so let's, to prove the general result, we first prove a very specific result, and then I'll show you how using that specific result we can put them all together to get the general result. So let's prove this specific result. So I want to prove the divergence theorem for this box. For convenience, I put the one corner of the box at the origin. So it's just in the positive x, positive y, and positive z direction. X goes between 0 and a, y between 0 and b, and z between 0 and c. So let's write down what this is. So the integral over this box of del dot u dv is a triple integral over del dot u. So this is du1 dx plus du2 dy plus du3 dz. And then integrated over the volume. So we have a dx dy dz. X goes from 0 to a, y goes from 0 to b, and z goes from 0 to c. Okay? We have to apply the fundamental theorem of calculus here to move these to double integrals instead of triple integrals. So the first term, the du1 dx term, we can integrate dx, right? And then we can change the order, and the du2 dy term, we can integrate dy. And then we can change the order for the third term and integrate dz. So I'm going to write this as three integrals. So we have the first term, I'm going to integrate dx first. So we have the integral from 0 to c, the integral from 0 to b of du1 dx. Also the integral from 0 to a of du1 dx times dx dy dz. So the x integral goes first, plus the triple integral, 0 to c. And then the second one, I want to do so the dz is the same, but I want to integrate du2 dy dy, and then integrate dx dz. So z goes from 0 to c, x goes from 0 to a, and y goes from 0 to b. So I changed the order of integration because I know how to integrate du2 dy dy using the fundamental theorem of calculus. And then the third one will be a triple integral. And then we have du3 dz. I want to integrate dz first, and then dx dy. So z goes from 0 to c, x goes from 0 to a, and y goes from 0 to b. Okay, so what have we got? So we can do the inner integral on all of these using the fundamental theorem of calculus. The integral of a derivative is just a function. We have to evaluate it at the limits. So the integral from 0 to a of du1 dx is u1 of a minus u1 of 0. So here we have the integral from 0 to c, the integral from 0 to b, and then we have u1 at x equals a. So a, y, z, minus u1 at x equals 0, 0, y, z. And we still have a dy dz integral. Okay, so that's the first integral. I'm going to run out of space here, but let's try and make it compact. The second integral, we can integrate dy. So we have a double integral here of 0 to c, 0 to a. And then we have the integral of du2 dy will be a u2 at x b z minus u2 of x 0 z. And then we're still integrating dx dz. And then finally, the last piece will be, we still have a double integral from 0 to b and 0 to a. We integrate z now, so we have a u3 of x, y, z equals c, minus u3 of x, y, z equals 0, and we still have a dx dy. Okay, it looks complicated, but actually it is not that complicated. We're integrating del dot u dv over the volume of this cube. Del dot u is just the sum of the partial derivatives. This is a simple rectangular integral. So from x goes from 0 to a, y goes from 0 to b, z goes from 0 to c. Each of these derivatives we can integrate one time, but we have to integrate the first one over x, the second one over y, and the third one over z. We're allowed to switch the order of integration. So I do that, and then I use the fundamental theorem of calculus to integrate. Okay, what do we have here? This first term is, each of these terms now is a surface integral. If we look at this first term, this u1a of yz corresponds to the x equals a face, right? So let me just look at this one. This front face here, right? This face here is the x equals a face. And then this face back here is the x equals 0 face, right? This one should be, sorry, the 3D picture doesn't look good. That one there, okay? So this one is the front face here. So the front and the back face. So this is u1 evaluated at the front face times dy dz. Here, ds in this front face, right? In this front face, ds is equal to the outward-facing normal vector, which is I, times dy dz. So I times dy dz is ds. So u dot ds picks out u1 because of the I here, picks out u1. And the ds will include the dy dz. On the other hand, the opposite face in the back corresponds to x equals 0. Here, x equals 0. The ds for this back face is negative I dy dz because it's pointing in the negative x direction. So we get a minus sign u1 of 0 yz, and we're still integrating dy dz. So this first integral here is the integral over the surface u dot ds corresponding to the x equals a face and the x equals 0 face. This second integral here is the integral over the surface u dot ds corresponding to the y equals b face and the y equals 0 face. The unit vectors are in opposite direction. And this third integral here, corresponding to z equals c and z equals 0, corresponds to the top and bottom face. So the top face has the normal vector in the positive z direction. The bottom face has a normal vector in the negative z direction. So this whole thing then, if I bring it up here, is equal to the integral over this surface of u dot ds. Okay, I hope I convinced you that that's correct for this particular box. Okay, so how do you get from a box like this to the full divergence theorem, which is true for any volume that has a surface surrounding the volume? As long as u has no, u is differentiable, has no singularities inside. Okay, so that's an important caveat. But we're talking here about differentiable functions. How do we get to a general surface enclosing a volume? Well, if you have a general surface enclosing a volume, you can break that up into a bunch of infinitesimal cubes, okay? And then you can do the divergence theorem across every one of those small cubes. It doesn't matter that we place the cube at the origin. The cube can be anywhere. This generalizes. What happens is that the volume integrals all add, but the surface integrals for the surfaces inside of that volume, the surface integrals all cancel. You have a surface normal this way on one cube, and then the adjacent cube has a surface normal exactly in the opposite direction. So you get a plus contribution and a minus contribution from the same surface. So all those internal surfaces cancel. And all you have left is the external surface that has nothing to cancel with. So the volume integral of del dot u dv, all the volumes add, is equal to the surface integral of u dot ds. All the internal surfaces cancel, and you just have left the external surface that's surrounding the entire volume. Okay, so let me review. In this video, I tried to give a rigorous proof of the divergence theorem for a cube with the axes aligned. And then I'm trying to, by waving my hands, generalize that proof to an arbitrary surface enclosing a volume. Okay? There's no point in this course being rigorous about the generalization. So what we have is a fundamental theorem. The integral over the volume, del dot u dv, is equal to the integral over the surface u dot ds. This theorem is satisfied as long as u is differentiable inside the volume, or u is a nice function on the surface. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So in this video, I want to test the divergence theorem. So the divergence theorem is this integral over the volume of del dot u dv equals the surface integral over the surface enclosing the volume of u dot ds, where ds is the normal vector to the surface pointing outward from the volume, and times the element area ds. To test the divergence theorem means I want to compute both sides of this equation and show you that they're equal. So we're going to test the divergence theorem using a vector field u, which is xy times I plus yz times j plus zx times k for a cube of side L lying in the first octant, which means that x, y, and z are all positive here. The faces of the cube are in the planes of the axes. Okay, so let's start with the right-hand side. So to compute the integral over the volume of the divergence of u, we need the divergence of u. So we have del dot u. Remember, this is the partial of u1 with respect to x, which is derivative of xy with respect to x is y, plus the partial of u2 with respect to y. The derivative of yz with respect to y is z, plus the partial of u3 with respect to z. The derivative of zx with respect to z is x. Okay, so that's x plus y plus z. So now we want to compute this volume integral. So we're computing the volume integral, which is a triple integral of del dot u, which is x plus y plus z. And we're integrating over a cube, so that's a simple integration. So we're integrating dx, dy, dz. The sides are length L. The lower back corner is at the origin. So each of these integrals then go from 0 to L. Okay, straightforward integral. Remember, x, y, and z are dummy variables. So the integral, triple integral over x of dx, dy, dz is the same as the triple integral over y of dx, dy, dz is the same as the triple integral over z. So this is just 3. And then let's just do the x one. So then we have dy, dz, so we can separate, we can factor. So 0 to L dz, 0 to L dy, and then 0 to L of x dx. So this will be L. This is x squared over 2, so is L squared over 2. So L times L squared over 2 times 3. So that becomes 3 L to the fourth, L squared, L to the fourth divided by 2. Okay, so this is the left side of the divergence theorem, right? So this is the integral of del dot u dv. So the right side of the divergence theorem, so this is the left side. So the right side, what do we need? We need we have the u is this function. We need the ds, okay? So there are 6 surfaces to integrate over, the 6 sides of the cube. One of them will be at x equals 0. So let's look at the ones that are in the planes of the axes. So one of them will be x equals 0. That's the back face. For that face, the normal vector is in the x direction. So u.ds will just pick out the first component of u. But the first component of u is xy. And x is equal to 0 in the back face. So u then, the first component of u will be 0 on that back face. Okay? So the contribution to the back face will be 0. What about at y equals 0? This left side face here. At this side face, when y is equal to 0, then we have the normal vector is in the minus y direction, right? So that's minus j. And then we pick out, then u.ds will pick out this third one, this yz piece here. But y is equal to 0, so that will be 0 also. The other one will be z equals 0, is the bottom. When z equals 0, then ds points along minus z. So that will pick out, u.ds will pick out zx here, but z is 0, so that's also 0. Okay? So the faces with x equals 0, y equals 0, and z equals 0 will all give 0 contribution to the surface integral. So that remains 3 more faces. So we have x equal to L. So that's the face that's this way here. X equals L. And then what is ds there? So ds is in the I direction, right? In the positive x direction. And then we have to integrate dy and dz. So I, dy, dz. Okay, what about the other faces? So y equal to L. That is this face here on this side. And then the normal vector is in the y direction. So this is ds equal to j. And then we have to integrate x and z. So dx, dz. And the last one will be z equal to L. And there ds, z equal to L. So ds is in the vector, normal vector is in the z direction. So it's k. And then we still have to integrate dx and dy. Okay, now we set up the right-hand side. So we get the right-hand side then is going to be equal to the integral over the surface of u.ds. So we have 3 integrals here. We have one of the integrals will be u.ds. So ds is I, so that's picking out I here. So it's xy, but x is equal to L. So that means Ly times dy dz. So y then goes from a cube of side L, so it goes from 0 to L, and z goes from 0 to L, plus a second integral, which is at y equals L. So we have ds equals j dx dz. So u dot j will be pick out yz. Y is equal to L, so that becomes Lz. And then we're integrating dx dz from 0 to L, 0 to L. And then the last piece here is u dot ds, which is k here, so it picks out zx. Z is equal to L, so it becomes Lx. And then we have dx dy. And that's from 0 to L, 0 to L. Okay, 3 integrals. But remember, y and z in the first integral are dummy variables. X and z are dummy variables. X and y are dummy variables. So in fact, all three integrals are identical. They're all the same. So we only need to do one of them, and it factors. So we get 3, and then L comes out. And then if we do the first one, we have 0 to L y dy, and 0 to L dz. And we still have a little space to write the answer. So 0 to L dz is just L. 0 to L y dy will be y squared over 2 evaluated at L. So it's L squared over 2. So L squared over 2 times L is L cubed over 2 times L is L fourth divided by 2 times 3. So we get 3L to the fourth divided by 2. The same result, okay? So the left-hand side is calculating del.u dv over the volume. The right-hand side is calculating the integral of u dot ds over the surface. And in both cases, we get 3 times L to the fourth over 2. Okay, I hope I demonstrate now the divergence theorem for this particular case to show you that it works. You know, that's the thing about theorems in mathematics. They're supposed to always work. So if it didn't work, it means that I would have to reshoot the video because I made a mistake. But I didn't. We got a match. And that's the example of divergence theorem in Cartesian coordinates. Next up will be an example of the divergence theorem in spherical coordinates. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. So in this video, I want to try and test the divergence theorem again, a second time. The last video, we used a problem in Cartesian coordinates, because we were talking about a box. In this problem, I want to use spherical coordinates, because we're testing the divergence theorem in a sphere. So I want to test the divergence theorem using a vector field, which is r squared, the length, the distance of the point to the origin squared, times r hat, the unit radial vector, for a sphere of radius capital R centered at the origin. So the sphere looks like this. So we're going to test the divergence theorem. So I want to compute both the left-hand side and the right-hand side and show you that they're the same. So we need the divergence of this vector field. So we need del dot u. Now is the time to use del dot u in spherical coordinates, because the vector field u is given in spherical coordinate variables. So what is the form here? So you don't have to remember it, but you should go back in the notes and look it up. Okay, so we're looking at the divergence of u in spherical coordinates. So the first term is a 1 over r squared times d dr of r squared u sub r. So that's the component of u in the r hat direction, plus other terms that depend on the component of u in the theta direction and in the phi hat direction. But there is no component of u in those directions. The only component that u has is in the r hat direction. So all these other terms are 0. Okay? That's typically what happens when you're working a problem in spherical coordinates. You usually have some type of symmetry associated with the sphere. So you get a nice simplification here. So u sub r is r squared. So that's 1 over r squared. And then there's only an r dependence, so I can just write that as d dr. And this would be r to the 4th. These other terms here are all 0. Okay? So we have the derivative of r to the 4th is 4r cubed. So 4r cubed divided by r squared will be just 4r. Okay? So del dot u is 4r. dv is our volume element in spherical coordinates. So that's r squared sine theta, dr, d theta, d phi. Remember, that's coming from the Jacobian of the change of variables. The Jacobian is r squared sine theta. Okay, so let's put it together. The left-hand side. So we have the integral over the volume of del dot u dv. So we have a triple integral here, but the integral over the angular elements is one of the problems in the homeworks I give you. The integral over the volume element is just 4 pi. So this is equal to 4 pi times the integral over the r direction, which will be 0 to big R. And then we have 4r times r squared, so 4r cubed dr. And this will be r to the 4th over 4, which is just r to the 4th times evaluated at big R. So this will be 4 pi r to the 4th. Okay? So I did a shortcut here. I did the angular integration. If the function multiplying this only depends on r, which it does here, 4r, then you can do the angular integration immediately and get 4 pi. Okay, so that's the left-hand side. What about the right-hand side? So the right-hand side is this surface integral of u dot ds. So on the surface of the sphere, then u, on the surface, right, then little r is big R. So u is equal to r squared r hat on the surface. Okay, so this is going to be the left side here. And then ds, what is ds? ds, so the normal vector is r hat. And then the ds element here is going to be our dv volume element, except that r is going to be capital R squared. And then we have a sine theta. And we're no longer dr because we're just on the outside of the sphere. So we just have a capital R squared d theta d phi. Capital R squared sine theta d phi. Okay? This is something that I haven't taught you yet. But if you have a surface element of a sphere, you basically have a fixed radius. So you put the radius in the r squared. We're not integrating over r, so there's no dr, but we still have this sine theta d phi. Okay? Something you should know. Okay, so let's put this together. So we have the integral over the sphere of u dot ds. So this will be u dot ds. So the r hat dot dr, r hat dot r hat becomes 1. So we have an r to the 4th. So we have an integral over the surface of r to the 4th sine theta d theta d phi. So we're integrating. Theta goes from 0 to pi. Phi goes from 0 to 2 pi. Again, this is the integral of over the angles of sine theta d phi is 4 pi. And r to the fourth just comes out. So this gives us 4 pi times r to the fourth, which is the same. OK. So I tested the divergence theorem. The left-hand side is the same as the right-hand side. So let me review. We're doing spherical coordinates now. We have to pull the divergence of u in terms of spherical coordinates. You don't remember this. You look it up. There's only the first term because u just depends on it's just u sub r hat. So you only have the first term contributing. And then you can calculate it. That's 4r. Then we need to integrate 4r over the volume. The angular part will give you 4 pi. And then you have an integral over r, which gives you r to the fourth. Okay? On the other hand, if we compute the surface integral of u dot ds, then u on the surface of the sphere is the radius of the sphere. Capital R squared times r hat is the normal vector. ds we get from the angular part of dv times r squared, capital R squared, and that's in the r hat direction. And then we do this integral, and again we get 4 pi r to the fourth. Okay, this is a bit sophisticated now. We're able to work both in Cartesian coordinates and in spherical coordinates. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. In this video, I want to derive the continuity equation in fluid mechanics for fluid flow. Continuity means continuous. What is continuous here is the fluid itself, right? So you have fluid can be transported from one location in space to another. Its density can change, but it has to do it continuously. So how do we derive, why are we doing this in this lecture now? We're doing it because it uses the divergence theorem. It's a nice theoretical application of the divergence theorem. So to derive the continuity equation for a fluid, we need two quantities. One is rho, which is a function of position in the fluid and time. Corresponds to the fluid density. The mass per unit volume. The other is u, which is a vector field, which is a function of position and time. And that corresponds to the fluid velocity, right? The length per unit time. Okay, to derive a continuity equation, you consider a test volume. It can be any shape, any size. So this is called a test volume. And it's enclosed by a surface. So it's a test volume V, enclosed by surface S. Okay? And then let's try and write then how the mass of the fluid in this test volume changes in time. So we're writing an equation for the dm dt, the derivative of the mass inside this test volume as a derivative with respect to time. The mass of fluid in this test volume changes because of the mass flux through the surface. So I introduced the mass flux before. So it changes, it will decrease when the mass moves through the surface. The flux of the fluid mass through the surface is given by a surface integral through the surface. And then we have rho times u dot ds. So the units of this right-hand side is mass per unit time. The left-hand side is mass per unit time. And the mass, the time derivative of the mass in this test volume is equal to negative of the mass flux through the surface. Okay? So this is essentially the continuity equation. We want to put it in a more standard form. A more standard form would use m. So the mass in this volume is a volume integral over the density dV, right? The mass per unit volume integrated over the volume. That's the left-hand side. So then if we want to write dm dt, that's the time derivative of this. Rho is a function of position and time, but the volume integral is the integral that you're integrating over is independent of time. So we can bring the time inside of the integral. So that would be the integral over the volume, and we'll need to use a partial derivative here because rho is a function both of position and time, dv. Okay? So that will be the left-hand side. The right-hand side will use the divergence theorem. So we have the integral over the surface of rho u dot ds. Applying the divergence theorem becomes an integral over the volume of the divergence of rho times u dv. Okay? And that gets a minus sign on the right-hand side. So if we bring the right-hand side into the left-hand side, and we use these two results, so the minus sign on the right becomes plus on the left, and put them all under one volume integral, we get the volume integral of d rho dt plus del dot rho u dv equals 0. Okay? So our continuity equation, dm dt equals minus the mass flux, becomes a single volume integral. The volume integral of d rho dt plus del dot rho u dv equals 0 by way of the divergence theorem. Okay, this is true for any test volume. The test volume can be anywhere in the fluid flow. It can be any shape, any size. The only way this is true for all volumes V is if the integrand equals 0. So that gives us the usual form of the divergence theorem, which is d rho dt plus del dot rho u equals 0. Okay. Standard form for a divergence theorem, for a continuity equation, the standard form of the continuity equation. There's a special case that's called an incompressible fluid. So for an incompressible fluid, we have the density is a constant. Okay? So a typical fluid, such as a liquid, is very hard to compress it. If you can't compress it, you can't change the density. So typically for a liquid, the density is a constant. A gas is easier to compress. You have these tanks of compressed air. You can compress a gas. So for a gas, sometimes this condition doesn't hold. But if rho equals constant, d rho dt is 0 then, and rho can be pulled out of the divergence. So then we get the incompressibility condition will be del dot u equals 0. Okay? Del dot u equals 0. Physically, what that means is that if you have some volume, whatever flows into the volume has to flow out. Okay, we'll see that's the meaning of del dot u equals 0. There are no sources or sinks of fluid, and fluid cannot get compressed inside of that volume. Okay? So let me recap. In this lecture, I derived the continuity equation for a fluid. The reason I'm doing it here is because the derivation converts this mass flux integral using the divergence theorem into this divergence of rho u dv integral. And by doing that, we can combine both the left-hand side and the right-hand side and end up with this partial differential equation that's called the continuity equation for fluid flow. If the density is a constant, it reduces to del dot u equals 0, or u has 0 divergence. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video. Okay, so far we've talked about the divergence theorem. This is one of the most important theorems in vector calculus, having to do with the divergence of a vector field. The other very important theorem is called Stokes' theorem. That has to do with the curl of a vector field. To introduce you to Stokes' theorem in a more gentle way, I want to start with Green's theorem, which is essentially Stokes' theorem in 2 dimensions. Okay? So for Green's theorem, we have a vector field in the xy plane equal to u1, which is a function of x and y, times I, the unit vector in the x direction, plus u2 of xy times j, the unit vector in the y direction. So Green's theorem says the integral over an area or a surface in the xy plane is equal to du2 dx minus du1 dy. This should look to you like the third component of a curl. ds is equal to a line integral, which is essentially u dot dr in the plane, which is u1 dx plus u2 dy. And the line integral then is enclosing this surface. This is the surface S here. Okay, this is our S. Okay, and this curve here then is our C. So first I will prove Stokes' theorem for this rectangle, and then argue in the same way I argued for the divergence theorem that this can be extended then to an arbitrary area surrounded by a curve. Okay, so let's write down the left-hand side of this equation. So we have the integral over the surface of dut dx minus du2 dx minus du1 dy ds. This is a double integral. So this is a double integral of du2 dx minus du1 dy dx dy, because we're in the plane. And then x goes from a to b, and y goes from c to d. So this is an area integral. Okay, this is a fundamental theorem. So we're going to use the fundamental theorem of calculus to remove one of these derivatives and lift it up into a curve integral instead of an area integral. So the du2 dx, we can integrate dx. So the first piece here gets integrated dx. The first term gets integrated dx. So we have the integral from c to d. Using the fundamental theorem, that will be u2 of x equals b, y, right, minus u2 of x equals a, y, dy, minus, then we can reverse the order of integration and integrate the second term with respect to y. So then we have an x integral remaining. So we have an integral from a to b. And then we end up with a u1. So we have x. And then y at the top limit will be d minus u1 of x. Y at the bottom limit will be c. And this is dx. Okay? So let's look at the dx piece. The right-hand side says it should be an integral over the curve u1 dx. So we have a minus sign here. So this minus sign and this minus sign would be a plus sign. So this is the integral of u1x when y is equal to c. So let me label the terms. This is number 1 here. That's an integral when y is equal to c, and it's positive. So that's this bottom integral. That's a 1. This one is minus the integral from a to b u1 of xd dx. Y is equal to d, and it's negative, meaning it's in the negative x direction. That's number 2 up here. That corresponds to 2. Okay? Finally, in this first integral, we have positive, the integral dy, u2 of by, let me call that 3. So we're at x equals b here, and we're in the positive y direction. That's number 3. And then finally, we have in the negative sign, u2 ay dy. We're here integrating dy, x equals a. This is in the negative y direction, so it gets a negative sign. So this is number 4. So putting this together then, we have the integral here, which we can write as the integral over this closed curve of u1 dx plus u2 dy. Okay? That's a Stokes theorem in the plane, which is called Green's theorem. Okay? That's valid for a rectangle where the sides line up with the axis. So we can extend this then to an arbitrary shape by using the following trick. So if we take 2 of these rectangles, they can be as small as we like, and then we glue to it to another rectangle. So this one's going down, like so. We apply Green's theorem to both of these areas. You see that the left-hand side, the integral over the area, will add, because you're integrating this area on the left and this area on the right. The areas add. But the integral over the curves, the internal lines cancel. The inside line, this one's going up. The one next to it is going down. Those curve integrals will cancel. And the only thing you have left then is the outer integral, right? So given any sort of area in the plane, you can divide it up into very tiny rectangles, and then the inner lines in the curves of the rectangles will cancel each other, and all you'll have left is the outer curve. So that means Green's theorem will give you this surface integral, or area integral, is equal to the line integral where the line is surrounding the area. Okay, so let me review. Green's theorem is, we'll see that this is Stokes' theorem in the xy plane, in the two-dimensional plane. It says that the integral over this surface, which is an area in the xy plane, of du2 dx minus du1 dy ds is equal to the line integral around the curve that is surrounding that area, u1 dx plus u2 dy. This is a closed curve. In the next lecture then, I will derive Stokes' theorem by just extending Green's theorem to 3 dimensions. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. So the two most important theorems of vector calculus are the divergence theorem and Stokes' theorem. Stokes' theorem is the 3-dimensional generalization of Green's theorem, which I discussed in the last video. So how do we generalize Green's theorem to 3 dimensions? I mentioned that this du2 dx minus du1 dy looks like a curl. In fact, du2 dx minus du1 dy is the curl of u, but it's the third component, so dotted into the unit vector in the z direction. Okay? In order to get del cross u dot k here, then we should define ds vector will need to be this k times ds scalar times the surface area. Okay? Finally, this u1 dx plus u2 dy is simply u vector dot dr. Putting everything together, we end up with the integral over the surface of del cross u, dotted now into ds, right? And that's equal to the integral over the closed curve of u dot dr. And that's Stokes' theorem. Okay? The generalization of Green's theorem to 3 dimensions. I won't prove it here, but we can see that this 3-dimensional version just reduces to Green's theorem in 2 dimensions. But then this one is valid in 3-dimensional space. So U is a vector field in 3 dimensions. This is the curl. We're dotted into the, we have a some surface, not a closed surface like in the divergence theorem, but an open surface where it's bounded then by a curve. So there's a curve and then there's a surface. So in 2 dimensions we have a curve and the inside is the surface. So now the surface can be 3-dimensional, but then it has a lip which corresponds to the curve. So the integral of del cross u dot ds on the surface is equal to the integral over that lip, that curve, u dot dr. So there's one technicality here that you have to be aware of. It's easy to see it in this rectangle, so let's look at the rectangle. The curve here is a directional curve. The surface is the inside. So the question then is, how do you determine which direction k is in here? So k can be coming out of the screen or going into the screen. So you have to choose which one. Here, del cross u, k is x I cross j, k. So the k direction here is coming out of your screen, right? You use the right-hand rule, my right hand. You put your fingers in the I direction and cross it into the j direction. So the k direction then is coming out of the screen. So that means ds then has to be coming out of the screen. Another way of doing that in general is that you move your fingers along the curve direction. So the curve is going here and up. And you curl your right hand, your fingers in the direction of the curve. And then the normal vector to the surface points in the direction of your thumb. So here it's coming out of the glass. So that's a very important point in order to get the signs correct in this expression. And it relates to the definition of the curl in terms of the right-hand rule. Okay, so let me review. All I'm doing in this video then is pulling Green's theorem from the xy plane and showing you how to rewrite that so it would be valid in a three-dimensional setting. Okay? We're not actually proving Stokes' theorem, but I'm showing you what Stokes' theorem would have to be if we generalize Green's theorem. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. In this video, I want to talk about the meaning of the divergence in the curl using the divergence theorem and Stokes' theorem. We'll end up with a definition of the divergence in the curl of a vector field which is coordinate-free, doesn't depend on Cartesian coordinates or cylindrical coordinates or spherical coordinates. So let's start with the meaning of the divergence. So we start with the divergence theorem. So the divergence theorem says that the integral over a volume of del dot u dv is equal to the integral over the surface that the volume is within of u dot ds. Okay? So you have some volume that's surrounded by a surface. Okay. How do we get the definition of the divergence of u from this divergence theorem? Well, we can take our volume and shrink it down to a point, okay? And then the integral will just become del dot u times the volume associated with that small volume, you know, but we're limiting to a point. So that gives us del dot u equals the limit as this volume then goes to 0 of 1 divided by the volume of this surface integral of u dot ds. Okay? So from the divergence theorem, we can actually have a definition of the divergence of a vector field in terms of this limit. Okay? Coordinate-free. I don't say whether we're working in Cartesian coordinates or spherical coordinates. So from this definition of del dot u, let's see if we can construct some type of physical meaning of del dot u. Let's look at, say, a volume surrounded by a surface. I take something like a sphere. If u dot ds was equal to 0, this would be like putting a sphere in an incompressible fluid. So if you have a fluid flow, that looks something like this, right? The density of the fluid doesn't change. So the flow that's going through the surface, the amount of fluid going through the surface is equal to the amount of fluid coming out of the surface. So in this case, fluid in equals fluid out. So u dot ds equals 0. So here del dot u is 0. Okay, so this is fluid in equals fluid out. Okay, and that's the incompressibility condition for a flow. So whatever goes in goes out. So the density of the fluid doesn't increase in the sphere or doesn't decrease in the sphere. Okay. Then when can you get this surface integral of u dot ds different from 0? Okay. So here is an example. You have our surface surrounding a volume. Let's say you have some hose or something here, and out of the hose you have fluid flowing, right? So you have fluid flowing here. Okay? That's called a source, right? A fluid source. And here you have the integral over the surface u dot ds then, because you have fluid coming out, would be non-zero. And in fact, then, because the limit as v goes to 0, you would have del dot u would diverge, would become infinite. But in any case, you can have more gentle situations than a pure source like this. Here you have del dot u being positive. Okay? On the other hand, you could have a drain, and that's called a sink, and then fluid flowing into the drain. And here you would have del dot u being negative. Okay? So that's kind of the physical picture one should have of the divergence. If there's no sources or sinks, then typically the divergence is 0. And then if you have a source, the divergence is positive. If you have a sink, the divergence is negative. Okay. So what about the meaning of the curl? So the meaning of the curl means we will use the Stokes theorem to get the meaning of the curl. So Stokes theorem has a surface and a curve. So the integral over the surface of del cross u dot ds, right, is equal to the integral over the curve, which is bounding the surface, of u dot dr. So that's Stokes' theorem, okay? So we have our del cross u here. So we have a surface, could be three-dimensional, but it's not a closed surface. It has one, it's bounded then, has a lip on it that is a curve, okay, a closed curve forming the lip of the surface. If we want a coordinate-free then definition of del cross u, we can limit this by shrinking the surface then down to a point, down to the surface of a tiny area around the point, right? Say a disk around a point. And how do we limit this? Well, we end up with then del cross u. We still have the normal vector to the surface. So I'll choose a unit normal vector here to the surface. And then this is going to be equal to the limit as that surface goes to 0. We have the surface here, S. So we have 1 over S times this closed curve integral of u dot dr. Okay? And then this is our coordinate-free definition of the curl. Because the curl is a vector, we have to look at a component of the curl. The component here then is the one that's parallel to the normal to the surface. Okay, definition of the curl. So let's look at how this works. So we have a surface. Let's look at then a disk in the plane, right? So this is the surface S. And the surrounding, the bounding curve then is here. That's our C. So this is the surface S. This is our curve C, right? The normal vector, if you use your right-hand rule, so you point your fingers along the curve, the normal vector then will be going towards you, out of the screen towards you, right? That's the normal vector. So we're looking at the curl of u in the direction of the normal vector, okay? So that's equal to this limit, but within the limit then we're looking at the integral of u dot dr. So if the integral over this curve of u dot dr equals 0, then the curl will be 0, right? So how do we get a u dot dr around the curve not equal to 0? Well, that's if the fluid is somehow circulating, right? So you have a fluid flow that is moving around in some sort of circulation, okay? This looks like turbulent fluid, right? So del cross u in this case is not equal to 0. And that's called vorticity in fluid motion, okay? And vorticity is essentially associated with the eddies of, say, a turbulent fluid. So you end up with a swirling fluid, and then you can get the curl not equal to 0. Okay, so let me review. What the divergence theorem and Stokes' theorem can give us is a coordinate-free definition of both the divergence and the curl. And it can also give us some physical meaning. The divergence of a vector field is 0 for an incompressible fluid. Whatever flows in through a surface flows out. But if you have sources and sinks, then you can have a non-zero divergence inside of that volume. The curl is non-zero when you have some sort of swirling motion in the fluid. This is a rather generalization, but this is a good way of thinking about it, that the curl of a vector field is what's called vorticity, and it's related somehow to the swirl of the field. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video. In this video, I want to show you how our knowledge of the divergence theorem and Stokes' theorem can be used to convert what's called the integral form of Maxwell's equations into their differential form. So we have 4 of Maxwell's equations in integral form. We have Gauss's law, which tells you that the surface integral of the electric field is equal to the charge enclosed. We have these 2 constants. Epsilon naught is the permittivity of free space, and then mu naught is the permeability of free space. These show up in the SI unit system that engineers typically use. So we have Gauss's law. Then we have Gauss's law for magnetic fields, which is the same as Gauss's law for electric field, except the right-hand side is 0, and we say that law states that there are no magnetic monopoles. Then Faraday's law, the integral of the electric field around a closed curve is, so if you have a closed curve and then you have a magnet that you move in and out of this wire, this circular wire, then you have a time-varying change in the B, you end up with an electric field. So actually it causes a current to flow in the wire. That's Faraday's law. So Faraday's law was important because it was the first time someone showed a connection between the electric field and the magnetic field. Then we have Ampere-Maxwell's law, which gives you the integral of the magnetic field around a closed curve is equal to this constant mu naught times the current that the closed curve that passes through the closed curve. That's Ampere's form of the law. And then Maxwell added this very important second term that was then enabled the Maxwell's equations to predict the electromagnetic waves. Okay, so how do we convert these integral form of Maxwell's equations to differential form? Well, we need to replace the charge and the current by the charge density and the current density. And the formula is that this charge, or the charge enclosed, is going to be equal to the integral over the volume of the charge density times dV. And the same for the current. The current enclosed by this loop is going to be equal to a surface integral of the current density dotted into ds, the surface element. Okay? With those definitions of a charge density and a current density, then we can manipulate the Maxwell's equation. So let's start with Gauss's law. So we have Q now is rho dV. So it's integral over a volume. So we can use the divergence theorem to convert the closed surface integral into a volume integral. So Gauss's law can become an integral over a volume. And then we have del dot E from the divergence theorem. And then we can bring the right-hand side to the left. So we have a minus rho over epsilon naught. And then integrating then dV. And that's supposed to be equal to 0. Okay? So application of the divergence theorem, replacing the charge by the charge density, gives us this integral equation. But this is true for any volume. Okay? So if it's true for any volume, the integrand has to be identically 0. And that's the Gauss's law in differential form. So we get del dot E equals rho over epsilon naught. Okay? So that is the first of Maxwell's equations in differential form. We can do the same thing for Gauss's law for magnetic fields. Here we just apply, this just becomes del dot B dV equals 0. So immediately you can see that del dot B then has to be 0. And that would be Gauss's law for magnetic fields, which basically says there's no such thing as a magnetic monopole. Okay, how about Faraday's law? Here we have an integral over a closed curve, so we can apply Stokes' theorem and convert that to del cross E dot ds. So we have then the integral over a surface. We have del cross E, applying Stokes' theorem. And then the d dt we can bring inside of the integral sign. B is a function of position and time, so d dt on the outside, because we're integrating over the position variable here. When you bring it in, it becomes a partial derivative. We bring it to the left-hand side, it becomes plus partial of b with respect to t. And then this whole thing then is then dotted into ds and is equal to 0. Okay? So again, this is true for any surface enclosing any surface. And so if it's true for any surface, the integrand has to be 0. So we get the differential form of Faraday's law then would be del cross E equals negative dB dt. And that's the third of Maxwell's equations. Okay, now what about the Ampere-Maxwell's law? Well, it's the same idea then. We convert B dot dr into del cross B dot ds. So we have the integral over a surface. We have del cross B. And then we bring the right-hand side to the left. The I enclosed then becomes, we want to change I enclosed into this integral over the surface of j dot ds. So we have a minus mu naught. And then we have a j, right? And then we have a plus epsilon naught. We have this surface integral here. So again, we bring the d dt inside of the integral. So it becomes partial E with respect to t. Okay, this whole thing multiplied by mu naught. And then this whole thing, then this is a vector, gets dotted into ds. And that's supposed to be 0. Okay? So it's almost the same as Faraday's law, except we have one extra term, which is the current here, and then we replace that with the current density. So again, this is 0 for any surface, and then we can write down the fourth Maxwell's equations, which will be del cross B then is equal to mu naught times j plus epsilon naught dE dt. And that's the differential form of the Ampere-Maxwell's equations. Okay, let me put a nice check here. So we got 4 Maxwell's equations. Okay, so let me summarize. The purpose of this video is to show you the power, the theoretical power of the divergence theorem and Stokes' theorem. So in a beginning electricity and magnetism course, typically you learn Maxwell's equations in their integral form. And then when you move to an intermediate electricity and magnetism course, you finally learn them in their differential form. Because in order to get from kind of the experimentally accessible integral form to the differential form, you need to know some vector calculus. I'm Jeff Chasnov. Thanks for watching.